Hi everyone and welcome to this new video. This video is the full compilation for the Linux privilege escalation series. Now the series is over, it's officially over. There are 14 episodes in total and in this video I just put them all together so it will be easier for you to watch. So, what did we cover in this series? In the first episodes, we introduced the idea of Linux, the Linux operating system, and how we can interact with the Linux operating system. That is the concept of the Linux shell, how to use it, what can we do with it, and also how the file system can be configured and how the permissions in the file system work. This is because in terms of security, one of the critical points is permission. It's like, how do you set up the rule to define who can access what kind of data? How do you define the policies for executing binaries, for reading configuration file and modifying files? How do you set it all up? How do you read it? How do you understand it? And how can you exploit it? So always in terms of security, the first step is always understanding the system regardless of security. You just want to get to know how the system works. Then moving on from the third episode to the 8th episode, essentially, we show different exploitation techniques. So PATH Hijacking, SUID Exploitation, SUDO Exploitation, wildcard expansion exploitation, the Unshadow attack. And then in the 7th episode, which was a little bit different, we showcase how to deal with reverse shells in Linux. So what are reverse shells, why they are interesting, why we should use them when we are exploiting a system. And so this is like the basic idea. After that, we did 3 episodes on enumeration, so system enumeration, which means the enumeration of the entire system with the most important resources and information. Cronjob Enumeration, which is specific to the aspect of cron jobs, which are tasks that are executed asynchronously on the system. So how can we know if such tasks are executing? How can we understand which task and how can we exploit misconfiguration in the cron job system? And finally, we saw capabilities enumeration for the enumeration portion of the system. So after that, we finish with 3 more exploitation techniques. One is specific to local services. So this has to do also with port forwarding, because to access a local service on the server or to expose your local service to the victim machine, you need port forwarding techniques. And I showcase how to do this with SSH, which is the typical scenario you will often find in various CTFs and things of the sort. And the final 2 episodes were a little bit more advanced because they talk about Linux binary exploitation, that is the exploitation of Linux binaries, the fact that if a binary contains a vulnerability, like a memory corruption vulnerability, an attacker can take that binary, can craft a specific malicious input and can hijack the execution flow of that specific binary. And sometimes, if the binary is configured to run as root user, as the root user with root privileges, this hijacking of the execution path can bring forward a privilege escalation scenario. So it's dangerous to do. It's also hard. I just showcase a simple 32-bit Stack Overflow attack, but of course in modern systems there are much more rich and complex attacks that you can still do if the binary is vulnerable. And finally, in the last episode, we talk about Linux kernel exploitation. So not binary anymore, meaning that the Linux binary exploitation was focused on the user space, which is the space we typically interact with and most applications are written in. But everything that happens in user space is supported by code running in kernel space. For example, system calls are the way to interact with the kernel code, with the kernel services that are implemented by the Linux kernel. And so Linux kernel exploitation tries to exploit exactly that code, the code that runs at kernel level. If there is a bug in that code, through the specific usage of system calls in a malicious way, an attacker can abuse that to obtain once again privilege escalation, to hijack the flow of the kernel code and obtain privilege escalation. So there's really a lot of subject that we cover in this series, all has to do with Linux privilege escalation. Now, of course, I did not show all the possible techniques you can use because these are actually infinite. Depending on the program, depending on the configuration, depending on the system, you have a lot of possibilities. In this series, I wanted to bring the most important techniques and the techniques that will give you the most in a penetration testing engagement, in a CTF, in a exam, a certification exam, like the OSCP exam. So my focus was on capturing the essence of the most important systems. For example, how the path is handled, how the SUID system works, how the SUDO utility works, how Cronjob works, how capabilities works, and so on and so forth. So this was the idea with the series. I hope you can enjoy it. If you want to support me, subscribe to the channel. Just check out my content online. I have a blog, I have this YouTube channel. I have also a YouTube channel in Italian, but that is only if you understand Italian. And just keep following my work and enjoy the video. Hi everyone, and welcome to this new video. In this video, I start a new series, and this series will be about Linux privilege escalation. So this is going to be the first video of the series, and in this introductory video, we will introduce the idea of the Linux shell. So we will discuss a lot of different concepts, and you can find them here. We will go into a lot of details here. Now, regarding with this series, with respect to the other videos that I'm planning to make, for now, this is my idea. Of course, it could change with time as I go further into the series, but the idea essentially is that I've already covered the path hijacking video, so that is already done. And then I want to talk about file permission, SUID exploitation, SUDO exploitation, wildcard expansion exploitation, and then finally some enumeration, general system enumeration, and Cronjob enumeration specifically. So this is my idea for the series. Once again, my target is, for example, an OSCP certificate. So this means that if you understand all the concepts that I cover in this series, and you do, of course, a lot of practice, because theory is important to have, but then you need to do a lot of practice and just laboratories. If you know all of this and you are used to like doing these techniques, then you will be able to obtain an OSCP certification, or anyways, you will have the required knowledge with respect to the Linux area. So my target for this series, for the web exploitation series, which I've just finished, and also for the Linux privilege escalation and the Windows privilege escalation that will come, is OSCP. I'm trying to like build a foundational OSCP knowledge. Once I've done that with all the series, we can go further. We can go more in depth, more difficult topics. So now that I've introduced everything, we can actually go into the content of the video. So the first thing that I want to do is I want to showcase this simple Docker file. This creates essentially a container that has SSH login on. And I'm doing this to create a playground when we can actually play with the shell in order to understand how it works. So this is the Docker file. It creates this sort of container, this environment where we can play with the shell. To actually build it, we need Docker installed in our system, and then we can execute these commands. So Docker build to build it, Docker run to run it, and then we can either do Docker execute to obtain a shell, or we can actually log in with SSH. And the credentials here are SSH user and password. Now in my system, the one I'm using, I've already run it, so we can just log in with SSH. And this is essentially where I wanted to start this video. So consider this SSH command. This is a command that we can execute through a command shell, through a Linux shell. Now this command is made of various parts, and when we want to understand how the shell functions and how we can use it, we need to understand every part of this command. Now, first of all, why should we use the command line? Why should we use the CLI, which stands for Command Line Interface? So this is a way in which we can speak with the computer. It is an interface, but instead of being a graphical interface, a so-called GUI, which stands for Graphical User Interface, so graphical user, this time is a command line interface. It means that to interface, to interact with the computer, we use commands. And commands are a string of text. They are just a sequence of specific characters that have a specific structure, and we will need to analyze this structure. But the idea is that instead of having buttons in the screen where we can click on them, we have strings, we have commands that we can execute. Now, why should one learn the CLI instead of sticking with a GUI? Well, the idea is that even though GUIs initially can be helpful, especially when we are at the start of our journey into learning cybersecurity or computer science, the thing is that the GUI long-term has certain downsides that we only see when we become expert in cybersecurity or computer science. Specifically, GUI are extremely complex to handle, and typically they are easy to use with the mouse, with the keyboard, but they always require some kind of manual interaction, some kind of user interaction, like a user sitting in the computer clicking on stuff. That's like manual effort every time. The power of the command line is that once we learn how to use it, we can automate stuff, we can script, we can write programs that do things automatically, that perform like commands and operation on the operating system without any user interaction, based only on the output they get from other commands, on the state of the computers, and so on and so forth. So the idea is that even though at first it may seem that CLI commands, that command line interface, is just boring and hard to learn, in the long term it will actually save you lots and lots of hours, and you will be glad to have learned it. I mean, this is the idea. Like when I started to learn computer science, I was like, wait a second, this command line is very, very hard. I need to remember all these commands, I need to write them out, etc., etc. But then I actually learn the power of the command line, the fact that I can automate stuff, that I can write script, and it is a very efficient way to interact with the computer, to talk to the computer and obtain information about its state. Because the idea is that at any time the computer has a certain state, and if we want to operate properly on the computer, if we want to use it, if we want to use it with all of its resources, we need to understand how to extract the state, how to understand the state, and how to execute specific commands to move the state in specific directions. So that's the idea. For example, in this SSH command, what we see is that the first part is the name of the command. So this defines the program we want to use, and every command line program has a name. Actually, even every GUI program has a name, because ultimately the command line is the first way we interact with the computer. First we interact with the command line, and then we tell the computer to spawn graphical interfaces. So it means that GUI are built on top of CLIs, on top of command line interfaces. So that's the idea. So the first part is the name. Then every command has different options that sort of modify the behavior of the program. This is because, of course, programs are really, really complex and they have to interact with the user. So we have to tell the program how to behave exactly, which means that each program will have a different set of options, and these are specified in different ways. Now, this is where the complexity of command line sadly arises. This is never truly easy, and the best way to handle this is to read documentation and write your own documentation with respect to how the options are written, essentially. So for example, consider this case. Now, SSH is used to create a secure communication channel between two endpoints. So essentially is that we have two TCP ports, one here and one here, and we want to create a secure channel on top of this, which means that the data that is transferred between these two TCP endpoints must be encrypted and must be protected with respect to integrity also. So a lot of cryptographic protections. Now, to do this, what we say is, essentially we have to specify the machine to which we want to connect. And here we do it with this syntax. So this is the username. We want to log in into the machine. And this is the IP address of the server that is listening, because SSH has a client-server architecture, and in particular, this command SSH implements the SSH client. So this is the open source SSH client, so it's implemented in this command. And so we say, look, I want to connect with SSH to the server running at 127.0.0.1 with username SSH user. Now notice that since we are connecting with TCP, it is assumed that we need to know the port, the TCP port where the SSH server is listening to. In this case, we are not specifying the port because implicitly we are using the default port 22, which is assigned to SSH. Now this is like an implicit stuff, we don't put it into the command line because the program already knows. So every time the program already knows the data, we don't need to explicitly tell the program. However, for example, let's say that we had a different SSH server listening on port 77. Now in this case, I will need to tell somehow with using certain flags how to connect to that port. And the fact that it was not port 22 that I was interested in, but rather port 77. So this is the first thing. But notice that after the SSH and before the SSH user @ which stands for username IP address, here we have another thing. Now this is called an option, and essentially it modifies the behavior of SSH. In particular, I'm telling SSH to do a certain operation. Now every time I connect with SSH here, if I remove this, what it does is it tries to understand the authenticity of the machine I'm connecting to, of the host I'm connecting to, by analyzing its public key, the fingerprint of its public key. And it asks me, do you want to save this for future connections, so that future times, if you connect to the same IP and port, you will get the same fingerprint. Essentially, a check will be made to make sure that the fingerprint has not changed, because this could mean that the machine has been compromised, so we don't want that. So it asks us if we want to save this fingerprint or not. And typically, if we say yes, I want to save it, it saves it into a system file that is actually not system, but it's like based on a specific user. So it saves this fingerprint on a specific file, and I don't want to do that. So essentially here what I have to do is I just have to do this to say, look, okay, we go into terminal, and you have to say, look, I don't want you to save this fingerprint for long term. I just want you to connect. So it says I can say yes now, and when it's gonna try to save the file, to save the fingerprint within the file, it will actually just discard it. And now it asks me for the password. The password is found in the Docker file, so it's this one. It's called password. So I can just copy, paste it, and now I am inside. I am inside the Docker. I've successfully run the SSH command, and I can do various commands that we will talk about now. Now, in order to use this command, we had to answer the following questions. So first of all is, what kind of program do I need to access that functionality? In this case, it was connecting with SSH. So every time we have to operate with the computer, we have to do different actions, and different actions are done with different programs. So one of the things that you need to master if you want to use the Linux shell is understand which programs does what, to make sure that every time you have to do a specific action, then you already know the program that you need to use. So this is the first question, is that what program do I need to use? In this case, we had to connect with SSH, so the program we needed to use is called SSH. Now, to use SSH, of course, we have to connect to a specific server. So the next question is, okay, what kind of IP address is the server I'm trying to connect as? So what is the IP address I'm trying to connect to? And then what is the username? And then what is the password? And then if I want to make the program behave in a certain way, for example, by not saving the public key of the server, then I need to know, okay, but what kind of option allows me to modify the default behavior of the program to avoid saving the public key option? So this is all the complexity of the Linux shell. And in this video, I will start with some basic concept to help you get started playing with the shell. So a useful starting point is to understand the difference between concept of like terminal, TTY, and shell. In this case, it's like, consider we have the terminal, TTY, and bash. So here we have the user. Now the user typically interacts with a terminal. For example, xterm. So xterm is a terminal, and I can open xterm right here. So for example, in this case, this thing that you see here, it is called xterm. So this is a graphical user program, a GUI program that actually allows us to communicate with the shell. So even though, we have to sort of like separate the graphical part of the terminal with the shell itself. Now, why do we have to make this distinction? Because the idea is that there can be many different types of terminal that use the same shell. So consider what is happening here, for example. Here I have open xterm here, but I also have this other shell down here. This is because I have two terminals. This one is xterm, and this one is called instead of wterm, and wterm is handled by Emacs, the programs that I use. So every time you see the terminal like down below, it is called vterm, which is run and handled by Emacs. While, for example, xterm is a different terminal implementation. So the concept of a terminal has to do with the graphical user environment. So right now I'm running x11, which is the server that handles all the graphics and stuff. So the idea is that I have different terminals because the terminal implements the graphics of to interact with the shell. So it's like it is the thing I interact initially. Now continuing, both terminal, so in this case xterm and wterm underlined here, so the one on top white and the one down here, wterm. So both of these terminal are actually running the same shell, which is called bash. So bash is a command line interpreter. So there's this word, interpreter. And the idea is that we give to bash a series of commands through text. Bash understands the text, understands the commands, and executes them on the operating system. So that's the key difference between the terminal and bash. Bash is the interpreter of commands that executes them, and the terminal is just the way we interact with it graphically. Now, between the terminal and bash, there's actually a third component, which is called a TTY, and without going into the details of this thing, you can actually think of the TTY as a sort of like channel where data is exchanged in two directions. So from the terminal to bash, and vice versa from bash to the terminal. So it is like this communication channel that the terminal and shell use to exchange information. And on this regard, I found a cool article that exposes the differences between these components. So you can go and read it. It's here. It's this article. So I just suggest, if you're interested, just read this article. It's really, really useful, essentially. So that's the diagram where I took it. So if you are more experienced and you want to see more details, you can read that. For now, we will stick with the basic and we'll just think, okay, we have the terminal, which is the graphical thing we interact with. Then we have the shell, which is the component that interacts with the actual operating system. So it's the last component. And between the terminal and the shell, we have the TTY, which is this communication channel. Now notice that there are many different types of shell. That is, there are many different types of command line interpreters. For example, another type of command line interpreter is called sh, which is simpler than bash, if I remember well. So like we can do /bin/sh, notice here. Now here in this xterm, here I open sh. So I'm using the same terminal, is still xterm, but now the underlying shell, the final shell, the program that allows me to interact with the operating system, it's no longer bash, but rather it's sh. So this is why I wanted to mention the difference between the shell and the terminal. The shell is the interpreter you use, and for example sh is a shell, you have the bash shell, there is also the fish shell, so there are many different types of shells. And also there is the terminal, which is the graphical program you use to interact with the shell. Typically, if you want to configure your system, you have to choose which shell you use and which terminal you use. When it comes to the TTY, that is more technical, and for beginners, I think it's not really that important. So it's just remember that it's a communication channel that sits in the middle of these two components. Okay, now that we covered this, we can actually kill this terminal because we don't need that. We can just work with this and we can continue, and we can start to talk about basic information. So the idea is that every time we are using a shell, as I said, we have to use programs to extract information out of our system. And this is really the first step, is to extract information, to understand, wait a second, what is happening? What can I do? Who am I? What are the files? What are the resources in this operating system, in this system? So in this chapter, we will talk about extracting basic information. So the first basic information we can extract has to do with the username. Now, this is because modern operating systems have different users. So you will have many users in your system. And this is done to make sure that the programs, the resources are divided between the users. So you have an administrator, you have a normal user, you have a service user. So you have different types of users depending on what you need to do with the system. Just imagine that you have an operating system that is accessed by many different people. So each one of them will have their own user with their own permissions. So if you want this kind of permission-full system where each one has its own permission, you need to have the concept of users, and modern operating systems have that. So the first command you can type is, okay, who am I? This command gives you your current username, so the user you are interacting with the shell. This is because every time you are interacting with a shell, you have a username. So you are given a username and you can extract it with the whoami command. In this case, the whoami tells us SSH user. And notice that we can also see it in the prompt. So this is the prompt is the thing that gets printed for every new line. So every new line, here I start to type, right? But there's something before I start to type. That is the prompt which contains basic information. Now, sometimes the shell do not have a prompt. For example, if I use sh, just notice with sh, with this other kind of shell, I do not have a prompt. So notice that sh is a more primal kind of shell. It's a more primitive kind of shell. If I do exit, I get back to bash, and here I do have a prompt. So this shell has a prompt. So that's the first thing. Another command that you can use to extract information regarding who you are is the id command. Now, the id is a little bit more complex because it actually gives you information about your user ID, UID, which is 999, and this is the username. Then it gives information about the group ID, so this GID, which is 0, it's root, and then it tells you which groups you belong to. So in Linux operating system, root is also the administrator. So the administrator is known as root. So it means that I belong to the group that is owned by root. So to the root group, essentially. So this is the first piece of information. It's who are we? What can we do in this system? Well, the first thing that we need to understand is who we are. In this case, we can use whoami or id. Now, the next command is the hostname command. This tells you the name of your host. So this is the name of the server you are interacting with respect to the network. So this is the name. In this case, notice that this name is the same thing that we see in the prompt. This is because the host name of this Docker is this string of 718878. So a bunch of characters. This is the host name. So this means that in the prompt, what you see is the username extracted with the whoami and the hostname extracted with the hostname command. So getting comfortable with the shell is all about learning what kind of commands give you what kind of information, and to understand in a given context, you are okay, I need this piece of information. What is the right command? So do not try to memorize all commands because that thing will not work. Rather, try to understand what you can do with a shell, what are the resources you can access, how you can access them, and then once you have an action, once you can conceptualize an action, you can say, okay, I need to know what user I am right now. Then you can go and search for the right command. You can maybe write it in a piece of paper, in a note, in a file txt, something like that. And this is how you get comfortable with the shell. Do not go and try to memorize all commands because that doesn't work. It takes months, of course, to learn this kind of stuff. It's not immediate, but the focus is that try to think conceptually on the things you can do with the shell, on the information you can extract and interact with the shell. So the first two basic information is username and hostname. A third basic piece of information is the working directory. So this is extracted with this command, which is called pwd, which stands for print working directory. So if we execute this command, we get this result. So we get this result, which is like /home/ssh user. Now this thing actually is representing a path in a file system. So we have a path. Now a path is like, intuitively, a path is like a street we can go, somewhere we can go, right? Well, a path in the context of a digital file system is essentially the same thing as a physical path, sort of. It tells us where we are in this file system. And you can think of the file system as like a tree of resources. We have a starting point, which is called the root of the file system, and in Linux the starting point is symbolized by this slash, and then starting from the root you have a bunch of different directories or files, and for each directory then you have other resources. So you have this sort of tree of resources, and every time you jump into a node and you go down, you are adding stuff to your path. So for example, in this case, how can we read this /home/ssh user? The idea is that we start from the root, so this is slash, then we go into the home node, and then we go into the ssh user node. So here we are right now. Here, this is our path. So the path is like this series of nodes in the file system. And with the working directory command, we understand the working directory. Now, the idea of a working directory is that every program that executes in the operating system has a series of information, such as the username who started that program, like that program is running as the user Leo or as the user SSH user, stuff like that. And then it has a working directory. So every program has the concept of a working directory, which is sort of like the base place where all the resources can be accessed to within that program. So you can imagine it as a sort of like the point of view of the program within the entire file system. So the working directory, you can get access to the working directory of the shell with the pwd command, which stands for print working directory. This is extremely useful because, for example, while the username and the hostname were pieces of information that we could extract just looking at the prompt here, we could know, okay, this is the username and this is the hostname. When it comes to the working directory, sometimes the prompt does not tell us. We can customize it, we can customize it to make sure that it tells us, but sometimes it doesn't tell us, which means that we could have a different working directory, and so we can ask, like, every time we work. So for example, now I'm going to do an operation, I will explain later, and so for example, I go here, so now I do print working directory, and it says slash. Now I go into tmp, okay, now it actually tells us, so print working directory /tmp. So in this case, when we went into here, it did not tell us explicitly /home/ssh user, because actually here there is this character which is called a tilde. So this is called a tilde, and in Linux operating system, a tilde is sort of like an alias for the home directory of the user. So since I am currently in /home/ssh user, and I am the SSH user, it's sort of like I am in my home. I am in my home folder, so it just prints the tilde. So this is sort of like an alias. So we have username, hostname, working directory. Two other pieces of information are the environment and the which, like the which command, which is extremely useful. Now when it comes to the environment, so we go here to our shell, essentially it's that every time we have a program, we also have so-called environmental variables. So these are like a programming language variables. The difference is that they do not belong to a specific like language, they belong to the program itself. So it's sort of like they are variables that the program can use to interact with other resources, with the operating system and stuff like that. So once again, they are variables that control the program, in this case the shell, but also other programs have environmental variables. Now to get access to the list of environmental variables, you can just write env. Now notice that this kind of environmental variables have the same syntax, so it's like the name of the variable, then there is an equal, and then there is the value of the variable. So in this case we have pwd/home/ssh-user, we have shell, which is bin bash, so like this shell environmental variable points to the program that represents the shell, which in this case is bin bash. This other environmental variable points to the current working directory, which is home ssh-user. This is the log name, this is the home, this have to do with the colors, we will see later. So all of these things are called environmental variables and they have the same syntax. The name of the variable equal the value of the variable. And they can be accessed with, for example, echo, and then I say dollar and I say shell. With this command, I have access to this environmental variable. So without printing them all, I can also print individual environmental variables. So for example, I can add the command echo here, where the command echo is simply used to print stuff. So the command echo prints stuff to the screen. It can be a literal string, like in this case, echo hello. It can be also an environmental variable. And to print out the value of environmental variable, I need to use the dollar sign. So I say dollar name of the variable, because in bash, variables are prefixed by dollars when I need to use them. So when I need to refer to a variable, I say dollar. And here it stamps shell. I can also, for example, print the value of the environmental variable home, which tells me /home/ssh-user, and so on and so forth. Now, the last thing is the following, the which command. And for me, this represents one of the basic information, because every time you use a program, for example, echo, right? The question is, but wait a second, where is this program found within the file system? Now, to actually map programs to file system, you can use the which command. How does it work? You write which and then the name of the program, for example, echo, and it tells you the path within a file system for that particular program. So this is the idea of which. For example, which env, it tells the path of the program that prints the environmental variables of the system. If I say which UMI, it prints the program that prints the current user, which id, it prints the program that maps that prints out the current t, which hostname, you know, every kind of program. Every time you, for example, write hostname, what actually happens is that this specific command, hostname, is actually resolved to its full path before being executed. So there is this translation process where you go from the command to the path of the command, and then you load into memory that binary, the program hostname, which is found in user bin hostname, and then you execute it. Which means that to understand which particular host name to execute, you need the full path, and you can see the full path of a program with the command which. Sometimes we have troubles using command line systems, command lines programs, because we don't even know which program we are actually executing. So in this sense, by using which, you can get an idea, okay, like this is the program that is being executed once I write hostname. Then you can go analyze that program, maybe see if it's well configured or not. So that's the idea. So this covers the basic information we can extract from the shell. To give a quick recap, and of course, by the way, you can find all these commands in my notes.txt. So here you can find all of these commands to play around with them. So the basic idea is that username, who am I, hostname, where am I, working directory, what is the current directory the shell is executing at, environmental variables, what are the variables of my environment, and the which command, which allows me to resolve the various programs. Now, I've already discussed in the PATH Hijacking video, so in the PATH Hijacking video that I've already done here, PATH Hijacking, I've uploaded, it's called PATH Hijacking, I've already discussed how this translation happens. So if you're interested in that, go and check out that video, but essentially, to give a quick recap, a specific environmental variable is used, which is called the path. So thanks to the path, the program which, and in general the shell, is able to resolve the programs to their full names, to their full path in the file system, and then it's able to execute them. So this covers the basic information. Now we can talk about relative and absolute path. Now, every time we have to specify the location of a resource in the operating system, as I said before, we need to specify its path. So the file system is sort of like this world, this map where we have different resources. And now when I want to access a specific resource, I need to say, okay, this is the path of the resource. Go and fetch it, go and use it. Now, having said that, there are actually two different ways of specifying these resources, and they are called respectively absolute path and relative path. So the idea is that the absolute path always starts with the root of the file system. So consider this path. It starts from /, then it goes to home, then to Leo, then to projects, then to foundation, then to YouTube-n, and so on and so forth. So the key idea to understand about absolute path is that they start from the root of the file system, which is the initial location, which is where everything starts off from. So the / is the start, then it goes into many different directories, and then you traverse the entire tree until you get to the actual resource. So this is one way of specifying a location. Another way is to use a relative path. Now, relative paths have a distinction in that they don't start from the /, they don't start from the root, they don't start from the start. Rather, they start from the current working directory. So here we are already trying to link two pieces of information, right? So with this command, with the pwd command, we extract the current working directory. So notice here, so here with pwd we extract the current working directory, and then now I'm saying that relative path actually start off from the current working directory. So the idea essentially is that once you want to resolve a relative path, what you do is you take this path and then at the start in the left here, so like here in the left, you actually put the current working directory. So you have to concatenate these two pieces of information, like so. For example, we have the current working directory and then I put the relative path. So to actually get an entire path, you have to take the relative one, but you have to append it to the current working directory. It's sort of like saying, instead of starting from the root of the tree and then going downwards, you start from a specific node, say for example this one, and then you go either up or down and so on and so forth. Now to specify the fact that you want to go one directory backwards, because the idea is that if you do not start from the start, right? If you start for example from this node, you might want to go backwards. You might want to say, look, I want to go backwards one directory and then forward another directory. So to specify the backward directory, the previous directory, you actually use this syntax, is dot slash. It's the forward slash. So you do // and this actually means go back one directory. If you put, for example, three times this // you are saying go back 3 directories and then move into the third OSCP, into the full directory and into the video directory. So this is the idea between absolute path and relative path, and it is highly connected with the working environment. And so this is a really important piece of information in order to read the path that you will use in the Linux shell. We will use this relative and absolute path. So now we have the file system commands. So as I said, one of the most important aspects of our operating system is the file system, because the file system is actually the place where our data is stored, which means that it is also the place where we can read our data. So every time we have to write a file, every time we have to read a file or create a directory, which is a container of files. So every time we have to interact with a resource in the operating system, we have to use the file system, because it is actually one of the most important things. Every program that exists, we actually write to the file system most of the time, most programs, if we want to use them many times. And then we read from them, we read from the file system, we put into memory, and then we start to execute it. So it's really like a crucial piece to understand well because it's highly used. So how do we extract information from the file system? We start with the pwd command, which prints the working directory, because this is our entry point within the file system. So it tells us the location that we are at in the file system. So very, very simple. Now to actually change, so to move in this file system, we can change directories, because the idea is that, look, I actually want to change. I want to move between directories. So we can change directories, and another critical piece of information is to list out the resources in a particular directory. So for example, I can do cd cd ... and this is like, okay, go back one directory. I go back one directory. Now I am in /home. Before I was in /home /ssh user. Now I am just in /home. Perfect. I can go back another directory. So cd ... Now I am in the / directory, which is the root directory, which is where everything starts out from. So now I want to say, okay, I want to list out all the files in this specific directory, and I go ls. Now ls gives me all the resources in these directories, where typically the resources are either files or directories. You have also different types of special files, but for now we just consider about files and directories. So here they are colored differently. So for example, these blue ones are directories, while this other color is like symlinks, so they are links to other directories, so we don't care about that for now. So like the idea is that, okay, I have all these directories. Now I want to change into a specific directory. What do? I do cd, which stands for change directory, and then I put the name of the directory I want to go to. For example, var. I want to go into the var directory, and I go cd var. And now I am in /var. If I print the current working directory, I'm no longer in /home. Now I'm in /var. I can go list out the directory in /var, and I can see, oh look, there is a backups directory. Let's go there. I do cd backups. I press OK, and now I do print working directory, and now I change directory. So you see, this is how we travel through the file system. Of course, if you are not used to that, it can be confusing, but the idea is that to develop this muscle in your brain to understand, okay, I am in this directory, I need to go into this other directory, I'm going to do a bunch of CDs and ls to move there. And notice that if we go back to the root directory, and we can do that with a cd /, it says, go to the directory / go to the root directory, and we do an ls. Here we have a bunch of different directories. Now these are standard Linux directories, and you will need to understand the roles of each. I mean, you don't need to understand completely the roles of each, but for example, in /home, typically you will find the folders of the current user. So here we have two folders. We have the Ubuntu folder and we have the SSH user folder. So for privilege escalation, this directory is pretty important and you should know it very, very well. So this is the idea. We can go into the SSH user directory. So this is our home because we are the SSH user, and we go into the /home /SSH user, and we can list out the files. So here notice I did ls and there are no files in this directory. However, actually, there are different types of files which are not shown here. And the ls command can be used with different flags. And once again, these flags change the behavior of the program. Now here, I'm not going into the details of the various flags for each program, otherwise this video would be endless. But the idea is that a useful command for ls is ls, then do -a. So with this ls-a, essentially, what I'm doing is that I'm actually printing all the files, even those that starts with a dot. Now, why initially they were not shown is because in Linux, there is this convention which says, look, if a file starts with a dot, do not show it immediately. It's called an hidden file. I mean, this is not really hidden, it's just for convenience. you typically use these files to configure your programs. So these are sort of like technical files you can think of. So the idea is, okay, we don't want the user to see all these technical files, so we want to hide them, and we only want to show them to technical experienced people that understand them, so understand their role. So this is why they're called hidden files, and with ls you can extract them with -a. Another option for ls is -ah. Actually, I think it's -al. It gives you this kind of listing, which is more structured, and it gives you various information. And then if you want to actually get the size of the in bytes of the various files, in terms of kilobytes, megabytes, gigabytes, and stuff like that, you can put the h option. So it's like you have different option. Here I'm just gonna save this as a proper option here, so into this list file because it's useful. And so to interact with the file system, so far we've seen working directory, change directory, and list files. Now of course we have 3 more commands, which is move files, copy files, and remove files. Now these commands are pretty straightforward once you get used to the idea. So suppose that I have 2 files. So now I'm gonna do an echo hello1, and I'm gonna create a file test1.txt. So what I did here essentially, I'm not gonna explain too much about it, but essentially the idea is that now echo typically prints out the content to the terminal, right? So if I just say echo, it just prints out to the terminal. With this particular command, what I said was that, look, you take the output that you were about to print into the terminal and you redirect it into the file test1.txt. So this essentially creates a test1.txt file, and I can look at the content with, for example, cat test1.txt. Now cat initially was not actually developed for viewing files, it was developing for concatenating files. This is why it's called cat, concatenate, but you can also use it to view single files like that. It works okay, let's say. So notice that the content now is not printed on the terminal anymore, it's actually printed within the file. And with this we can create, for example, another file. So here I can create hello2 test2.txt. So now I have 2 files, cat1.txt and cat2.txt. And notice that if I use cat like this, so how am I using this program? I'm saying this is the name of the program and this is the argument of the program. So the argument modifies the way the program behaves. The argument is the name of the file test1.txt. If I put 2 arguments, it's actually gonna concatenate the results. So this is the idea why it's called cat technically. So we have these 2 files. So the idea is that we can move files. Now to move a file, what you do is you take move, you take the path to the file you want to move, and you define the new position of the file. So for example, a move command could be, okay, I want to rename test1 into test3.txt. I want to do just a simple rename. I press OK, and I've renamed it. Now test1 is no longer test1, it's already test3. And so this is like a way of moving files. If I want to change the directory of the file, I can do, okay, test2.txt, I actually now want to put into /tmp. So I want to change the directory. So notice, here I'm putting the path to the file I want to change, and I'm putting the new path, the new directory. I'm not giving it the final name, and the move command is configured that when I do not give the final name, the destination name, it's actually going to keep the same name, it's just going to move its position. So I do this command, I do ls. Now notice here that test2 is gone, but now if I do ls/tmp/ I see a test2. And if I do cat/tmp/test2.txt, I see the content hello2. And if I do cat tmp test2.txt test3.txt, I see the concatenation where the hello2 is actually put first and the hello1 is put second. So this is like a lot of information I understand, but this is the idea. I'm just playing around with the shell. Notice also this, that here I put the full path to test2. This is like an absolute path, while here I'm putting a relative path. I'm not saying where it starts, because remember, it starts from the current working directory, which means that if I do print working directory, the actual path that will be used in the program is like this. So technically it's going to be like this. So this path is going to be resolved into what? Into, I'm going to take the print working directory path, and I'm gonna append it to the start. So this is actually the final program that is executed. This one. Because of course all the relative paths have to be resolved before executing. So I can either write like this or I can write like this, and the relative path is resolved to an absolute path. So this is when it comes to the move commands. Then we can do the same, but instead of moving the file, I'm just creating a copy. So it means that the destination will be created, but the source will not be lost. So that's the idea of the copy command with cp. So the idea is that I say, okay, I want to copy this time test3 into tmp, and I do lstmp. Notice I get test3.txt in lstmp, so I have created a copy there, but now if I do ls on the current directory, I still have it in the current directory. So the idea is that it exists on the current directory and also in the final destination. This was not true when I moved the file, because I say, okay, before moving, I do ls, and I have test2 and test3, right? Perfect. Then I move the file into tmp, and I do ls again to list out the files. Notice that test2 has disappeared because I moved the file. So moving means taking one resource from one place, putting it into another place. Copy, I still maintain the original. So when I copy, I maintain the original. And finally, there is rm, which stands for remove file. So this is the most dangerous commands, of course. So the idea is that suppose I want to remove this file. So I do remove, I do the path to the file. And that's it. I do ls, it's gone. It's no longer here. There are other files, of course, but there's no test3. If I do ls/tmp, of course, notice that in this other folder, the file still exists because I just deleted the test3.txt that was in the current working directory. I did not delete it from the entire operating system. I just deleted from a single location. So these commands are extremely important to get used to it, and I just of course mention them. You have to do a lot of practice, but that's the idea. Like, this is a really key. These are all key commands that you must know about. So having finished the interaction within the file system, for basic interaction of course, these are just basic commands, other sets of commands which are extremely useful are those to interact with the resources of the operating system. So specifically, the file system is just one system, but the operating system has many different devices, has many different resources. Specifically, we have the disk, which is like the hard drive, the HDD, and we can sort of use it in terms of, we can understand how many devices are currently connected to our computer with the fdisk-l command. We can understand okay, but what kind of percentage of our disk did we use and what still is left. So for example, it could say, look, you have 30% of disk space left. So this is one resource, the disk. And then you have the processes. So the different processes is another resource that is handled by the operating system, but also you have the network interfaces. So you have network resources, which is another set of resources that is also handled by the operating system. So here I put the most important commands for all of this stuff. So for example, disk devices. Now here I have an output for the fdisk output. So consider sudo fdisk. So the idea is that this gives you the idea of the various partition in your hard drive. In your hard disk, you have different partition, and this gives you, okay, look, this is the start sector, this is the end sector, and this is the description of the partition, and this is the number of blocks, the size, and stuff like that. So this is technical information. It says that we have 31 gigabytes of disk, and this is not mine, it's just an example I took from the internet because I don't want to show mine. But the idea is that with this command you can extract information about your specific partitions in the hard drive. Then you have the disk usage. So for example, in terms of disk usage, you can either ask two different questions. So you can ask a question about the entire disk usage, so with this df-h. So the idea is that, for example, in this case, we have the various folders with the various file systems that are mounted on, and I've actually used 779. So I have 779 news, and available I have 92. So this is the root directory. Then I have others directories in which I have different sizes. So the idea is that it tells you for the different partitions, okay, these are mounted, this is the usage for in general for the entire system. So this is the df. Another useful commands is the du. The du instead is specific to a given folder. So essentially it says, look, in this folder I'm using 20 kilobytes starting from this folder. So as I said, imagine the file system as like this root of stuff here. So the question is, okay, but starting from one specific node, so like this node, what is the entire size of all this subtree, of all this section? And with the du command, you execute the du starting from a given working directory. So in this case, it's my home folder, right? And you get the entire size divided by folders, essentially. So this is the idea. For example, if I do in slash, I do du. Here, of course, it's extremely huge. I have 258 megabytes. It's actually not that much because it's just a Docker. And here I have divided by all the files with their relative size. So this is for a local viewpoint of the disk. Then we have the processes which are running. So let's say PS. So if I do PS and that's it, here I actually get the processes that are controlled by the current terminal. But if I want to see the system processes, I can actually say ps aux, and here it tells me, okay, look, I have, for example, ssh-d, because it's running an SSH login. And another question that I can ask is, for example, I want to see the hierarchy of the processes. So notice, I have the SSH server, which spawned an SSH session, which is the one I'm using, which spawned a bash interpreter, which spawned a bin bash, and now I'm spawning a PS. So like all these like processes are intertwined, and there is an hierarchy, once again, of processes. We have an hierarchy of file system, we have an hierarchy of processes. When you go inside a machine for like a privilege escalation, you need to understand what are the processes that are running on that machine. Because if you have a vulnerable server, if you have a vulnerable process that maybe you can only see from inside the machine, then you need to go with this PS, with this like command to list out all the processes that are actually running within the machine. So processes are one of the fundamental things you need to know if you want to do privilege escalation, and with these simple commands you can get a view of the processes that are controlled by the terminal, in general a list of system processes, and system processes with a given hierarchy. So this is useful commands. And then of course you have a lot of information for the different processes. For example, notice here it says TTY because for this bash session there is actually allocated a specific TTY. And remember what we said, that a TTY is a communication channel, and this communication channel is another resource that is handled by the operating system. So of course the operating system has all the information about it. Finally, another critical point that has to do with resource management has to do with network interfaces and in general with networking. So the idea is that modern computers have always network connectivity, like pretty much all the time. It is embedded into the kernel, into like the operating system software essentially. So every time we have a bunch of different network interfaces. And specifically when it comes to networking, the first question that we can ask is, what are all the different network interfaces that are available to us? And we can obtain this list with the command IP address. So notice here, currently I have essentially two interfaces. One which is the loopback localhost interface, which has this IP address 127.0.0.1, and another which is the ATH0, which is the interface that Docker uses to communicate with the Docker engine, because currently I'm inside a Docker container and it has to communicate with the Docker engine, because technically I can, for example, ping google.com. So this is sent, actually I don't have the ping command, but technically I do have internet connectivity. Let's see if I have the curl command. I don't have the curl command. If I have the wget, I have wget. For example, I can just get the main page for my website, and actually it says permission denied because I'm in the root. I go into my home folders and I get the index file. So notice here, this is the file of my home directory, which means that I do have internet connectivity. To obtain this internet connectivity, I actually have to use a network interface of the Docker engine. So here I have two different interfaces, and this is critical because once again, when we are doing a privilege escalation, sometimes we might get inside a host and discover that he has access to a specific network interface that was previously blocked, that previously we could not get access to. So enumerating the network interfaces available is fundamental. So this is like this other interface, and this is the 127.0.0.1, the localhost, and this is the internal Docker communication. And we can also write, like we can do it as IP address or IPA. So the IP command allows us to interact with the network stack of our system. And finally, another command that has to do with network is the one to enumerate the open ports. So we can do netstat LTPN, and here we get all the listening TCP ports that are currently running on our system. So it's sort of like we log in into a machine, we do this netstat command, and we get all the services that are running on that machine. And this can be really, really critical. Now, of course, for question of time, I cannot like zoom in into every option available for all of this program. For example, in this case, I say LTP because are the most important, options for specifically, but there are many other options. And when you interact with the program, you can typically say, look, netstat and then --help. So you can typically use the help command, and it lists out all the possibilities, all the options with the various usages. So for example, route or interfaces or groups or statistics. So to actually understand how to work with these programs, you need to sort of like understand how to read this syntax, how to read this documentation, which is really, really critical, because otherwise you might get lost into this like sea of commands. This is like a lot of different commands with a lot of usages. I just suggest to start slowly and slowly get used to like extracting all of these pieces of information. And so a quick recap, when it comes to resource management, we did the disk commands, the processes commands, and the network interfaces commands, so the network-based commands. So at this point we are almost over. We need to see 2 more sections. So this one has to do with users, and the final one has to do with packages. So when it comes to users, of course, as I said, the operating system has support for multiple users connecting and using the operating system at the same time. So we have a bunch of different commands that have to do with the management of those users. So for example, this user add command, which is typically called with the sudo. Now, I will do a specific video on the sudo command, but essentially, to give a quick overview, the sudo command stands for super user do, and it is used when we want to execute an action as the administrator of that particular machine. So typically, we are not always the administrator. That is, we are not always the root user, right? Typically, we have our own user, and this is done for like security sake and stuff like that. But the idea is that when we actually want to execute a privilege action, when we want to execute an action that only the root user can do, such as adding a new user to the system, we can use this program, which is called sudo, that allows us to temporarily execute programs as root, even though we are not root. Like we become root for a specific amount of time for executing a specific commands, maybe with a password, maybe we have to authenticate ourselves with a password, stuff like that. So this first thing is like user add -m and then you put a username. So this is to create a new user. So for example, I am in my Docker here. Actually, I'm gonna put it here. I am in my Docker. I can do sudo user add /m leo. So I go into /home now, and notice I have also the leo user. So this is the first command. Now internally, how are user handled by the operating system? So there are 2 files of interest, which is the /etc/passwd file. So we go into the cat /etc/passwd. We cut out this file. Now this file contains a description like metadata for every user in our system. And specifically, there is the username, there is the password, the user ID, the home folder, and the shell to use for that particular user. Now here I said there is the password, but actually the password is no longer put into the passwd file. And if you notice here, we just see a bunch of X's. So there is no password here. The passwords for the virus user is actually stored in a different file called the shadow. So it is etc shadow. So the shadow files contains the passwords. So for example, in this case, here you can see the actual password, which is hashed. So this password is actually hashed, but you can find it there essentially. So you can do cat etc shadow. Of course, if I just do cat etc shadow, it's gonna say, look, permission denied, because you cannot see that clearly. But if I do sudo, I'm actually running a super user, so I'm actually able to actually see that password. So that's the idea. So this is to create a user. Now, if you want to change the password of a user, you can do sudo passwd. So I'm gonna do sudo passwd leo. I'm gonna put a password, I'm gonna put test. Now notice that when I did the cat etc shadow here to leo, it actually printed this exclamation mark. It did not actually print the hash of a password. This is because that particular user actually did not have yet set a password. So now if I see it again, if I do again sudo cat etc shadow, notice that now I see the hash of the leo password. So it has been set, and I can do su, which stands for like change user in a way, and then do leo. Here it asks me for the password. Here I can say test. So I type it wrong. I have to type it again. So test. And notice now that I am who am I? I am Leo. So who am I? I'm Leo. ID. I am Leo with the UID of 1001, with the GID of 1001, and stuff like that. I do exit. I go back to the previous shell. So notice that I can start one shell and then another shell and then another shell. And so my interaction with the computer changes. So going fast, this is how we create a user, this is how we change user password, this is how we delete a user. So sudo user del. So we do sudo user del, and then we can do -r to say delete also the home directory. So we say leo, and then we say ls, and now we do not see anymore the home directory of leo because we've removed it. And also if we cut the file tcpasswd, there is no leo here anymore. So here in this passwd, there is no leo anymore. So this is how we delete a user. This is how we list the groups of a given user. So we have the id and my to get my information. But then if I want to list out the groups, I can either say groups. So this is my groups. And if I want to list out the groups of a specific user, for example, of the root user, I can say groups and the username, and it's gonna give me the user of that user, the groups of that user. So because essentially groups are containers of users. So in a group you can have more users. For example, here I am in the sudo group and in the root group. So I can say groups, for example, let's say sudo. Actually, there's no such user, clearly. So let's say groups backup. The backup is in the backup group. www-data is in the www-data group. So not too much interesting, let's say. Then we can add a new group, and we can add a user to a group. So the group add is just say group add. You put the name of the group, and you have created a new group. While if you want to add the user to an existing group, you just say usermod -a-g. You put the name of the group, and then you put the username. So this, when it comes to user management, these are the most important commands. Once again, these are like the basic, I understand, but this is how you get started, by mastering these basic commands. If you master these basic commands, you at least know how to manage your system, and then you can go and explore more complex stuff. And then we go into the final section of package management. So this is the final section because essentially many times the programs that I mentioned before, like for example fdisk, right? Here I say, look, fdisk-l to get the information about the disk. Now, many times it can actually happen that you do not have that program installed in your system. That is, your system does not contain that binary, so you need to get it somehow. Now, the cool thing about Linux is that in Linux there are so-called package managers, which are programs that help you to obtain, to download, to compile, and to install other programs. So essentially, this is the idea of a package manager. So in this case, we are running Ubuntu. So we are running Ubuntu, and we can get this information by saying lsb_release -a, and here I get Ubuntu 24.04 LTS, so the long time support version. So this is like a useful command also if you're running Ubuntu, if you're running this kind of distribution. So many times we do not have the specific command. So how do we do then? We use a package manager. Now in Ubuntu there are two different types of package manager which are actually sort of like similar, and it's called apt and apt-get. So the idea is that apt is a simpler interface over apt-get. So we can say apt-help, essentially. It provides the same functionality as the specialized apt tools like apt-get and apt-cache, but enables options more suitable for interactive use by default. So this is the apt, and then you have the apt-get, which we can also use with the help, is a command line interface for retrieval of packages and information about them from authenticated sources, and for installation, upgrade, and removal of packages together with their dependencies. Now, the problem of managing dependencies is actually quite difficult. So here we talk about dependencies. So the idea is that every program can depend on other programs. So you create this network of programs and of like dependencies, this network of constraints, so that maybe you want to upgrade one program, right? But this other program does not want to get upgraded, and sort of like you break this kind of constraints, and so everything falls short. So these programs are like complex because they have to manage this kind of dependencies. However, as the final user, especially if you're a beginner, you don't really need to think about that. The idea is that you have a program to obtain other programs. And in this case, the program is called apt. So for example, you can say apt-get install fdisk, and it's going to install this program, fdisk. So I do this. Of course, it says permission denied, right? So I need to say sudo. And here it says okay, and then it installed it. And so like I can either do apt-get install or apt install with the sudo actually. Then I can search, because of course the problem is that how do I understand that the name of the package is actually called fdisk and not in any other way? This is actually tough. You can use search engines for this. They can help you, hopefully. So the idea is that all the commands that we've seen so far, these basic commands, are essentially the same over all distributions. However, when it comes to packages and how we manage them, this is highly dependent on your distribution. For example, for work, I use Ubuntu, while for my personal usage, I use Arch Linux, and they have two different ways of managing the packages. But all of the ways essentially allows you to install new packages, to search a database of information regarding packages, to remove a package when you don't want it anymore, to update and to upgrade. So there is a key distinction between updating and upgrading, because the idea is that to work, these packages, they have to download metadata into a local repository. So it's sort of like this is your PC. So this is your PC, and this is like a local repository of metadata. When you do update, you're actually not really like installing new version of the software. What is happening instead is that your PC communicates with the remote repo to sync up with the latest metadata. So it syncs up, it sort of says like, okay, of these packages, I have the latest version of these packages, new version have been released. So when you do an update, it's just like the exchanging of metadata. Then when you do the upgrade, actually you are downloading the new packages, you are installing them, and you are replacing the old packages with the new packages. So this is the key difference between updating and upgrading. Typically, of course, upgrading takes more time, and you need to like update frequently to get the latest metadata. And then, as I said, you can search. For example, let's do this. So when you do search, it actually searches the local database for all the packages that contain that keyword. So in this case, it was disk. So look at this, small printer daemon intended for diskless workstation. So you get a description for the various programs. Here you have a bunch of libraries. So these are used when you want to develop something or you want to use a program that needs this particular library. So this is like, can be helpful. And so like you have a lot of different programs, and in this mess there's also the fdisk, which is this one, collection of partitioning utilities, fdisk, noble, and the version. And it also says, look, this is actually installed. Pretty good. So this is how we search. To remove, we can actually do the purge command. So look at this, I go here, I say purge, with sudo of course. So here I just purge everything, I just delete everything, and now I do not have anymore the fdisk command. I do not have it anymore because I've deleted it. And finally, I can do the update to fetch the latest metadata. So here, I'm gonna get the latest metadata. Actually, I have to always do the sudo. So here it's downloading all the latest metadata, and I can do upgrade to actually swap the packets with the newest packets. So once again, I have to do sudo because I have to authenticate as administrator. So it says, for example, look, the following packages will be upgraded. So there are new versions for those packages. I say yes, download the new versions, and now I've downloaded the new versions. So essentially, this covers it, all the basic commands to get started with the Linux shell. To finish off the video, I will do a quick recap of what we treated so far. So we discussed the difference between the terminal, which is a graphical entity which lives in the GUI, the TTY, which is a communication channel, and the shell itself, which in this case is bash, but we also have another shell called sh. There's also fish, and so on and so forth. ZSH is even another shell. So it's ZSH is another shell. So we have different types of shell, different types of terminal, and typically the TTY is specific to the operating system, so that is kind of the same. Then we saw the commands to extract the basic information, because the idea is that when I use a command line, when I use a shell, I need to extract, I need to understand the basic commands that I need to extract the basic information. These basic information are: who am I? What is my user? What is the name I'm currently running on, the host name? What is the current working directory within the file system? And what are the environmental variables? And how can I print the single environmental variable with this syntax? Then the which command is useful when we want to extract the path that is actually like used to execute a program. Then we discuss about the difference between relative and absolute path. So there are two different ways of resolving path in the operating system, of specifying resources in the operating system. Then we talk about the basic file system commands. So to print the working directory, to change the directory, to list the files in the working directory, to move, copy, and remove the files. So this is like the basic interaction we have with the file system. This is really, really important. Then we have the resource management, which is divided into the disk, the processes, and the network interfaces and the network ports. Here I've shown an example with TCP. You can also enumerate the UDP ports. I mean, that goes like into detail, but this is the main idea. Then we have the commands to deal with the users. So remember that we have two specific and important files in Linux that manage the users, which is called the etc passwd, which contains all the username and the information about the shell being used by that user, and the shadow file in /etc/shadow, which actually contains the hash, the hash of the password of the user. So this is really important to manage the users. And finally, we discuss about package management. So the idea is that we use programs such as apt or apt-get to install, search, remove, update, and upgrade our system by interacting with a remote online repository that is contained by different programs. So we can download those programs, we can install those programs, and this is like done easily through this interface with apt. And all these commands with apt, they require the usage of sudo, because we actually have to be super users. Now, in this video, I mentioned a lot of things. I couldn't go into the details because it's really like a crazy amount of stuff to cover, but I hope that this introduction gave you some idea with respect to the Linux shell, how to orient yourself within the Linux shell. And as a final resource, I highly suggest playing with this website, which is called overthewire.org/wargames because it contains a bunch of challenges essentially that you can use. So this is the site and you can play with Bandit. So Bandit is the first. Now it contains many different levels. There are around like 30 levels that allow you to play with the shell, with the various stuff that you can do with the shell and stuff like that. So to actually get used to the Linux shell, you kinda need to do a lot of practice, and this overthewire.org contains a lot of levels that are really fun and useful to do when we are starting out learning the shell. So this is extremely useful and I highly suggest this other than the usual Hack the Box, Try Hack Me, OSCP Labs and stuff like that. So I hope the video was enjoyable. If you have any feedback, please leave it in the comments and see you to the next video. Hi everyone and welcome to this new video. In this video I continue my Linux privilege escalation series, and specifically in this episode we will talk about Linux file system permissions. So the idea is to analyze all the things related to the permissions in the Linux file system. This means that we will understand how permissions are structured, how we can read and understand the permissions on a given file or directory, and now we can update the permissions on a given file or directory. And finally, we will talk about two specific systems which allows us to interact with permissions in special ways, and these are the SUID and GUID bits that can be set on an executable, and the SUDO subsystem, which allows us to execute commands as other users. So that's the idea. I hope the video is enjoyable. If you have some feedback, please leave it in the comments, subscribe to the channel and share this video with like-minded people. So we can go on and enjoy the video. So the first thing I want to mention is that in my first video of the Linux privilege escalation, I showcase a lot of different commands. So here we see the org file for that video and all the commands that I showed, for example, the basic commands like username, hostname, working directory, and so on and so forth. Then we showed some file system commands, then some resource management commands, for example, disk usage, processes, network interfaces, open ports, and so on and so forth. So a lot of different commands I showcase. Now, to understand how all of those commands worked, there is a system called the man pages, which essentially is a documentation that tells you exactly how those commands work, what kind of options they take, what kind of arguments they take, and stuff like that. So to access all this information, you have two ways essentially. Either you download the man command. So using your package manager, depending on your distribution, you can download this command, which is called man, and it is a shorthand for manual page. And when you have this man, you sort of like can access locally the documentation. So for example, if you do man ls, it's gonna give you the documentation for the ls command. And we can do it here in this other here. So I can do man ls here. I do man ls, I execute it. And here I have the documentation for the ls command. And notice that this kind of documentation has the same format, so let's redo it. So we have the name of the command, so the short name and a long description, list directory contents. Then we sort of have like a description on how we can use it. And so this is the synopsis. The idea is, okay, you use ls by giving a bunch of options and then a bunch of files. These three dots mean that you can have more options and more files. And the description tells you exactly what it does. List information about the files, the current directory by default, sort entries alphabetically if none, or, and here it tells you essentially how the various options modify the behavior. Now, reading these pages is not too trivial. You're gonna get used to it, to the specific syntax that information are displayed. But the important thing is that with enough practice, you will be able to understand how to read it, which means that if you then forget how to do a specific action using, for example, the ls command, then you can quickly search through the page to understand what was the specific flag. So for example, if you do the -a, it says, do not ignore entries starting with dot, which means that typically by default it ignores the entries that start with dot, and if you want to include them, if you don't want to ignore them, you have to do -a. And you know, by going forward, you see all the different options, so there's like a lot of stuff here. And this is for the ls command, of course, and then I think that at the end, like towards the end, You also see like the author, some other information. Sometimes there are even examples, not all the time, however. And so that's essentially the idea. So I wanted to talk about this because in the previous episode I showcased a lot of commands, and to access the documentation for all those commands, the man pages are extremely useful. So you can say, for example, man ps, and it says report a snapshot of the current processes, or you can do man df, and it says report file system space usage, and it's the same thing, it's the same idea. You just go read the main page, you see all the different flags, you do some trying, of course, because it's a lot of practice too. So that's the idea. If you don't want to download these main pages, you can just go online. Here there are online main pages, so here I put a link. So the idea is, how do you use these main pages? You can either search by individual sections, so like you have 8 pages and each page is filled with different commands. So like different pages have different like commands, and sometimes you have the same name for the command but present in different pages, because maybe the page 1 contains certain information and the page 3 contains other information. So you might find essentially the same name in different pages, and they describe different commands with different documentation. So you can either do this, or it's much faster, you just put here in this form the command. For example, ls, and here it's gonna do a Google search that filters only the results from the website, man7.org. So here you get the first result, ls, and then you can get essentially the same thing you get from the man command locally, but this time it's through the web, so you don't need to install the man command. And so this covers this first introductory. I wanted to mention it because in the previous video I did not introduce the man pages, but they are really fundamental part to understand Linux. And when you're doing a box, for example in OSCP, and you find a command that you never used, the first step of course is to just read the main page, understand what the command does, and try to find maybe the specific option, the specific flag, or the specific arguments that allows you to do the privilege escalation. And so now we can actually get to the content of the video, which will be about file system permissions. So when we use ls with the option lha, so essentially with the option L, we're gonna get a lot of different information about our files. And specifically here we have this first set of information which has to do with permissions. So technically what happens is that we have this set of information that has to do with permissions, and also this other one and this other one. So we have three things which have to do with permissions. And how we read them is that this is the set of permissions associated to the resource. So the resource most likely is either a file or a directory. This is not everything in Linux. You also have device drivers and special kinds of files, but you can imagine that any sort of resource is either a file or a directory, where a directory is a sort of special type of file that contains other files. So that's the general idea. So like in the first section here, you have the set of permissions associated with that resource. Then here you have the so-called owner of that resource, which is the user in the operating system that owns that resource. And then you have the group owner of that resource. So this is like the group owner, which is the same thing as the owner, but this time it's not a user of the operating system, but rather it is a group of the operating system. Because in Linux we have the concept of users and the concept of groups, and the groups are essentially containers of users, so a group is made up of different users, and this means that a given resource can be owned by one user and by one group. So for example, consider this line, this exec.sh line. So here we have typically the sh extension is used to contain commands that will then go to a shell. So in the previous episode we discussed the role of the shell, and we said that the shell is a so-called interpreter of commands. So like we give to the interpreter commands encoded through text. The interpreter reads the commands, understands them, and executes them on the operating system. And these commands can do anything. They can modify the file system, they can modify the processes, they can start a new process, they can create a new file, they can check network interfaces, they can create a new network interfaces, so that the commands essentially have full control over the operating system resources, and they can just use them and manage them. So this is like a typical extension. Now, in the case of this exec.sh file, essentially what we have is that the owner of the file is the Leo user, which is my user. The group owner of the file is the users group. So this file is owned by the users group. And then we have this set of permission. We have dash rwx r-x r-x. So this is like the idea essentially. Now for each file we have the following information regarding permissions. So we have the file permissions, we have the user that owns the file, and we have the group that owns the file. So in this case, for example, we have this, which is found essentially here in this exec.sh. Now, as you can see, within each string of the form of this particular form, we find 11 letters. So there are always 11 letters. Actually, I think they are 10. So let's say they are 3, 6, 9, 10. So there are 10. So there are 10 different letters, and now the objective when understanding Linux file system permissions is to understand the meaning of each letter. Like, what does it mean when here there is an X, and notice that down here there is not. So down here there is a dash, but up here there is an X. What does it mean when there is this difference in the file system permission strings? So the idea is that permissions are encoded in this single string, and then we have a user and a group owner. So that's the idea. Now we find 10 letters, which can be either set or not set. So that's the idea. The first thing to understand is that each permission can either be set or not set. And when it is not set, so when it is not defined, there is a dash. So the dash stands for like the bit 0, stands for like we don't need that permission is not activated on that particular resource. So if you see something with all of dashes, it means that no permission is activated. For example, in this case, we have a bunch of different permissions that are not activated. In the uppercase, it's less. So that's the idea. So the first letter, so once we said that the dash is for not setting the permission essentially, then the first letter specifies the type of the file. So for example, when we have regular files, we just have a dash as the first letter. Instead, when we have directories, we're gonna have a D. When we have links, which are special files in Linux which point to other files, so it's sort of like I have a file here, but this file 1 actually points to another file, a file 2. Now this is called a symlink. This is called a symlink. And so in this case, for this file, the first letter would be the L letter because it is a symlink. So for example, let's consider the assets that form this lecture, like the notes and stuff like that of this lecture. So I do ls in the current working directory, which is this one. So it's like home Leo projects foundation, then we have the YouTube, then we have Linux Privesk, we have 02 and so on and so forth. So this is the current directory. Inside this directory, I just have a single nodes.org file, and I can check the permissions of this file with the option ls lh. So with -l, essentially I get this listing, and with the h, I transform the number of bytes into a more readable format. So it says that I have 11 kilobytes of information. Now, with respect to the permissions, we know that this file is owned by Leo, by the user Leo, and belongs to the group users. So this is the first 2 pieces of information. Then we find this string of specific permission, and it says that the first one is a dash, which means that this is a regular file. Now, if you go back one directory with cd ... so we go back one directory. Now, if you do the same ls-lh command, we have 3 different directories this time. We have content, we have thumbnail, and we have video. And they all start with the D letter because they are all different directories. So content, thumbnail, and video. So that's the idea. If you see D here for the first thing, it's a directory. Otherwise, it's a regular file. And of course, the idea is that we can go inside a directory while we cannot go inside a file. We can just read the contents of the file. We cannot traverse it with the normal file system operation. So that's the first letter. It specifies the type of the file. Then what we find is we find 3 groups of 3 letters each. which means that, for example, this thing actually, how do you expand it? You expand it as follows. You have the first letter, which specifies the type of the file. Then you have a block of 3, another block of 3, and another block of 3. And notice that they kind of repeat themselves because they're like R, the first one is always R, the second one is always W, and the third one is almost always X. In this time at the end is T, we will talk about that later, but essentially look down, for example, so we expand this down, so we have D, which is like the type of the file, then the first set of permission, the second set of permission, and the third set of permission. So they expand into 3 groups of 3 letters each. Now, the first group specifies the permissions for the user who is also the owner of the file, which means that out of all these 3 different groups, essentially each group specifies a set of permissions. However, the difference between one group and another group is that, for example, the first group is specifying the permission of the file with respect to the owner of the file. It means that the owner of the file has this set of permission. However, if I am not the owner of the file, I do not have exactly this set of permission. So that's the idea. The second group specifies the permissions for the users that belong to the same group as the group that owns the file. And the third set of permission is for every other user. So it's like the first group specifies the permissions for the user who is the owner of the file. The second group specifies the permissions for the user who belongs to the group that owns the file. Finally, the third group specifies the permissions for all other users. So here it's users. That is, for users who do not belong in the group that owns the file and are not the owner of the file themselves. So the idea is that to read this kind of permission, we have to say, for the owner, we have to consider the first set, the first group. For the group, we have to consider the second group of permissions. It means that if our user belongs to the group users, then we have to consider this set of permissions. Finally, if we have a user who is not the owner and also does not belong to the group that owns the file, then we consider this other third set of permissions. If we imagine software like sets, the idea is that the most close set is just the user who owns the file. So the first permissions are the most like the one that only apply to the user that owns the file. The second is a little bit more big in terms of applicability because it's for every user that is on the same group of the group that owns the file, while the third one is for everyone else. So no matter who you are, the third group will always apply to you. So that's the way to read it. So now each group works in the same way. And the idea is that we have 3 different permissions. We have read permission, we have a write permission, and we have execute permission. And they are signified, they are represented with 3 letters. R for read, W for write, and X for execute. Now there are minor variants in this, so like sometimes, especially with the execute bit, sometimes it's not written as X, sometimes it's written as S, other time it's written as T, so the execute bit is not always straightforward. Sometimes it can be different from X, but when it comes to the read and write, they are always read and write. So that's pretty simple to remember once you understand it. So for example, in this case, we have this exec.sh, but here in the owner set of permission in the first 3, the execute bit is not X, but rather is S. This is because there is this mechanism called the SUID bit, which we'll discuss later on, which modifies how the program behaves with respect to permissions, but it's a special case. So here also in the group there is S. So for now, just consider that every group of permission has read, write, execute. So going back, what does it mean? It means that, for example, consider like we have this entry. So I'm gonna open a new buffer here. I'm gonna put it in org mode. I'm gonna go here and I'm gonna go, okay, suppose that we have this entry, example entry. So we have the file name, which is exec. So like we know that the user who owns exec is Leo. The group who owns exec.sh is users. Here Leo is lowercase. Then we have essentially for the Leo user the following permissions apply. So what do we have? We have read, write, execute, right? So we have read is set, write is set, execute is set. It means that the Leo user can read this file, can write to this file, and can execute this file. So this is really important. Then for the group users, the following permission apply. So what do we have here? We have like, can we read the file for the group? Yes, because notice that the second section of permissions, we have read and we have execute. We do not have write. It means that the group can only read and execute it, but it cannot write to it. Which means that, for example, if we are a user who is not Leo, let's say like another user, like the user X, so we are not Leo, but we belong to the users group, it means that for our user, the permissions that apply to this file are the second group, this r-x, which means we can read it, so we can read its contents, we can execute it, but we cannot write to it, which means that we cannot modify it. We just can read it and execute it. So this is for the group users, and then for every other users, the following permission apply. So once again, if we are any other users, now we have to consider the third set of permissions, which is once again just read and execute. So that's how you should read this kind of permissions in Linux. This is like essentially the core idea. You go to the name of the file, you check who is the owner and who is the group that owns the file. Then you go look into the permission and you say, okay, what kind of file is this? This is, for example, a regular file. And then finally you take out the 3 sets of 3 permission each and you say, okay, the owner can read, write and execute it. The group can just read and execute it. Everyone else can just read and execute it. So this is what typically happens with critical scripts, which you want your systems to execute. You want them to read the contents. However, you do not want them to modify the script because maybe it's like critical and you just don't want to do that, but you want to allow them to execute it if it's needed, but you don't want them to modify it. So like this is how you read this kind of permissions. Now that we have covered the basic concepts, we can do some practice into reading file system permissions. So to read the permissions, we can use the ls command. So we can do ls with -lha. So A is to show the hidden files. H is to make sure that the file contents are printed in a readable way. So with, for example, kilobytes, megabytes, gigabytes, and so on and so forth. L is to show all the information regarding permissions. So we can analyze such output line by line as follows. The first line is referring to the current directory. So this is the dot. Dot means current directory. It is saying that it is a directory because the first letter is D. It is owned by Leo, which means that the first group of permissions apply to the user Leo, and particularly they're telling us that Leo can read R, because here there's an R, can write to it and can execute to it. So he has full permissions over the file. He can do anything he wants over this current directory because it is owned by Leo. Now, this directory belongs to the group users, so the users instead can read and execute the directory but cannot write the directory, which means that they cannot write new files into the directory. So that's the idea, while every other user can read and execute but cannot write. So it means that this directory is owned by Leo and only Leo can write new files, while everyone else can just read the contents of the file already existing in general. So that's the idea. Now the second line is saying that it applies to the previous directory, not the current, but the previous. So remember, in the previous video we introduced the idea that the file system is a tree of resources starting from the root, which is represented with the slash, and then we have different directories or files. Then if we have, for example, a file.txt, that's it, this is like the last node of the tree, while if we have a directory, we have other nodes, because we go down, we go deeper into the structure of the file system. So for example, in home, we have the directory for Leo, and then we have other files here. So this is the current directory in this case, it will be this node, so it will be this node, while the previous directory, it will be the home folder. So this is why the previous directory is actually owned by root, because Leo just has access to his own home directory, not to the home directory itself. The home directory itself is owned by root, which is the administrator account in Linux systems. And it is saying essentially that the user root can read, write, and execute on this directory, and essentially also all other users. Why? Because here we have all permissions for all users, so they can both read, write, execute, and read, write, execute. So everything can write into the home directory. So that's the idea. Then, for example, just jump into the last line. The last line is referring to the resource test.txt. It is saying that it is a regular file. Notice here, the dash is a regular file. It is owned by Leo, it is owned by the group users, and Leo can read and write its contents, while everyone else, so users belonging to the users group or any other user in general, they can just read their contents. Like they can just read the contents of the test.txt file, but they cannot modify it. So this is sort of like saying Leo, the owner, can modify it, everyone else can just read it. And essentially it's the same for the exec.sh. However, for the exec, the difference is that the users that are not owner of the file can also execute the file. It doesn't happen with test.txt because test.txt is not really an executable. You just read it, you don't need to execute it, which means that you don't need this permission to execute it. While with exec.sh, given that it's like a shell script, is a command, it's like it encodes commands that are executed by the shell, you probably want to execute it, because the idea of a shell script at the end of the day is to execute it, is to do some task automatically. So essentially, that's how we read this kind of contents. You just have to do practice day by day to understand the permissions. If you check a problem with permissions, it probably means either you do not have that specific permission, or maybe you are not the owner of the file. So for example, if you're trying to update a file, you always need to understand, wait, do I have the write permission? Do I have the W permission? And if you see something like this, something like test.txt, you try to write to it, but you're not the owner, then you will encounter a permission problem, because only the owner can write to the file. So essentially that's the idea. Now there are some special cases that you need to consider. Here I just mentioned 2. You have other special cases, but the point of this video is to introduce the file system permissions, not to expand all of its details, because once again the idea is once you understand the basics, the fundamentals, then you can look into the documentation, you can look into the mem pages to understand all the subsequent details. So for example, here I mentioned 2 special cases. Sometimes it can happen that for the last position of the value, you will see t instead of x. So typically the last one is this xxxx, but sometimes you see t. This is called the sticky bit, and essentially it implies that the users in the group who technically have the permission to delete a file cannot do it as long as the sticky bit is set. So it's sort of like it modifies the way that the permission works. So consider this, you have a t, you have a sticky bit here, t, so it means that it applies to the previous directory. So that's the idea of the sticky bit. You don't need to understand it completely, it's just saying that there are special cases in which you will not see x, but you will see a t. Another special case, which is actually much more important than the sticky bit, is this. Sometimes instead of x, you will see the value of s. Now this instead has to do with the SUID and GUID permissions, which will be discussed later in this section, SUID and GUID. So this is it for when it comes to reading file system permission. Now we can talk about, okay, how can we set our specific permissions? How we can update the permissions of a file? So here the idea is to use the chmod command, which is for change mod, sort of like change permission, chmod. So you can search the main pages for chmod. Here I will showcase simple examples. So let's assume that you start with the following file. So you have an exec.sh, everyone can read it, but only the user can write it. So this is a regular file. The owner of the file can both read and write it, he cannot execute it, and everyone else can just read it. So the group users can just read it, and every other user can just read it. Now, suppose that we want to add the execute permission for all types of users. So for all groups of permissions, which means for the owner, for the group, and for everyone else. How would we do that? Well, we do chmod, then we do plus x because we are adding this permission, and then we put in the name of the file. So in this case, it should actually be exec.sh. So once we do that, and after that we do an ls, notice what happens. Here we modify the permissions as follows. So before we just had read write, now we have read, write, and execute. Before we just read, now we have read and execute. Once again, before we just read, now we have read and execute. So to add a permission, we do plus x with the name of the file. So for example, let's say I create a new file, test.sh, I do ls, and here test.sh does not have the execute bit. To add it, I do chmod plus x test.sh, I do ls again, and notice that now it has the execute bit, and also ls by default actually colors this in green. This is because, this is like a little note for those curious, why does it color in green? Because actually ls by default is called with a special argument, because there is a so-called alias in ls, and when we actually execute ls, we are executing ls color equal auto. So we are actually doing this, and when we do this, it uses like specific environmental variables which govern how different files should be colored in the shell. So if you remove this, I think it's like never. If we remove this, if you say color never, notice that we do not get this color grading. We do not get colors anymore. However, if you do color auto, we get back again. And we can also do just with ls, so ls like this, because there is a concept in bash called the alias. We can do alias ls, which means every time you execute ls, what you're actually executing is ls -- equal color auto, -- color equal auto. So that's the idea essentially. So continuing, that's how we can set the permissions. So this is like adding a permission, right? Now, how can we remove read and execute permissions for other users? So this is the third group. The third group, which means users that are not the owner and do not belong to the group that owns the file. So in this case, we have to do a minus. We say -xr to say, I want to remove the execute and the read permission, but before this minus, we have to put O, which stands for others. And this others here, it means not the owner of the file and not the group that owns the file. So like this chmod command, the structure of this chmod command is, here we specify the sort of like group we are targeting, and if we do not specify the group, like in this case, it will apply to all three groups. And then after we specify the groups, we have to say plus to add a permission, minus to remove a permission, and then we write all the letters that represents those permissions. So this is like add to all group the execute bit. This is like remove from the others group the execute and read bit. And for example, here we say add write permission for group that owns the file. Why? Because we use the G keyword. So like while O was for others, so O others, G is for group, which is the second section of permissions. Because remember, the first section is for the user that owns the file, and this in chmod is represented by the U. The second is for the group, and the third is for the others. So that's the idea, that's the structure of Linux permissions essentially. Now, suppose you have a directory and you want to make a change across all the files in the directory, right? Because a directory essentially is a container of different files and directories, so it has a recursive structure. Now suppose you want to make a change into all the subtree, into all the structure that is represented by the directory starting from the directory, then you can use the recursive option -r, capital R. So in this case it would be, okay, you're gonna remove all permissions from the others section, all read, write, and execute across all the directory, because it is recursive. So essentially this is the idea. So for example, so let's do other examples here. So we have this file, so we have content, we have this test.sh. So let's say that I want to remove those permissions from the others group. So I say chmod, I specify the group I'm interested in, which is the other, which is the third section of permission, and then I say, look, remove, read, and execute. Then I do ls again, and notice that it's gone. The read and execute is gone. Say now that I want to add all permissions for the group, and I want to remove all permission for the user. So I can say chmod user minus rwx group plus rwx test.sh. So I do this. So I think I have to do one at a time actually. So first I do the user, and then I do the group, then I do the group, and then I do ls again, and notice now the owner of the file cannot actually do anything on the file. The users belonging to the group users, so the group of the file can read, write, and execute, and the others can do nothing, because first I remove all the permissions from the owner of the file, which is represented with the keyword u, and then I add all permission to the group that owns the file, which is represented by the keyword g. So the chmod is really simple. You just have to select the group you want to operate on, which can be either U for the owner, G for the group, or O for the others. Then you put plus or minus, plus if you want to add permissions, minus if you want to remove permissions, and then you put the series of symbols which represent those permissions taken from RWX. R for read, W for write, X for execute. So that's the general idea. Now continuing, there's actually another way of dealing with permissions. Sometimes we can use numbers essentially. So we have why, because since permissions are like bit mask, are like sequences of bits, so we have that the no permission belongs to the sequence 000. The execute permission like this belongs to the sequence 001. The write like this belongs to the sequence 010. So we have a mapping between the set of permissions we want and sequences of bits, and then we can map those sequences of bits with numbers. So that's the idea. So this is essentially the idea, is that given that with 3 bits we can represent the numbers from 0 to 7, this means that each number can represent a specific set of permissions. So it's essentially said, instead of using the identifiers UGOA with RWX, it is also possible to set permissions using a sequence of 3 numbers. This is because read and write and execute permissions can be represented using 3 bits, and we can also represent the numbers from 0 to 7. Specifically, we have the following association between bits, permissions, and numbers. So this table is really useful to keep in mind. Full permission 111, which is 7. Read write dash 110, which is 6, and so on and so forth for all the 8 examples. So for example, A5 is actually representing read and execute. This means, for example, that 5 represents the read and execute permission bits, while the 7 represents the entire read, write, and execute bits. Remember that we have 3 groups of users. This means that to fully specify the basic permission for a file, we will need 3 numbers, each going from 0 to 7. So for example, what does it mean? So let's go back to our Scratch buffer. We have another example here. So we have another example here. So we have example 1, and then we have example 2. So we have example 1 and example 2. Now, in terms of example 2, we start with this, let's start here. We start with this. So what chmod 764, what does it do? Well, we have to use our table like this. So our, essentially this translation table, which is really useful. So we keep this in mind. And then we say, so let's just transport it like this. Okay, and then we say essentially, okay, so 7 stands for, 7 stands for this, 6 stands for this, and 4 stands for read dash dash dash, which means essentially that this is gonna give the permission to the file okay, the owner is gonna have read, write, execute. The group is gonna have just read and write, not execute, and everyone else is just gonna have read. And so this means that this is the permission mask that we want to see on the file after executing this command. So what do we get in our notes? We can say, look at this, we get read, write, execute. So read, write, execute, then we have read, write, and then we have just read. So for example, let's do in practice in a real working shell. So we have this test sh, so we have this test sh, so we do chmod like this with testo, and then notice here what happens. We have exactly this mask. We have read, write, execute for the owner, read, write, execute for the owner. We also find it here. Then we have read, write for the group, read, write for the group, and we have write for everyone else. And we obtain this set of permission with the numbers 764. Why is that? Because each number in this is representing 3 bits, So 3 bits, because we have numbers from 0 to 7, and each 3 bits is representing a set of permission between R, read, write, and execute. So with this table, just keep this table in mind. You're gonna find it in the notes for this episode. Just keep this table in mind, and by going from the number to the permissions, you'll be able to understand the effect of that particular chmod command. So for example, another thing is that if we want to set read write for the user, read for group, and nothing for others, so we can say read write, because it's sort of like we have 1, 1, 0 for read write. So this is this is 2 and this is 4. So this 4 plus 2, that's 6. No, this is like the translation between binary and decimal. Then we have, so this is for the owner. For the group, we just want to read, right? So we have 1, 0, 0. So this is 4. So this is 4. And nothing for the others. So we want 0, 0, 0. And this is, of course, is 0, which we find it here at 0. So with this chmod, we get read write for owner, read for group, and nothing for others. And so this covers essentially the basic working of the Linux file system permissions. To finish off the video, we will talk about two specific mechanisms, which are the sudo and which are the SUID and GUID bit permissions and the sudo system. Now, certain executable files can have special permissions called SUID and GUID. So these are special bits in the permission, which are called SUID and GUID. Now, SUID stands for set user ID. Now, the idea is that binaries that have this bit allow the binary during its execution to change user permission. So for binaries that have this SETUID bit, this set user ID, the idea is that typically they run with one set of permission, but they can change that set during its execution. So specifically, these kind of programs can be executed by anyone. And if they are executed by anyone, first they will start their execution with a set of privileges associated to the user that executes them. So for example, if I am Leo and I execute a program with this kind of thing, initially it will execute with my permissions. However, during its execution, they have the choice. They can change their permission and take the permissions of the owner of that binary. It means, for example, that if I am the user Leo and I execute a program, and this program is actually owned by root, so it's owned by root, and this program has the SUID bit on, it can change its privileges during its execution from Leo to actually root privileges. So this is really important, and one might wonder, why do we need this mechanism? And this mechanism is useful when you want a program that can be used by anyone, but needs special permissions in certain cases. So for example, consider the program used to change the password, which is this, passwd. So you can use this command to change your user password. What does it mean? Let's just reason about it. It means that everyone should be able to use it, everyone should be able to execute it, because every user at any point should be able to change their password. But since we are changing a password, we need to save the new password, and specifically we need to save the hash of the new password into a privilege file in the system, which will then be used for later authentication. So the idea is that this program has to write to a specific file which requires high privileges, which requires root access. So the idea is that anyone should be able to use it, should be able to run it, but then at some point this program has to write into root-owned files that only root can actually write to. So at some point in its execution, this program will need to elevate its privileges, and it can do so with this particular bit, the SUID bit. So notice that if you do this in your system, this is the typical location of the passwd command, and you do ls-lh. Here, instead of execute bit, you will see the S, which stands for SUID, and it is owned by root. So in the shell, typically, this is represented in red, because it's kind of a dangerous thing. So notice this. It's in red here, because this is kind of a dangerous thing. And it is kind of a dangerous thing because during its execution, at some point, it will become root. So it's something to be careful about. So the executable bit flag is not X, but rather S. This is because the program has the set SUID bit set. This means that during its execution, at specific times, the program will change its roles in order to become root. This change of permissions is done by using the function setuid offered by the standard C library. It is necessary since the shadow file is owned by root and only root can edit it. So this is the actual source code. Here I put a link. Here you can just click on the link. It's like the source code of the shadow implementation of the passwd implementation. And in this source code, at some point, you will find this line. So it's the setuid 0. And then it says if setuid 0 is not equal to 0, we have an error. So we cannot change ID to root. After we do that, we say update shadow, or else update no shadow. So essentially the idea is that we update the shadow file. Now the shadow file is the file that contains all the hashes of the password of your users. I showcased it in the previous video. It's like if you go into user management, here there is an example of a shadow file taken from a Docker container. So in this file, you see all the users, and then here, for example, for the SSH user, there is the hash of the user. So when we call the passwd command, the idea is that we need to update this file. We need to update this etc shadow file. But of course, the problem is that this file is owned by root and its permissions are like this. Only root can read and write to it, which means that to make sure that everyone can use it, that everyone can update their password, but they also update this specific sensitive file, the idea is that, okay, the binary has the setuid bit on, and in a specific moment during its execution, thanks to the setuid function, it will elevate its privileges, it will become root for a moment, for just a brief moment in time, it will update the shadow file, and then it will go back on to execute as a normal user. We want to limit the window of execution in which we are root, so this is like the root execution, and this is like the entire execution. We want to make this window as small as possible, because the larger it is, and the more vulnerable we are to specific attacks, to privilege escalation attacks. Because if we have a program running as root that we, the user, can control, it could be dangerous. So the idea is, I'm just gonna elevate my privileges for a little moment just to update the shadow file, and then I'll go back to run as a normal user. So that if I get compromised during my entire execution, right, the moment where a compromise could actually become dangerous is very limited. It's just the tiny window where I become root, and all the other times I'm the user Leo, and after that I'm still the user Leo. If I'm compromised in these two windows, nothing happens, because you will get execution as Leo, which you already had previously, so there's nothing new. However, if I get compromised during this window, then you get execution as root, which of course can lead to privilege escalation. So this is why this setuid bit this mechanism has to sort of being handled carefully. You have to be careful when you put a SUID bit on something. To actually set a SUID bit, you can just use the S flag. So like the S meaning is like execute, but with the setuid. So you can say exec with user plus S, and notice here, so like let's say that we do this. So we have this test sh, right? So we have this test sh, then we say chmod u plus s test sh, and then here we have this thing, and this thing is only for the user. So this is the idea, only for the user. So here actually should be an X. The same idea, however, applies also to the group permissions, but this time it is called GUID, not SUID. It's called with a G because it's group OID. And we can also use chmod. It's just that instead of the U, you can put the G, so G plus S, and you're gonna have an execute bit. Instead of X is S because you have used the SUID mechanism, but however it's called GUID because it is applied to groups. It is the same thing. It means that during its execution, at some moment in time, the binary can have the privileges of the group that owns the file. It's the same idea. It just applies to the concept of groups and not single users. If you want to set the S bit for both user and group, you can just do plus S. So the idea is that you do. So let's remove it from the user. Now we don't have it for the user. If we do a simple plus S like this, we're gonna set it for the user and for the groups. So notice this S and S, capital S here. So that's the idea. So actually in this case it is a capital S because previously the group could not execute the file. So to actually make a lowercase s we have to do g+6. I think with g+6 it should be good. Yes, now it's a lowercase s. So once again it was a capital S because initially the group could not execute the file. Then we did give the GUID permission, but it still could not execute the file. So after we gave also the execution file, it became a lowercase s once again. So that's the idea. Finally, we have to talk about sudo. So an important subsystem that relates to permissions in Linux is the sudo functionality. Now sudo stands for super user do, and it is a utility in Linux that allows a user to change user for the execution of specific commands. So it's sort of like saying, okay, you are the user Leo, but you can execute a specific commands as if you were the user root or the user another user. So you sort of like you execute a command with a different user. And this is especially useful when you want to execute command as root, so that instead of being root all the time, you are your normal account Leo, but then if you want to execute a root command, you say sudo and then, for example, you install a package. So for example, in the previous video, I showcased that for package management, you always had to use the sudo command, because packages, like these kind of managers, like apt or apt-get, they typically write into sensitive places in your file system, so they need higher privileges. So to actually get them, you can use the sudo to say, okay, this command you execute as root, and once you're done with the execution, you go back to the previous user, which is like Leo or whatever users you were. So like once it is installed, we can check the way we can use it with the sudo-l. So for example, here I have a bunch of sudo-l commands, outputs from like Actebox machine and stuff like that. So the idea is that these commands tells us how we can use it. So for example, in this case, it was like a canopy machine. It says, look, you can broot to execute this command. So user bin pip install and then anything here. So the idea is that you can install with pip as root anything you want. So of course, this kind of configuration is vulnerable to privilege escalation, because by inserting a specific Linux package here, you can get actually root execution, because you are able to execute this command as root, but this command can be anything, because this asterisk, you can place any sort of Python package, and if you craft a malicious Python package, you are done for, essentially. You become root. Then this is like another, it says all no password, user bin Python, like another asterisk, home richard test. Essentially it means you can execute this command using any user you want without password. So we can be root, we can execute Python like 3, we can execute this script, and once again we have privilege escalation, assuming we can write into here. If we can write into here, we have privilege escalation. Another entry is like, okay, as root you can execute this user bin tryharder. So depending on how this binary is implemented, we can maybe find some kind of bug in the logic and we can exploit it to become root, because once we execute this tryharder, we are executing it as root. So this is essentially the idea. Another thing is that no password all, so like with every user, you don't need to put a password, you can execute the docker network inspect command and docker network ls commands. Another is that you can execute, this is like even more dangerous, because it means you can execute using the script manager user and group, you can execute all commands without a password. And actually I showcase how to do this in the bash machine. So in my Actebox, so like in my Actebox bashed, here I also have the report, essentially report content PDF. So you can watch the video, you can also watch the video wherever I this report. But at the end, so we have here, so the first pivoting from www-data to script manager is like, once inside as www-data, we can check the sudoers and we have this configuration. So like the idea is that we can just do this. This of course is like a critical vulnerability, because with this payload, so we say sudo-u script manager, it means execute the following command as a script manager. You do python 3-c, so like you create a bash with a TTY using Python, you spawn that, and then you are script manager. So this allows you to become script manager to the pivoting to script manager, and then you can spawn a shell and stuff like that. because the sudo configuration was vulnerable. So this is all to say that the sudo program allows you to execute commands as other users. It can be a normal user of the system, like script manager, or it can also be a root, like in this case all, it means all users of the system, including the administrator account, which is root. And here it says, if you have to put a password, so if you say no password, it means that you do not need to authenticate to that user. And here you have the specific commands that you can use with that user. So the sudo subsystem is extremely useful to analyze for privilege escalation. I will do a specific video on it, on how to abuse it, because for example here I showed a lot of vulnerable configuration of sudoers. So these are like configured in the file /etc/sudoers. The idea is that here you configure how you can interface with the sudo command, and then you can just check your configuration with sudo-l here. And once you have your configuration, you can check if it's vulnerable, if you can exploit it, if you can abuse it. And typically in, for example, OSCP-like scenarios, in CTFs, many times the sudo-shell is vulnerable to misconfiguration, and you can actually exploit it to do privilege escalation. So this is like a very common pathway to privilege escalation. So this covers everything for this video. We talk about file system permission. We also talk about main pages, which are extremely useful resource. For example, you can do like man chmod. Here you have all the things about the chmod of the different things, all the different documentation. You can do man sudo. You have all the execute a command as another user. So this is like all the things regarding sudo, how to use it. There are a lot of things here, of course, a lot of considerations and stuff like that. Then we talk about the file system permission, how we can read them. So how we can make sense of this output, how we can update them, how we can write them with the chmod command. And okay, here I did not talk about it essentially, but so the chmod is to change the permission. If you want to change the owner of the file as last thing, what you do is to do chown. So you do chown and then you put the username. So for example, chown root test sh. Of course, to do this I need to be root, so I need to do sudo. So with the chown command, you actually can change the owner of the file. And I think that the chown command, if we do chown --help, it should also be used to change the group, I think. Yeah, you can see this is like owner : group. So the idea is that, for example, if we say sudo chown root with the name of the file, we do this, and now we also change the group of the file. So we can add this because it's important in the updating file system permission. So here essentially it's like, okay, I would say that we can do this section here. To change the owner of the file, we can use the chown command. So the chown command, so it's like chown root test.sh. If you want to change the group, you can use the syntax with the colon here. So it's like chown user group test.sh, like for example chown root : root, like root : root test.sh. And then if I do ls lh like this, I get back this, which is useful to showcase that we actually change the stuff. So you can also use the recursive -r flag to make it recursive. I mean, there's of course, as always, a lot of things to say, but the chown is extremely useful to just change the user. This is for the -recursive to operate on an entire substructure, subdirectory structure. And after that, after the chmod and chown, we are essentially set. We talk about the SUID and GUID and the sudo. For these last two topics, I will make specific videos on privilege escalation, abusing the SUID bit and abusing the sudo configuration. So that's it for this video, and to the next video. Hi everyone, and welcome to this new video. In this video, I want to discuss a technique for doing privilege escalation on Linux machines. Now, this technique was mentioned in my OSCP technical guide blog post, which I also made a playlist here on YouTube. In particular, in the Linux section here I describe a little bit of the knowledge you need in order to pass OSCP, and then here I mention this technique for doing exploitation. In particular here, among the various techniques that I suggested to learn and practice before doing OSCP for the Linux privilege escalation part, here I mention PATH Exploitation, and this is what I want to show specifically in this video, which I call the PATH Hijacking. It is a way to exploit the path variable, and in this video in particular we will see exactly what is the path, what is the role of the path and why we use it, and then I will describe the actual attack. So if the video is interesting, please leave some comment, subscribe to the channel and let me know what you think of it. And that's it. And so we can start to understand, and we begin with the basic question: what is the path? And this is a thing that I suggest you to always do, no matter the context. Before you learn how to exploit something, before you learn the offensive side, first take your time to learn about the functionality you are trying to exploit, because otherwise you will not understand everything you need to. First, you learn the functionality, you learn why it is used and what does it do, and then you learn how to exploit it. Otherwise, you will just learn how to type a bunch of commands, but you will not really understand what is going on beneath it all. So we begin by asking, what is the path? And here I prepare a bunch of notes that I'm gonna use just to talk. So the idea is, when you launch a program, consider for example the program ls, which stands for list, like list the contents of a directory. Now, when you launch the program, the shell actually executes the program. So for example, here I am in a shell, I do ls, which stands for list, and here I have the output, which I also brought here in the notes. Oh, and by the way, these notes will be available in my GitHub, so you will find links in the description. You will have all the material that I will present in this video to explain this attack. So, as we said, I launch a program like ls and I have an output. This is pretty basic. I mean, we are all used to it once we get used to the basic shell. Now, the question we really need to ask ourselves is, okay, but how does the shell know which command to execute? Why? Because, well, in modern operating system, resources are specified by path. So we have a file system in which everything has a path. For example, currently here in the shell underneath, this is a shell in Emacs, and this shell is actually executing within a path. And to get the path I'm currently executing in, I can do, for example, here I can do pwd, so print working directory, and here it gives me this directory. This is the directory I'm currently residing in, and everything in a modern operating system, especially in Linux and Unix-like operating system, everything has a path. Every process has a working directory, every resources has a path, which means that even the commands we execute, they ultimately have to have a path. So they need to have a path. So the thing is though, when I write simply ls, here I'm not specifying the full path where this command resides. I'm just saying ls. There is something I'm omitting, there's something I'm not telling the shell. I'm just saying, look, execute the command ls. The shell somehow manages to understand what is the binary, to load the binary memory and to execute the binary, to get our output, to get the functionality that we want. Now, this means that before executing the command, the shell needs to resolve its full path. That is, it needs to know where does the program reside within the file system. And this is where the concept of a path comes in. It's in this resolving, in this missing of information that is filled up by the shell, that we need to introduce the concept of a path. Why? Because the path is an environment variable, which means it's like a value that is that has its life within the shell. So in the shell we have different environment variables, and the path is one such variable. And not only the shell has this variable, by the way, every process that executes has its own environment, which is just a bunch of variables with their values. In particular, the path environment variable is used to determine how to resolve command names into full path, so that when I write ls without the full path, thanks to the path variable, the shell will understand how to fill the missing information and how to execute the correct command. Now, in order to print the value of the path, we can use the following syntax. We can say echo, and then $, and then the name of the environment variable, which in this case it's called path, all in caps, because Linux is case sensitive. So we do echo path, and here we have the output of the variable. Now there are many different environment variables. For example, there is the environment variable home, which has the path of the home directory for the user. So as you can see, in modern operating system, everything has a path. It's sort of like the physical address where the thing resides within the file system. So we're not talking about memory in the RAM, we're not talking about RAM addresses, pointers, and things like that. We're talking about we have a bunch of abstract resources, and each of these resources has a path. So this is the idea. So for example, this is the home and this is the path. Now the structure of this value is structured actually, which means that so here I say the command, as you can see, the path is actually a list of directory paths, separated with colons. Now, if we were able to take this value, this big value, which can be confusing at first, so we take this value, and then we split it by saying, okay, here we have a column, and then we have a new line, and we remove this. Here we have another column, and then we have a new line. And we can just replace everything very fast, like this. So here wait, no, I did it wrong. So I do replace string, then I do colon, and then I do new line. So that's the actual content of the path once we've represented in a more understandable way. But it's sort of the same. It's encoded, meaning that we have a directory path, then colon, then another directory path, then colon, and so on and so forth. And all these paths here are paths in the file system, and they point to specific directories. So you have usr locals bin, usr local bin, usr bin, opt CUDA bin, opt CUDA, and so on and so forth. This is the basic idea. So we go here. So this is the path. Now, the point is, how is this path used? What is the process that is implemented in the shell process that, by using this structure encoded in this variable, allows you to understand where the command is that you want to execute? Well, the functioning is actually pretty simple. When you launch a program without a full path, like ls, like the example we just did with just ls, here I'm omitting information, so the shell has to come in and has to fill other information up. Now, when I write such commands, the shell will use this list of folders, these ones that I just showed, in order to look for the correct ls binary. Now, what does it mean, correct? Well, in this case, correct means the first that you find in all these folders. This means, and this is a crucial thing that you need to know about the path, is that there is an order in which these different folders are viewed in order to check, is the ls binary in this folder? If it is, then you use that particular ls binary, the one which has path usr locals bin ls. Now, if the ls binary is not found in this folder, you need to look for the next folder, for usr local bin. And now you ask the question, is the ls binary in this other folder? If it is, you use that. You use the binary which has full path usr local bin ls. If it's not, you go to the next. So by progressively checking all the different folders, at the end of the day, either the ls binary is in one of those folders and the shell picks the first it finds, it does not go look for further folders, just the first one, or in the negative side, you do not find ls in any of these folders. So this is the idea. First, it checks the first folder. So essentially what it's doing is checking if this file exists. If this file exists, then the shell loads into memory and execute it, because in this case, this file represents a program. So like an elf binary. If it doesn't find it, it goes to the next. So for example, in my system, does this file exist? Well, if we just execute it, it says in Italian, file or directory non esistente, which means the file does not exist, and which means that the shell goes to the next location, and the next location is usr local bin ls. So once again we check, wait, does this file exist? It does not exist, and then we go to the next, and then we do usr bin ls. Usr bin ls. Does this file exist? We try to execute it, and actually we get the execution. We found the binary. So since there is such file in our current file system, it loads the file in memory and it executes it. Why? Because this file, this user bin ls, is an ELF binary which contains all the data and instruction needed to run the list program, the ls program. So once the shell finds this file, it loads into memory and it gives it control over the execution. And so we get our execution, we get our ls. Now, if you are wondering why the execution is a little bit different, because if we just do user bin ls and ls in the normal way, here notice that in the first one we do not have colors, we do not have highlight of colors. So for example, in the second case, the archive folder is blue, while in the first case it is not. Now this is because there is a different component of the shell which slightly changed the execution of the second command. Even though the binaries are really the same, they are exactly the same, what is going on in the second case is that there is a so-called alias that actually comes in. Now, an alias is a way for the shell to do simple command substitution. For example, if I say alias ls, the shell tells me, look, every time you type ls in the shell, I'm actually typing ls, a white space, dash dash, color equal auto. So essentially what the command we're actually executing is this one. And notice that when I execute this one or this one is essentially the same. But notice also that now if I do user bin ls color auto, it's the same as before. I have all the flags of ls, so it's literally the same binary. And so this is the idea. And as a little note, if you want to understand, so indeed, notice that if we execute ls or we execute user bin ls, we get the same command with all the same flags, with all the same behavior. It's the same binary that is executed. Now, if you want to understand how a given command is resolved within that specific shell environment, within that specific process, you can use the binary which. So the binary which essentially takes in input the name of a command and it gives you in output the full path where the binary that implements that command is to be found. So in which case, if we do which ls, it's gonna resolve the way the shell already does, but it's gonna just output. It's not gonna execute the command. It's gonna output the full path of that command. And so for example, we can do which ls, and here I have user bin ls. I can also do, for example, which who am I, and there is user bin who am I. And when I execute who am I, which is the command to print the name of the current user, I'm actually executing that specific binary, the one found within user bin who am I. And a cool thing is that we can use which on itself. So we can use where is the binary which, and here I have user bin which. Of course, notice that here a funny thing happens is that to actually resolve the first switch, I'm using this path, because the shell has to call this command, so it has to resolve it. It has essentially to transform the initial call into this other call. So basically, this is the idea of the path. Why do we use the path? We use the path for convenience, so that instead of, for example, writing all the time the full path of ls, that sometimes we might forget, we just write ls, and thanks to the path, so thanks to the path and the process of the shell, of course, this is resolved into the full path. So this is the role of the path. In order to omit information, we don't want to remember exactly where the program is. We just want to say, look, it's ls. It's a common program that is found within common file system directories. So that's essentially the idea. Now, having essentially discussed all there is to discuss about the path, at least from an initial beginner point of view, we can ask ourselves, okay, but what is path hijacking and how does it work? Now, before actually going to the notes that explains the attack, I want to showcase a typical scenario in which we have to use this sort of attack. So here I do my ls command, and now we know how this command is actually resolved, and we find a binary, this reader binary. Notice that it is in red. It is in red because it's an executable binary with the set UID bit. So we have the set UID bit, which is owned by root. Now this is a specific configuration in Linux. I will not discuss in detail in this video, but if you are interested in it, I can make further videos on it. Essentially, the idea is that when we execute this binary, we are going to execute it as the user root, at least for a certain period of its execution, which means that we will have access to a lot more resources. However, we will be constrained by the logic of the program. We cannot change the bytes of this reader as the user Leo, we can just execute it. So we have to understand its logic. Now, if we try to execute this binary, we are met with this usage, and it says, look, you have to call me reader, and we can also explain this syntax, --. Now this --, it means when it comes to resolving the full path starts from the current one. So this dot in Linux, it means from the current path, you have to find the binary reader. So essentially it means the reader binary executed the reader binary that is found within this directory. So this is why we use the --. If we don't use the --, and we just use reader, it's going to try to find the reader using the path. So going, for example, into /usr, /bin, and so on and so forth. So we do /reader, and then it says, look, to execute me, you have to provide a file name. Now, I have the source code of this binary, which is always useful to have, but sometimes you might not have the source code. A cool thing that I usually do when I don't have the source code is run a simple strings. Now, the strings command gives you all the ASCII string of the binary. And if I run on this binary, I get a bunch of stuff, essentially. So here I get a bunch of stuff, but among this stuff, though, so there are like a bunch of function, fprintf, strcompare, there is a bunch of file names, and then I have this, cat.archive-%s. Now, the presence of this string is actually suspicious because it tells me that this binary is executing a system command, because cat is a system command. And then there is the path of the file. So essentially, from what I understand from this, here we have a bunch of file names. So for example, let's put this 01.txt that we found also through string. And so we are able to read this file, but this file is actually found within the archive directory. And these are because the cat, if we remember the cat reads from the archive. And the archive is a directory to which we cannot access here, because only the root user can access to the archive. So this is just a small binary that I wrote to explain this sort of attack. And indeed, now we can read the source code. This was nothing too difficult, it's just a simple example, and the logic doesn't really make too much sense, but bear with me because the most important thing is what we have to exploit. So we have a bunch of libraries, we have an array of strings which represents valid file names, we have a counter which is true, which is for the true files, and then we have the main function. So that's it. It's really simple. Here I check for the input argument, and if I do not have at least two input arguments, where the first one is the name of the program, this argv of 0, then I just exit. I say, look, to use me, you have to call the name of the program, and then you have to give me a file name. So if this is not true, it means that we have a file name that was given by the user, and so what do? We go over through the valid file names, we check the string, if we found a valid file name, if the string compare of the user's provided file name and the valid one match, and notice here, I use the version of string compare, which only checks for this length, which only checks for this amount of bytes, where this one is computed through the valid file name. And I did this to avoid buffer overflow problems, because I don't want to give the user the ability to overrun the memory. But this is a different issue, and maybe I can do videos on buffer overflow later on. This is not the point of this video. The point of this video is here. Notice that if I found a valid file name, here I'm using the code to create a command. And the command I'm creating is cat, there's a space, .-archive-%s, which this one is filled up with the user provided file. So here essentially I'm creating the command cat me this file, show me this file. Here I do setUID0 and setGID0 to become actually root. And this is possible because the binary, remember, had the setUID bit, which allows me to do this kind of stuff. And then I do system of CMD, system of command. This execute the string within essentially the underlying system as if I'm doing this. Like, essentially, I'm doing this. However, this I cannot do with my own rights. I can as root, of course. I can do that as root, but here I have this other binary which sort of bypasses this sudo mechanism, but this logic allows me just to read these files. Now, why all this nonsensical logic? Well, the vulnerability is here. Could you exploit this to become root? Well, the answer is yes. The answer is yes, and to exploit this, you have to do a path hijacking attack. Why? Well, this is the final point that we actually execute a command. So the interesting thing is, how do we construct this command? Now, this command is constructed by giving cat. So we do not specify the full path of the binary cat that we want to execute. We just say run the command cat. Now, how could this be exploited? Well, the idea is, if we, as an attacker, can modify the path environmental variable that this program sees, so if we as an attacker can modify the path of this program before we actually execute it, then when it's gonna do this system CMD, it's gonna look for the path, it's gonna use the path to resolve this command, and instead of using the original path, it's gonna use our maliciously modified path. In particular, the attack is extremely simple. What do? First, I create a fake file called cat, a malicious file which contains malicious code. And here in my notes, I add the code for doing that. So essentially, I can do this. I can do this echo-en, and this is a simple one-liner that creates a simple file, cat, that just has these 2 lines of code. So the first one is the shebang is just saying to know that it's a shell script, and the second one simply calls bin bash. Nothing more than that, nothing fancy. I just call a shell. Of course, if I execute this, after writing it, I have to make it executable. If I execute this, well, nothing changes because it just spawns another shell. And if I do exit, I still have a shell because I just spawn a new one. Now, where does the maliciousness comes in? In this other line. Now we're gonna launch the program, but with a malicious path variable. So, how do we do this? How does this command work? Let's analyze it before we actually use it. So this command is like, okay, you execute the reader with the 01.txt so that you actually use the cat command, because otherwise you will exit in the flow before the system call, before you do system of CMD. But the path I'm gonna give to you program is gonna be different. It's not gonna be the original one. Before all the folders in the original one, I'm gonna introduce a new one. I'm gonna introduce the dot folder, which represents the current folder. So what does that mean essentially? It means if I execute this, notice what do I get. Here I have a shell as root. I've just become root. Why? Because when I do this, the new path becomes the old one. So this is the old one. This is the old one. But then before everything else, I put a dot. So the first folder the program will look to find a binary is gonna be the current folder. And given that in the current folder I introduced a malicious cat, when the program actually executes, this cat is going to look for the current folder of execution, which is this folder, which is the content folder here, and it's going to find, oh look, I found a cat. I'm going to execute /cat, and by executing it, I get a shell. However, since I was executing as root, I'm going to get a shell as root. So the exploit is really simple in this case, and in general, once you find cases of PATH exploitation, most of the time it's pretty simple. Maybe you cannot write to the current folder where the program is executing. In that case, you can simply put in tmp, so you do /tmp, and you modify the path doing /tmp, and that's it. It's the same idea. And I get a shell as root. Now I am root, and everything else works the same. So notice this. If instead I have this, so I modify the path, but I put the current folder at the end of all the folders in the path. This does not work anymore. And instead of giving me a shell, it simply executed the normal cut. Because if the current folder is the last one, it means that before going to the current folder, it's gonna arrive to user bin. And once you arrive to a SUID bin, it just executes the normal cut. So this is why in all attacks of PATH exploitation, we always put our malicious folder to the first one before all the others. Because we want to control only that particular binary, we want to resolve it to point to our malicious file. And this essentially is all that I've wrote here. So here is the binary, here is how I compile it. So I compile with this, with GCC, then I make the root owner of this binary, and then I put the SUID bit with chmod. So chown to change owner, chmod to change the modality of the file, so to have the SUID bit. Here I have the archive folder with the files, whatever. And here, the program just shown is vulnerable to PATH hijacking. Notice how the program makes use of the cat binary in order to print out the contents of the file. Specifically, notice how cat is called. No full path is given. Therefore, the path that used to find the binary will be computed at runtime using the path environment variable. And this is why the program is vulnerable and can be exploited. This vulnerability arises from the fact that here I do not put the full path, I put the incomplete path that will be filled on. But then, if I want to define this program, I have to either put the full path or I have to make sure that the environment variable path that is given to me, the path, is actually correct. It contains only valid values. Because otherwise, an attacker can just modify this. Here I do not have to change the binary. You see, I do not have to change the logic of the binary. I just have to change the environment in which the binary is executing. And if the program is not well written and it is vulnerable, it does not recognize even that the environment changed and that I introduce some malicious folders. This is the general idea of this attack, and it is an extremely useful attack. Now, before calling the binary, an attacker can set up a specific environment path, and the vulnerable program will use that to find the cat binary. An attacker can then create a malicious binary or a malicious script like we did, like a simple bash script called cat, place it within the first folder of the path, the one we modified, so we can know, we control that essentially, and when the program will execute, it will find the attacker's malicious code and not the original cat, which is gonna give us arbitrary execution as the root user. And this is how we become a root. We create the malicious binary, we modified the path, and we execute it to become root. And this is it for this video. I will put this technique also in the OSCP folder, I will link it in the description. I hope the video was enjoyable. I will make videos for this kind of techniques for other sort of like both Linux and Windows privilege escalation. And that's it. Leave me some feedback if you want, and to the next video. Hi everyone and welcome to this new video. In this video I continue my Linux privilege escalation series. Now in the previous video I discussed about the Linux file system permissions, and in that video I introduced the idea of the set user ID bit, the set user ID permission. In this video we will focus on how we can exploit binaries with this particular permission when they are owned by root. So this is called SUID Exploitation, and it exploits a specific configuration when a binary has the SUID bit on and the user who owns the binary is the root user. So I hope the video is enjoyable. If you have some feedback, please leave it in the comments, share it with like-minded people, and enjoy the video. So to start off, let's briefly review what is the concept of SUID. So the idea is that when we have an executable file, these files can have special permissions on their execute bit, which is called the SUID and GUID bit. So SUID here stands for set user ID, while GUID is for set group ID, so not user but group, because a SUID acts on the permission of the owner of the file, while the GUID acts on the permission of the group that owns the file. So different sets of permission. Now when it comes to SUID, binaries that have this bit allow the binary to change user permission during its execution. Specifically, for example, consider the Passwd program. So this is a binary that is shipped with Linux distribution. Now this binary allows you to change the password of your user. In order to allow for users to change their password, this program must edit a sensitive file in Linux, which is called the shadow file, and it is present in the etc/shadow. So it is this particular file, etc shadow. Why is this file important? Because this file contains all the hashes of the password of the user, which are used during authentication. So when you want to authenticate to your Linux system, you give to the system a password. The process that checks the validity of your password computes, starting from the password, the hash of your password, and then it checks if this hash is present in the shadow file. So the shadow file is critical for authenticating users. It means that it must be protected. And indeed, if we check the privileges on this file, we see that only the root user can read and write this file. Everyone else cannot do anything on this file. So this file is highly protected. However, we can use the passwd program as a normal user and it still works, meaning that it still allows us to change our own password. How can this work? Well, because in order to access the shadow file, the passwd has a specific configuration that uses the SUID bit. Indeed, if we check the privileges of the passwd program, we see that here, in the execute bit of the owner of the file, there is an S. And this S means that this binary has this particular SUID permission. Now, I explained all about Linux file system permission in the previous video of the series, so if you don't know about that, go check it out. What is important right now is to understand that certain binaries have this particular permission bit, which allows them to use the permission of the owner of the file, regardless of who started the process. It means that as a simple user, I can start the process, for example as the user Leo, but given that this program has a setuid bit, this program will have access to the root permission. So it means that during its execution, it will act as root for certain moments during its execution. It's sort of like it has the choice to be root, to have root privileges, and it can use this to, for example, edit the shadow file. So this is a snippet of code taken from the passwd, so the source code of the passwd command, and as you can see here, there's this line, setuid 0. Essentially, it's getting the root permissions, it's getting the administrator permission for a limited period of time, just enough to update the shadow file. So that's the idea. So to recap, the SUID permission allow an executable to obtain the privileges of the owner of the executable regardless of who started the executable itself. This is only possible when you have this setuid bit. If the passwd did not have this, then when we start it as a normal user, it would only have access to normal user privileges, which means that it would not be able to set its permission as the root user, and therefore it would not be able to edit the shadow file. This is really important. To actually set this bit on a given executable, we can use the chmod command. So for example, in this case, I have this exec.sh, I do chmod u plus s, it means to the user privileges, to the owner of the file privileges, add the setuid bit, and this transforms the executable bit from an X to an S, meaning that it has SUID, the set user ID. Now, what are the security issues with respect to this system? Because in terms of functionality, there's nothing wrong with what we just described. It allows, for example, users to change their password, right? So this is like very useful. However, when it comes to security, the idea is that having a binary that runs as the owner of the file can be problematic when the owner of said file is the root user. More specifically, if the owner of the file is the root user, we might be able to do a lot of actions that only the root user can do, such as read files owned by root users, or read and write files. So not only read, but also write files owned by root. And in general, we might be able to execute arbitrary code as the root user. This, of course, depends on the logic that uses this setuid bit. Because in the example of Passwd, the fact that this program has the set user ID bit is not a problem because the logic was carefully crafted to not allow privilege escalation during its execution, unless of course there is an important bug. So the idea is that this program uses root only for a short window of time, and during that window of time everything is controlled and the user cannot change the behavior of the program, cannot change the execution path of the program. This allows a safe usage of the SUID bit. If we instead have a custom binary that is not protected with the SUID bit on and the owner of said custom binary is root, this can be really dangerous because if the logic allows the user, for example, to execute an arbitrary command, then with the SUID bit we're going to execute this command using the root privileges. So anytime we have a binary that has this bit on, we have to be careful on how its internal logic is structured, and we have to make sure that it doesn't allow us to do privilege escalation and to maybe do bypasses like authorization bypasses and stuff like that. This is really critical when we have this particular configuration. Now here I have a simple example of a SUID binary, but before discussing this example, I want to talk about three sets of user IDs, which has the real user ID, the effective user ID, and the saved user ID. Now the idea is that anytime a program executes, you have these sets of identifications that the program can use, depending on various factors. Now the real user ID represents who you really are, therefore who owns the process. If the user Leo executed a specific process, then the real user ID of that process is the user Leo. That's literally who started the command. After that, we find the effective user ID. This is the user that is used when the operating system has to make an authorization decision. This means that if the operating system has to understand if you are allowed to access a file or to execute a command and so on and so forth, instead of looking at the real user ID, it will actually look at the effective user ID. If the effective user ID, for example, is the ID 0, which is the ID of root, it doesn't matter what's your real user ID, because the operating system will allow you to do whatever stuff you want, because your effective user ID is exactly 0. So that's the point. And then we find the saved user ID, which is used when a program running with elevated privileges needs to do some unprivileged work temporarily. So for example, you have a program that runs with root user and you want to lower your privileges. Now, if you want to lower your privileges, you will save into the effective user ID or the real user ID another user ID. For example, the user ID of user Leo. Now, to go back to the root privileges, you want to save into the saved user ID the root ID, which is 0, so that later you can get back to it. Now, an unprivileged process may set its effective user ID to only one of the following: the value of the real, saved, and effective. So like the effective user ID is limited because it is actually the most important one, and an unprivileged process, a process that does not start as root, can only put here a value that was already present in these two others, either real user ID or saved user ID. This means that when a privileged process goes unprivileged for a period of time, as long as it's saved on the saved user ID, the privilege ID, which is 0, then later on, since it can do this by definition, it can just use the saved user ID to go back to root. So this is why the saved user ID is important. In our case, however, we don't really care about the saved user ID, and here I put some reference to Wikipedia. We don't really care about that because in terms of exploitation, we are mostly interested in the effective user ID. Now to continue, here I have an example of a SUID binary that just showcases what I talk about. So consider this code. This is C code. Here we have a bunch of includes. Here we have the main function, and the main function essentially does two things. First, we get some data regarding the real user ID and the effective user ID, and then we try to execute a command which is trying to call the touch hello. And touch hello is simply used to create a file called hello, an empty file. So the idea is that we want to showcase how, depending on the value of real and effective user ID, the file is created with which permission. So we can take this code and we can compile it as follows. So the code is here, content source. Here I have the code, And now I'm gonna compile it. So here I have the shell. I'm gonna compile it. So I've compiled it. Notice that now this code is owned by Leo. So this is owned by my user. And then I can execute it. I execute it and it says, look, real and effective have both the value of 1000, which is the ID of my user. If I say ID, this is the value of my user Leo. And if I check now the created file hello, it is created with Leo permission because like I'm the owner of the process that creates this file. Now, however, notice what happens when we set the SUID permission and when we change the owner to root. So the idea is that first we're gonna change the owner to root like this, and then we're gonna set the SUID binary permission. Okay, notice now that the binary now is red. It's no longer green because bash is telling us that look, this could be dangerous, so we have to be careful about it. And notice that we have owned by root with the SUID permission on. So let's remove the hello we just created previously, so now there's no hello anymore, and let's just execute again the SUID example. Notice now the difference. If before we had 1000 and 1000 on the real and effective, now the real did not change, it is still 1000, but the effective has become 0. So it is no longer 1000. It means that effectively we are running this program as root. And the consequence of this is that any action we take into this program are gonna be recognized as an action taken by the administrator account. So for example, having created the file hello, now this file is created as the root user. So this is owned by root because as the root user, as the user with effective user ID 0, we created this file. So this is really important. So once again, this brings us to the issue using SUID, because the issue is that we can create file as root, we can modify file as root, and so on and so forth. Now the idea is that in your enumeration of a Linux file system, you might find binaries that are owned by root and that have this SUID permission on. In these cases, to actually exploit the binary and obtain various privileges as root, I suggest you check out the website GTFObins.github.io, because this website contains a list of binaries, and depending on the permission you have, it tells you how to exploit it. So here you just say SUID, and here you have the list of binaries, and for every binaries it tells you, okay, how can you exploit that binary to obtain root, execution, or read permission or write permission into the file system using the SUID binary, using the SUID permission essentially. So for example, in this case I brought a bunch of examples, 4 specific examples, just to showcase. This exploitation of course is binary specific, because each binary has its own logic. So for example, we can start with wget. So we can install wget locally as follows. So I do this command and now I have a wget with sudo here, wget. Perfect. Now the actual exploit works as follows. So this is the code. Let's try to understand it. So the idea is that we're going to create a temporary file using the maketemp command. So this maketemp creates a temporary file in the temp directory and it assigns the file path to a bash variable like this, so that with tf we have the path of the temporary file that has just been created. Then we're gonna make this chmod plus x, so we're gonna make this temporary file executable. Then we're gonna write into this temporary file this command in bash, which is called, this is the shebang that tells you that you want to execute this with a shell interpreter, with an sh interpreter, and this is essentially the command you actually want to execute, which is bin sh. So this is the idea. So now if we check out the content of tf, notice that we have this. So this first thing is saying, okay, look, execute this binary with the sh and the /p. The /p is used to decrease the security level, the way that permissions are handled. The second line is the actual command we want to use, and it simply spawns another shell. So it spawns another shell, which is the bin sh shell. And then finally, the actual exploitation is just we call the wget here, and then we use this particular flag, which is called the use askpass equal the file name with 0. So if we execute this, notice what we get a shell running as root. So the idea, the way it worked, is that the wget program has various flags. Now, since we are running this program as root, we want to find one of those flags, one of those parameters, one of those options that allows us to execute arbitrary code. And in this case, the way forward was with the askpass option, because the use askpass takes in an arbitrary command which is used to handle a password manager. It sort of like specifies the command to execute to get the credentials for doing HTTP requests with wget. So it's sort of like we are hijacking the logic of the program for our own personal benefit, which is that of privilege escalation. Now notice that of course this particular exploitation will be very different from others exploitation. The idea when it comes to SUID exploitation is that each binary has its logic. If the binary is configured with the SUID bit and is owned by root, we're able to execute that logic as the root user. So the next step to actually obtain, for example, a root shell is to understand that logic and understand what in that logic allows us to obtain a root shell or in general root execution. In the case of the wget command, it is this particular option, the use askpass. So to do it manually, once again, what we did is we copied the binary from the root own file. So right now I'm just gonna copy it as the normal user. Then I create a script, hello.sh, I made it executable. And in this script, essentially, I wrote the following content. So I wrote this first line, this one, and then this second line like this. And then I simply executed the wget here as follows. With the flag use askpass, then pwd to say print working directory, hello.sh, and then 0, like this. And now here I have a shell. Of course, in this case, the shell does not run as root because I did not put the SUID bit on. But in general, with wget, I can get a arbitrary shell. And then once we have the SUID permission, I have a shell as root. So that's the idea with wget. Now, the second example, we are using the program hexdump. And with this example, I want to showcase that not with all program we're able to exploit the SUID logic to obtain code execution. For example, with this program, we can at most obtain file reading as root. So once again, how do we do this? We install the binary with the SUID. So this is like a SUID binary. And then let's say that we have another, let's say that I'm going to move as root and I'm going to create a secret file that is owned by root. Secret. So secret file that is owned by root, I'm going to chmod this to have 600 secret. So secret is like only root can access it, right? So as a normal user, I will never be able to read the secret. Permission denied. However, given that I can use hexdump, how can I do it? I can do hexdump, C, and then I put secret. And this allows me to read a file owned by root. Why is this the case? Because in the logic of hexdump, I am able to read files. And when I have like the logic of the program and I can use root permissions to use that logic, then I'm able to read files by root. So the idea is that you have on the one hand the logic functionalities, functions, and on the other hand you have the permissions. So depending on the logic functions, having permissions as root allows you to do more stuff as root. But sometimes the logic only allows you, for example, to read file. So typically the kind of logic functions are either read, write, or execute. So depending on the kind of permission that a specific binary has, you may be able to execute stuff as root, which is the highest form of privilege, or only read or write stuff as root. So that's the idea. Of course, with something like this, if we, for example, steal an SSH key from the root directory, it could still be good, right? Because at the end of the day, with an SSH key, we can log in as root if it is configured to do so. So even having just readability can become detrimental if you can escalate it with typical attack vectors such as reading SSH keys. Now, the third example here is more interesting. It has to do with ssh-keygen, which is a utility that you can use to generate SSH keys. Now, once again, the first step is to copy into our local folder the SUID version of the binary as follows. So now we have this SUID vulnerable version of this binary. Now, ssh-keygen, in the options that it also offers the options to load a shared library. In Linux, these libraries are called shared object, so like .so. So with the D option, we can load an arbitrary shared object. It means essentially that we can inject in the code of the process arbitrary code. However, we have to wrap that code into an SO object. So how can we do that? Well, here I prepared a malicious example. So this malicious.c. So it's these two functions. Now the important thing is that here there is an init function because I compiled it with the no-start files. So there's not the typical main. I go directly with init. And also in this file, there is this function called cgetFunctionList. This is because ssh-keygen expects the shared object that is created to contain this particular symbol. So essentially we have to define a function that is called in this particular way, otherwise we'll get an error. So let's see what error we get. If we comment out this function and we compile everything with this, so here it says, use GCC to compile into a share object with a dash shared, then do not add the startup file, so like do not put the typical main that you see in C application. In this one, I don't want it. I just want an init. It means that I cannot take arguments from the command line. Then this is like an option in the way that the code is organized, position independent code. We don't really care about that. And then we put the output file as the malicious.so, that stands for share object. And here is the input file that contains this code. So we execute this and we obtain this malicious.so. And this is like a share object. Perfect. Then we can say ssh-keygen -d with the malicious SO. Notice, however, that in this case we do not get code execution. Why? Because it says, look, this share object does not contain the expected string cgetFunctionList. Because the idea is that when this binary loads the share object, it's gonna extract from the share object a bunch of symbols, and these symbols are specified by strings. In this case, when it tries to extract from the share object the symbol cgetFunctionList, it did not get anything because this share object does not export anything. It does not export this particular symbol. So to fix this program, we have to add an extra function, this cgetFunctionList, with our own logic, of course. We can hijack the logic. It's not really important, the logic. What is important is that this function has, like, it's called this function, and we also have like 2 times the malicious code. We can also have it just in init, it's the same. However, it's useful also to put it 2 times to make sure that it actually gets executed. So we compile it again. So we have a new malicious.sh, and now when I do ssh-keygen with the malicious, so let's say cannot open no such file or directory. So let's try to remove this and let's redo it again. ssh-keygen -d malicious. Okay, so I just had to specify the local path for the -d option. Here before that didn't work, I had this, so like it actually started, okay. So notice that here before it was not a local path, so I did not understood where it was, but with the .dash, now with the /, now it understands where to load the malicious share objects, and now we have code execution. Once again, we can execute things as root. Why? Because right now the logic of exploitation had to do with ssh-keygen. ssh-keygen in its logic allows us to load a dynamic library, and we have constructed a malicious dynamic library that when executed allows us to execute our code, which is a simple shell with bin/p with system. So as simple as that. And we do this setwd and setgid to make sure that this shell is executed with elevated privileges. And as a fourth and final example, I want to showcase how to exploit 2 important text editors that are also famous, which are Emacs and Vim. Now, both of them, if you happen to have the SUID binary that runs that particular editor, you can use it to obtain remote code execution. So this is the exploit for Emacs, and down we find the exploit for Vim. The idea essentially is that both of these text editors allows you to execute code. So in the context of Emacs, you can do this, which is -q to not load any configuration, -nw to open a new terminal window, --eval to execute customary Emacs Lisp code, and this Emacs Lisp code executes a new shell. So now I'm just going to execute it without copying in the current directory, because I have some problem with libraries. But you execute this and you have a shell running as your user. In this case, I'm running as user Leo because the Emacs binary does not have the SUID bit on, the SUID permission, If you also have the SUID permission, you can get root execution, so be careful about that. The same things happen for Vim. Essentially, the idea is that with Vim you can execute arbitrary code. So actually this specific payload for Vim does not work because I did not compile Vim with Python support. But in general, the idea is you find a binary that has the SUID permission, you go into this site, GTFObins github.io, and you search for your binary. For example, ZH, APT, Spell, AWS, AWK, and so on and so forth. Once you find the correct binary, you just do the payload that brings you elevated privileges, which could be read privileges, write privileges, or a remote code execution. And we saw a bunch of examples. Now to finish off the video, how do you search for SUID binaries? You can use this command. Find, which is a command used to find file system. You can also say, look, I want to find starting from the root of the file system, which means find in the entire file system all the files that are files, so type F, it must be a file, not a directory. And in terms of permission, as the user permission set to S. So the executable bit of the user is set to S, which means it is used to find the SUID binaries. The same thing can be done for the GUID binaries with the G equal S, -G equal S. And here you say chew with this redirection to say all the errors you just put into dev null, because you're not really interested in the errors. So when you reach into a Linux system and you want to do SUID exploitation, you search for all the SUID binaries, and for the ones that you find, you use these GTFObins. Depending on the binary, for example, if you find wget, you can use this. If you find ssh-keygen, you can use this. If you find hexdump, you can use this. If you find Emacs, you can use this, and so on and so forth. So depending on the binary, the specific exploitation is different, because remember, the idea is that with a SUID binary, if it's owned by root also, you are able to execute the logic of the binary as root, and depending on the options that the program offers, for example, loading a dynamic library is an option, or reading a file and printing the bytes in hexdump is another option, or using a specific command to use the password manager is an option. So you want to hijack the specific logic of the program, and if you are able to do that, you will obtain root privileges in read, write, or execute. If you obtain it in execute and you're able to spawn a general shell as root, you are done with privilege escalation. So I hope the video was clear. If you have any problem, just write me in the comments, and to the next video. Hi everyone, and welcome to this new video. In this video, I continue my Linux privilege escalation series. In particular, in this video, we will analyze how to do SUDO exploitation. That is, how to use the sudo command and the sudo subsystem in order to do privilege escalation and obtain root privileges. So this is the basic idea. The video is structured as follows. We have a Docker setup, so I prepare a really simple Docker image to play around with sudo. I will explain what is sudo. I already did that in the Linux permission video, but we will do a review to understand how does it work, what it is, and why it can be used to do privilege escalation. Then we will analyze how we can configure sudo, because the idea is that SUID exploitation has to do with misconfiguration of the system. So we will analyze how to read the sudo configuration and how to understand if a sudo configuration is vulnerable or not. And finally, we will do some sudo exploitation. So some practical example. I prepare 4 examples in which we're gonna exploit the sudo command. And then at the end, I leave some reference. So I hope the video is gonna be enjoyable and useful. If you like it, please leave some feedback, share with like-minded people, and subscribe to the channel to support me and future videos. That's it, enjoy the video. So as always, I like to play with Docker, with having some simple Docker file. In this case, to play around with sudo, instead of changing the configuration of our Linux system, of the system we use, it is much better to just play with sudo and change it there, destroy the container, and that's it, so we don't have to worry about it. So I prepare a really simple Docker file, this Docker file. I literally just get the latest image from Ubuntu, I do the update of the repositories, and then I install sudo and nano to edit sudo. Finally, this is important step, I set the password of the user Ubuntu, which is the default user of the machine, to the value test. So we know the password of Ubuntu, and it's gonna be critical. So this is the Docker file, how we can build it with this Docker build command. So we go into the directory where we have the Docker file here, and then we do sudo, like, okay, let's split it like this instead. We're gonna do this, sudo build, I already built it, then you can just run it. We do sudo run. I always give a name to my container, and I also use the option --rm. This means that the container is gonna be removed once I stop it. This is useful for all those containers that you just use for quick tries, so that not containers that hold services that you want to persist through the various stop and start, but containers that hold no really important information, so you can just delete them and create them new. So this is the idea, and then once we run the Docker, we can go into the Docker, we can obtain a shell into the container with this docker exec command. All these commands that I'm showing are gonna be available, just follow the links in the description, everything will be available to you, so you can also play around with it. So we do docker exec -t sudo lab is the name of the container, and then the command we want to execute, which is /bin/bash, which is our shell. So we do this, and notice the hostname change, the username change from Leo to root. It means we are inside the Docker. So at this point we can play around with this, we can do commands. So of course right now we are root, and we have a user in this machine, because if you go into the /home and we do ls, notice that there is an Ubuntu directory. This signifies that there is an Ubuntu username. We can also understand this by doing a simple cut of the etc passwd, because this file contains all the users of the machine, and in the last line of this file we see a line that starts with Ubuntu. So this tells us, look, there is a user that is called Ubuntu. So that's really important. So this is the setup, so we can review what is sudo and how we can use it to do privilege escalation. So what is sudo? Sudo stands for super user do, and it is an important subsystem. It is an important utility that relates to the way that permissions are managed in Linux distribution. For example, whatever distribution you use, sudo is sort of like distribution agnostic. It means that you can use it in Arch Linux, in Ubuntu, and in many different distributions. Essentially, any distribution supports the sudo utility. So the idea is that you're gonna have to download it initially. So you can do it, for example, with the pacman package manager or with the apt. So depending on the package manager, the download command will be different. In this case, it's apt install sudo in Ubuntu. And then, once you have installed it, you can say, okay, where is it in the file system? And it tells you the path. Now, the way you actually use it is, first of all, you have to understand how it was configured. Because this program, in its essence, allows you to execute specific commands as different users. Now here it says super user do. It's sort of like saying, okay, do this action as a super user, but actually in its most generality, sudo allows you to execute a command with a different user. Not necessarily the root user, so like not necessarily the super user of the system, but also as a simple other user. So for example, if I am the user Leo, and there are also the user Ubuntu in the machine, sudo could allow me to execute a specific command as the user Ubuntu. So this is the idea. Notice, I'm not executing any command as the user Ubuntu, but only a specific set of commands that have been pre-configured. This is why the first and most important aspect of understanding sudo is understanding how it was configured, because different configurations could be either vulnerable or not vulnerable, depending on how they are configured. So how do you check the configuration for your particular instance of sudo? The idea is to execute the command sudo-l. It sort of stands for sudo list out the configuration for my particular user in the sudo subsystem. Now, the first time you execute this command is actually gonna ask you for a password, and specifically it's gonna ask you for the password of your user. So if I'm executing sudo-l with the Leo user, it's gonna ask me for the password of the Leo account in the system. If I'm executing with the Ubuntu user, it's gonna ask me for the Ubuntu password. Now this step is really important because it is used for authentication purposes. The idea is that this system, this subsystem, the pseudo subsystem, can only be used after a proper authentication, so you need to know the password of your user. This means that if you get a reverse shell on your target, so you get code execution on your target and you get code execution as a normal user of your system, you are not able to immediately abuse the pseudo functionality. Before doing that, you need to authenticate. You need to find the password of your user. Conversely, it means that if you, for example, find an SSH login with the password of a user, so you know the password of the user and you obtain execution on a remote machine, the first thing you should always do is do a sudo-l to check how sudo was configured. Because if it was misconfigured, then you most likely have an easy way to do privilege escalation. So for example, if you are doing the OSCP exam, you get inside a machine and you have the password of the user, or in your traveling, in your machine, in your walkthrough, you find at some point the password of the user, then you must enumerate the sudo-l attack surface, because it's really important. So what happens when you do a sudo-l, for example? Well, you will get an output like the following one. So you would get matching default entries for root on system. So it says, this is how the sudo was configured for your specific user in your specific machine. This means that different user might have different sudo configuration. So if you get access to an account and you do sudo-l and nothing cool comes out of that, nothing usable, then if you get into a different account, you have to redo once again sudo-l, because different accounts can have different configuration. In this case, we are seeing the configuration for the root user of the machine. And specifically, the interesting part, so this initial part is not really that interesting. Essentially, it's saying how it is configured to be used. So like, for example, this mail bad pass, it's saying, if you use the sudo system and you forget the password, you put the wrong password, a mail will be sent to the administrator of the machine. So that's the idea. And this env reset instead is telling you that the new command, the command that you execute through the sudo system, will be executed with a different environment, with a more minimal and validated environment. And when I mean environment, I'm referring to the environment variables. So it's gonna mean that the new command will be executed in an environment with less variable and with variable with control values. For example, this secure path here, it's specifying the path variable that will be used to execute the sudo command. And why is it important to secure this variable? Because if you remember, I made a video on PATH Hijacking. It is a technique in which the attacker changes the path, and by changing the path is able to trick the program into executing a malicious binary. So in order to not allow this sort of attack, this path hijacking attack, the commands that you execute as sudo are executed within a control environment. So that's the idea. And finally, this is the most important part. The first line are always the same. You shouldn't really care that much about them most of the time. However, the things you really care about is this. It's saying, look, your user was configured as follows. And then here we see a bunch of all. Essentially, it's saying we can execute all commands as all users and all groups. Sort of saying you can do whatever you want in this system, which is of course a very positive thing. It's a very cool thing, but it also makes sense, right? Because we are just the root account, so there's nothing special about that. Now, if you're interested in reading the configuration for the sudoers, you can go into /etc/sudoers. So for example, in our Docker machine here, if I do sudo -l, I get the same output essentially. So I can, as a root, I can execute any command as any user and any group. So the part here within the parentheses essentially have to do with who can we impersonate while we execute the command. While the part outside the parentheses, it's about the commands we can actually execute. And the command all, the string all, is sort of like a wildcard. It says, no matter what, you can execute that. So the first all has to be interpreted like you can impersonate any user. The second all, you can impersonate any group. And the third all is you can execute any program. So we have user, we have group, and we have program. So that's essentially how we can read it. And so as I said, the configuration file is in /etc/sudoers. So we can understand how we do sudo configuration. So let's say that we want to edit this file, because let's say that, for example, in our Docker, if I do cat etc sudoers, I get all of this. So it's like all of this stuff. I redo it, cat etc sudoers. Actually, let's open it with less. I think it's going to be more clear. I don't have less here. Maybe let's install it. Let's hope nothing breaks. Okay, I'm downloading it and I do less etc sudoers. Okay, first I need to do a clear and then I do less etc sudoers. Perfect. So we see the actual file. So this is how it starts with this file must be edited with visudo command as root. And then it starts with the definition for the defaults. So it says mreset, mailbed path, secure path. So those are the things we already saw. Then if we scroll down, we see a bunch of comments, like all these lines are just commented because they have these hashtags essentially, which is like a comment. And then at the end of the file, we have the juicy part, because at the end of the file, we have this include, which includes other file in the configuration. And then we have this root, and then the all equal and the thing that we saw. So the idea is that this is saying, okay, apply this configuration to this particular user. So it's sort of saying, okay, apply the configuration which is on the right side of the line to the user on the left side, so to the root user. And the configuration we saw is, so there is this parenthesis here and this all. We already said that this is user, the first all, group the second, and program the third. But then here we see a fourth all, which is before the parenthesis. Now this fourth all actually represents the host in which we can actually execute that sudo command. And all means any host in the network. Why? Because sudo can also be used in setup where the machine is connected to other machines and they share the same authentication mechanism. So you can be a user on one machine, but you can also log in other machines. In this case, it makes sense to also have an identifier over which host you can authenticate with sudo, essentially. So in this case, it's all, this small joke with words, which means that in any host, you can impersonate any user and any group to execute any program. So it's literally saying you can do whatever you want. So this is interesting. And then we see these other two lines, which are also extremely interesting. Now, they are essentially the same. However, they do not apply to single users, but they apply to groups of users. It means, for example, that every user of the admin group, once again, is able to execute all programs as all users, and any user of the sudo group is able to execute all programs as all users, all groups, and as all hosts. So to specify a group, we actually use here the percentage sign, because it is a group. And essentially, this is the basic idea of the configuration. So for example, we say we start from the initial flags. This I already discussed. And then we have the thing where we specify the policies that have to be executed by sudo, essentially, that have to be implemented by sudo. So when we do something with sudo, sudo is going to look into this file to check if the action we want to take is actually allowed and authorized or not. So these policies specify how the sudo command will be used and what different users can do with the sudo command. So the rules are checked in order and the last rule that matches is used. Actually, on this part, I cannot guarantee which is the last rule or the first rule, but the idea is that if you have multiple rules that can apply, there's going to be someone who decides, okay, which one do we actually apply? So in this case, it could be the last one. I cannot guarantee 100% on this. You can do some experiments to figure it out. It should be fun. So the structure of the rules is as follows. So we have the user or the group on which this policy applies. Then we have the host name or the keyword all, meaning all sort of host names. Then we have the equal sign. We have the identification for the impersonification. So this could be a single line, for example, all, which represents the user, or we can break it into user and then colon group. And finally, the command. So this is like the basic syntax. On top of this basic syntax, we can have sort of modifiers, which modify the way the policy is executed and enforced. So for example, if you consider the following line, here we are applying a policy on the user Ubuntu. We are saying, look, on any host, you can impersonificate any user to execute any program. Notice, however, that between the parentheses and before the final all, which represents the program that can be used with sudo, we find this NOPASSWD and colon. So the idea is that this says, look, you can execute on any host any command as any user without supplying a password every time. So specifically, the first all refers to the host, the second to the target users, the last to the allowed commands, and the NOPASSWD is an extra option to not require any sort of passwords, which can be really, really useful. Because other times, it can also be like, it can also ask you for a password essentially. So depending on how it is configured. In this case, it says, look, you do not need a password. Now, if you want to edit the configuration file for the sudo system, we said that this configuration file sits on the etc file system. So we have like the etc sudoers, it is a file. So technically you can just open any file editors like Nano. You can go here and you can just edit it, right? However, to make sure you don't edit it in a way that breaks the sudo program, you should actually use a specific program called visudo. Now, why is this important? It is important because if, for example, I edit this file and I introduce a syntax error on how the configuration is written, so for example, I forgot to close a parenthesis here, I leave this parenthesis open, what happens is that the sudo program, when trying to read and parse and understand this configuration, is going to have a problem. It's not going to be fully able to understand it. So it could mean crashes, it could mean the sudo does not work anymore. To avoid this, what's the idea? We don't edit it as normal text editor, but before editing, we use the program visudo. So we use visudo to edit the file. Now this is useful because the program visudo will warn us if we have edited in the wrong way, if we have left some syntax error. So it is extremely useful to do it. Now to see some configuration, we're now gonna see 4 different examples of what we can do when we have a vulnerable sudo-l. Once again, for the sudo-l, a critical resource is represented by the GTFObins. Now this is already discuss about this in the video about SUID Exploitation, which is different from sudo. However, in the same website, there's also the filter for sudo. So what does it mean? It means that if you have sudo capability, you just write the name of a program, or like here you can see a bunch of programs that will allow you to escalate your privileges in the read, write, or execute, depending on the program, using sudo. So for example, if I can use a sudo and I can do base64, which we're gonna see at the end of this video, we're gonna be able to read root protected files, which is really critical because we have a read level permission of administrator. We could read private SSH keys that could do a lot of damage. So of course, the key idea to understand here that similar to the SUID exploitation, which was heavily dependent on the logic of the binary, here is the same thing for sudo. Depending on the binary on which we can execute sudo, we can do different things. Depending on the way that the sudo file is configured also, we can do different things. Because sometimes, and this is really interesting, within the sudo, we don't see just the name of a program. We also see the pattern of usage of that program. So consider this example. Here we have a look. You can execute the command sudo pip user bin pip install as the user root, and here we have a wildcard. Now this means essentially that here you can put anything after the install. So if you find a series of options that have this initial pattern and that allow you to get code execution, then you have a privilege escalation. But the important thing is that sudo just makes sure that the first part of the program is as it is written in the configuration file. If it doesn't start with usr bin pip, but with another thing, it's not going to be valid and you won't be able to use it with sudo. However, if it does start with usr bin pip, pip, and then with install, then you can put anything after that and you will be able to execute that as root with sudo. So the art of SUID exploitation is to understand the pattern that you're given and what you can do with it. And so to this end, we're going to see 4 examples. Of course, there could be 1,000 different examples here. The idea is just to understand how this works. So as I said before, to exploit sudo, you have to enter into this mindset that anytime you get access to a shell into a system and you know the password of that user, you should always execute a sudo the shell to understand how sudo was configured in your machine. When you understand how sudo is configured, you know, okay, maybe I can use it to gain privileges or not. So this is the idea. So we start with this first example that I've actually showcased already in the best walkthrough of ActedBox. Now, ActedBox is a great resource because the machines in ActedBox are filled with these kind of practical steps. And for example, in Bash, once we got a reverse shell into the machine, we were executing as www-data, right? So we were executing as this particular user. And then when we did sudo the shell, we were actually able to obtain this configuration. So we are able to obtain this configuration, and in particular it says, look, you can execute the following commands on Bash, and we were able to execute all commands without password as the user script manager. So in this case, it was just clear what we needed to do, essentially. So how would you exploit such thing? Well, the idea is that let's reason about it, right? So we are executing as www-data, but we can execute any command as the script manager user. So this is a sort of privilege escalation where we switch from one user to another, from www-data to another user, which is script manager. And we don't even need a password for doing this, which means that we don't even need to authenticate with the sudo the shell system to do this. The idea is that we just do the sudo the shell, we understand this, and then the actual exploit is the one as follows. So we use sudo, because of course we have to use the sudo subsystem, -u script manager, which means you're gonna impersonificate this user for the next command. So it means the next command you will execute as the user script manager. And what is the next command? Well, we have free choice over the next command. And so we do, look, call a shell, a PTY shell with Python. Now, this particular pattern, Python 3 -c import pty.spawn bin bash, is used to set up a full working shell with a PTY, which is like a communication channel that is robust. So it's like a really known pattern when doing reverse shell, when upgrading your shell to a normal shell. But we could put any command there. We could have put a command for another reverse shell. We could have put anything, essentially. The idea is that with this configuration, we can execute any command as the user script manager, which is extremely powerful. So this one, I won't even show an example, because if you check the bash walkthrough, you already see this in practice. So let's continue with the second command, which is actually more interesting. So in the second command, which was taken from a different ActedBox machine, the idea that I did not bring this time to the channel, so this is like brand new. The idea is that the sudo subsystem allows us to execute the pip command. And in particular, we can do usr bin pip install anything here. So it is not specified what we can install with pip. We can install any command whatsoever. So suppose that we have this configuration of sudo. It allows us to execute the pip command with a wildcard, so we can continue the command however we want. So how do we do this? Well, the idea for the exploitation essentially is to simulate the installation of a package. We're actually going to install a package, However, this package is minimal and it is malicious. Specifically, this is the structure of the code of the package. I took this as an inspiration from the following GitHub repository. So I want to thank the author 0x00 and I just sort of like stripped from everything in the repo. In the repo it is a bit more complex. I just took the main portion to understand how to hook into the installation process. So the idea is that we're gonna do this. We're gonna hook into the installation process, and in this function, in this method run, we're gonna execute whatever we want. And the idea is that this execution will take place as the root user. So let's do this exploitation. Here I have my shell on the left. So what do? I do this. I create a folder named test, which is gonna contain our malicious package. I enter into this folder. I create a touch setup.py, so I touch a file, which means I create a file. Then I edit this file with the following code. So this code is gonna hook into the installation process, and I'm gonna save this. So essentially we're gonna hook into the installation process, and upon the installation, we're gonna execute this install.run, which is normal Python code to install packages, but also we're gonna do os.system whoami redirect to tmp test. So we're gonna execute the whoami command, and we're gonna redirect the output to the /tmp/test. So how do we trigger this code? Well, the idea is that we go inside the folder here, and then we do. Remember that we have to satisfy the pattern configured in sudo, so we do sudo user bin pip install. Now at this point here there's a wildcard, which means that we can continue however we want, and the idea is to do --upgrade --force reinstall. So we execute this, and let's see what it's gonna do. It's gonna do like it's gonna create some problem because of a thing with the pip. But however, it says, look, if you want to ignore this error, you can just add the flag break system packages. And just to explain, this error has to do with the fact that pip before allowed you to install packages in the global repository, so in the global system. However, this led to various dependency problems. So in order to avoid this now, they don't allow you to install into the global namespace unless you explicitly say so with these break system packages. So I do this, and notice what happened. It installed the package test, and if we check into the tmp directory, we get a test folder, and if we check here, we get the root. So we are actually the user root. And to make sure that we are the user root, we can also do this. Let's go into the user directory here, and I'm not sure if we have ssh-keygen. Okay, we don't have it. Let's try to install it. ssh-keygen, probably not like this, right? Probably I just have to do ssh-t. What if I do ssh-t? Open ssh server. So I'm trying to remember how to install the OpenSSH server. So we're going to install a typical OpenSSH server. We're going to generate an SSH key, and we're going to read it using this method, just to showcase a little bit of more complex like technique that you would do in a privilege escalation. So now I should have ssh-keygen. Yes, I do it. And the way we can use it is ssh-keygen. Then I do, I think it's trsa, and then I do d, and then I do, let's see if I do like this. Okay, it's gonna say, okay, I'm gonna generate a private public RSA key. It's gonna tell me where to store it into the SSH directory, no passphrase. Okay, so it has generated a key here. So this is my SSH private key, and now I am the user root. Let's steal it with the user Ubuntu. So I am into the user Ubuntu now. Of course, I cannot access the SSH key because it says permission denied, right? But now we have execution as root. So what I did now is I changed the command that we execute once we install the package. Instead of just printing whoami into the tmp folder, now instead I'm reading with cat the SSH key of the root user, and I'm printing it into the tmp folder. So that's the new idea for the attack. So we can sort of like do it the same way. So let's remember the command here that I use is this one. Of course, notice that tmp now is just with test. So I execute this command, and I have to actually add this extra flag here. So let's write it here, and I'm gonna also note it here. So it installed the package. Now we go into the tmp. Notice we get a tmp drsa, right? So we do tmp id_rsa, and boom, we have our private key. So we have stolen the SSH key of the root user, and this is a typical path for privilege escalation, because with this SSH key we can log in into the user. Now, I do not believe that the SSH server is running, so what if I do SSH id_rsa root localhost? I don't think it's working because it's not running the server, so we cannot do that. Maybe in a later video I will show how to deal with SSH, but the point is that we were able to read a critical file as root thanks to this exploit. And to recap what we did with pip, the idea is that the sudo configuration allowed us to execute this command as root. However, this command was not fully specified because there was a portion that was missing, this wildcard, and it allows us to expand that portion with whatever we wanted. So the actual exploit was this: pip install dot upgrade force reinstall break system packages, and this dot was done into the directory in which we had created a malicious setup.py, which during the installation process executed an arbitrary command, for example, who am I, but also cut off the SSH key. So this is the second example that I wanted to bring, which had to do with pip. Now moving on to the third example. This time it's going to be faster because it's a single line of exploit. Suppose that in our configuration we can use the tar command as follows. So the first thing I'm going to do now is going to edit once again the sudoers, and I'm going to put this one instead. So we don't have this pip install right now, but rather we have this user bin tar des cvf and then wildcard. So this is sort of like, okay, you can do tar as root. Now let's go into Ubuntu. Let's do a sudo l, and now notice it is not the user pip install anymore that we can use. It is the tar command that we can use. So how can we exploit this instead? It is much easier because it is a single line and we don't even need any extra script or whatever. So the line is this. We're going to do a sudo tar. Of course, here it's going to put the entire path. Then we're going to do cvf. We're going to put exactly the way it was configured here. And then here we're going to put this devnull. We're going to put a checkpoint, and we're going to put a checkpoint action. The idea is that during the tar process, during the creation of compressed archives, which is the objective of the tar command, we're able to execute actions depending on certain checkpoint. And in particular, it says, look, every time you find a checkpoint, you execute the command bin sh. And since this command is executed as root, we will have a bin sh as root. So let's execute this. And notice what we get. Easily, we went from Ubuntu to root in no time in a single exploit, in a single line. And for example, if here we change from bin sh to bin bash, here we have a full root shell. We can go into the root directory, into the SSH, and we can once again read the private key of the root user. So this was a simpler example to showcase how dangerous tar is to be exposed in the sudo configuration. So that's the idea to understand. The sudo subsystem itself is secure. What matters, however, is how we configure it. It's the specific configuration that is done on the machine we are trying to do a privilege escalation over. And for example, in OSCP-like box, in active box machine, in CTFs, and sometimes even in penetration test, it happens that you find machine with misconfigured sudo. For example, in this case, this is a misconfigured sudo, because by abusing the tar binary executed as root, we're able to obtain like a privilege escalation. We're able to execute any command as root, and therefore also the bin bash command, which is a full-fledged shell as the root user. And so we can move on to the fourth and final example, which is going to be base64. So let's say you can execute just the command base64 with no extra flag. So this is just the command base64, and of course with the file that you want to apply this base64. So what can you do with this? Well, the idea is as follows. So let's do this. Let's put this into the configuration. So I go this, exit, I do visudo. I go down, and here I put not this star, wait, I have to go down, not this star, but user bin base64. Perfect. Then I go into Ubuntu, as always. I do a sudo -l. Notice now I can say, look, I can execute base64. Now in this case, we're able only to read file as root. We are not able to execute arbitrary programs as root, because base64 is used to read a file and compute the base64 of that file. It is a specific type of encoding. So for example, we can say echo, we can go into base64, and it's going to compute the base64 of this particular string, of the echo string. We can also apply that to files. So for example, let's say that I have a file. Let's say I create a file like test.txt. Hello, please subscribe. This is an example to showcase the base64 binary. Then I save the file. So this is my file. It's actually cat test.txt. So how can I base64 the entire file? I just do base64 test.txt, and here I have my base64. If then I want to decode it, which means going from base64 to the text content, to the original content, I can do base64 test.txt, and I can put into a file, encoded test.txt. So this is the encoded thing. And then I can take this and I can apply to base64-d. It means decode. So the idea is that we have some text, then we do a base64 of that text, and then we do a decode of that text to go back to the original text. Now the same thing, of course, can also be applied to the sudo. The idea now is that not only we can use the base64, we can use the base64 with root privileges. So what's the idea here? The idea is to do, okay, we do sudo, we do user bin base64. Here we put the file we want to read. For example, root ssh edrsa. And notice here what we get. We get not the content directly, we get the content in base64. To actually get the content directly, we just have to add a pipe and say base64-d. To say, like, after you got the content, I want you to decode it. And so here we see the line private key, we get the actual private key. But of course, even if we didn't do the second base64, we can take this base64 and we can use any decoders. It's practically as if we have the original bytes, because it is not an encrypted layer. It is a simple encoding layer which can easily be undone. We can easily remove the base64 encoding. And so this final example showcases when we cannot fully execute code. However, we can still read files as root, and this can be dangerous because we can read configuration files that maybe contain plain text password. We can read, for example, the etc passwd file. So another critical file, right? Because let's say that we are root and I want to read here the etc shadow. I want to read the etc shadow, not etc passwd, sorry, etc shadow. Now this file actually, if I decode it now, this file contains the hash of the various users. So in this case, the only hash that is actually present is the hash of the Ubuntu user. Everyone else is not there because we did not set the password for those accounts, but still, the etc shadow file could be a very dangerous file to lose, especially if the users have weak passwords that can easily be cracked. So that's the idea. So with base64, we can just read essentially any file. So this is it. I have some reference here. I'm gonna put in the description into the functioning of sudo, into the GTFObins. So this is like a critical resource that you should use. This covers everything for this video. I hope you got the idea of what SUID Exploitation is all about. It is all about understanding how sudo was configured in your machine and to exploit the misconfiguration. Understanding, okay, I have pip program, I can use it in this way to obtain privilege escalation. To this end, once again, I cannot recommend enough this GTFObins because it contains how you should exploit each binary assuming you have sudo capability over that binary. So this should become your best friend when doing privilege escalation in Linux. So this is it for this video. I hope it was enjoyable. I hope it was interesting. If it was so, please leave some feedback. Tell me what you think about it. Tell me what I've missed or what you want me to cover in the future, and to the next video. Hi everyone and welcome to this new video in which I continue my Linux privilege escalation series. So in this video we will analyze a specific technique called wildcard expansion exploitation. So it has to do with the shell wildcards. We'll analyze what they are, what is this feature of the shell with some practical example, and then I will showcase 3 specific exploitation scenario, one with the command tar, the second with the command find, and the third with the command rsync. The idea is that with these 3 scenarios, you should understand this technique, how to exploit it, when you can exploit it, and this can be helpful when doing Linux privilege escalation. As always, I ask you to give me some feedback with respect to the video, if you like it, or also if you did not like it, because I want to make the best educational content on hacking out there, so I need your feedback. Share with like-minded people, don't forget to subscribe, and that's it. Enjoy the video. So let's start off with a general discussion about shell wildcards, what they are and why they are useful. Now, when using a shell, such as sh or also bash is the same, it is often useful to use wildcard characters to perform complex actions. Now, specifically in the Linux environment, we have the following wildcard characters. Now, these characters are called wildcards because they can be substituted for other characters. They can sort of act like complex textual patterns. For example, to give a specific example, consider the question mark. This question mark can represent any single character. What does it mean? It means, for example, that if I have a string like test and then question mark, the shell is able to expand this into test and then another character. It could be 1, it could be 2, it could be 3, and so on and so forth. So the idea is that this wildcard character is expanded depending, of course, on the context. And here we can already bring up the examples. So consider this. Let's go into the tmp directory. Actually, let's create a tmp directory here in content. And let's create a bunch of directories. So I can do make dir, test1, test2, test3, test4, and test5. So now we have 5 directories, right? Perfect. I can do ls, and here they are, my 5 directories. Now, if I do the command ls test1, I'm gonna list out all the files present in the test1 directory. I do this, and notice I get nothing back. Why? Because the test1 directory is actually empty. So we can create a file, we call it file1, and we put it into test1 directory. So with this, touch test1/file1. Now I do it again, and notice I get back the single file1. Perfect. Of course, if I do ls test2, I get nothing back. We can create another file. We can call it test2 file2, so we can write different files. Now, when I do ls test wildcard with this question mark, notice what is going to happen in the shell. So notice this output. It's going to give me the files of test1, the files of test2, the files of test3, the files of test4, and the files of test5. So what happened exactly? The idea is that before the command was even executed, so before control was passed to the operating system, the shell performed a substitution of text. So specifically, what the shell actually executed is not this command that we typed out, but rather it is this other command. It is ls of test1, test2, test3, test4, test5. So if I execute this other command, see what happens. I get essentially the same output. Look, this output first is exactly the same as this output later. Why? Because this is the essence of wildcard substitution. So we take this pattern of text and the shell expands it to all possibilities explicitly, and then this is the command that is executed by the operating system. So before actually executing the command, the shell performs a substitution. So it transforms what we see to obtain the final command that is then executed. Of course, the ls command, the ls utility, is built in to make sure that if it receives multiple directories as the command arguments, it will act as follows. It will print out all the contents of those directories. Now, this is the essence of wildcard expansion. So as I said, we have, for example, the first example that we saw is the question mark. We have another really powerful, which is the asterisk, and this can represent any number of characters, including 0 or 0 or more characters. So not only one. The question mark was just a placeholder for a single character. The wildcard is a placeholder for arbitrarily many characters. So this is really important. Now, these characters are also called globbing patterns. This is not really that important to know, but just so you know, it could be useful. So we also have square brackets, curly brackets, we have the backlash to escape a wildcard. So for example, if you want to ls directly the question mark, we have to do ls \question mark. In this way, if for example I have test question mark here, actually if I have make dir test question mark this, is gonna create with the normal question mark, the escaped question mark, instead of executing the globbing pattern, the wildcard expansion. So that's the idea. Then we have the range, which is specified by the square brackets. The curly brackets are used to separate commands. So to give a proper example of these curly brackets in usage, so let's say that we have two different files. So we have test1.txt, test2.png, and test3.jpg. So we have three different file extensions, txt, png, and jpg. So how do we do this? So what we want to do is, for example, we want to ls all the files that have either the png or the jpg extension. So we can do this as follows. And notice we do not get the txt extension. If we instead did just wildcard so like for example like this, we're gonna, I think this is gonna create an error because it's gonna say no such file or directory cannot access this. But if we do this, of course we get everything back. So the idea is that we're gonna do 3 more, actually like this. So this is another wildcard. So we get anything, then a dot, and then 3 question mark, which represents any file extension that has a length of 3. Or we can do this, for example. This also works to extract all the files that have an extension. If you only want txt, we can do this, ls wildcard.txt. And the one before that I showed was, okay, let's extract only those which are either png or jpg. So with the curly braces, I think it was without space. It's important here, notice here, no space, otherwise it's gonna complain. So this is really important. So that's the basic idea of shell wildcards, and this is the functionality. Now here I give some example, but I already discussed them, so we can skip this because we've already done that. Now, when it comes to exploitation, let us try to understand why is this expansion behavior dangerous? I mean, where could it be dangerous and why could it be dangerous? Well, let's try to reason about it before actually seeing it some exploitation. So if we have a command, right, if we have any command, and then we have a wildcard here, any sort of wildcard character, I mean, we don't care which, just in general, wildchar. So what happens? The idea is that the command that is actually executed is not going to be this one, right? We know it's going to be something else that will take care, that will be sort of like constructed by taking into account another piece of information. For example, wildcard typically acts within the file system. So the rest of this command is going to be constructed by information from the file system, So here comes the dangerous part. What if an attacker cannot modify this command directly, cannot write on the script that executes this command? However, this command has a wildcard that reads from some directory, and the attacker has control over that directory. Then he can introduce malicious files with specific file names so that when the wildcard is expanded, we're going to change the command that is executed. And this is the whole idea behind wildcard expansion. The idea is that we have a command that uses a wildcard, a shell, a wildcard expansion, so like a shell wildcard, and we have control over a directory in the file system, and the command uses the wildcard in that particular directory file system. So to make it more clear, because I can understand this kind of discussion can be theoretic, so let's make it clear. So to this end, I've brought 3 different scenarios. Now consider a cron job, or any script actually, that uses wildcard expansion within one of its commands. If the wildcard is not properly used, the wildcard expansion done by the shell can introduce security vulnerabilities. So let's get our hands dirty. Let's see this example with the command tar. Now tar is used to create archives of files, so it has a pretty basic syntax. So for example, let's say that I want to create, I'm gonna remove all these directories here. I have just these 3 files. So yes. I have just these 3 files and I want to create an archive out of those files. So I do tar, I do c to create, wf to make it verbose, and then I'm gonna say, look, any, like all files here, and I'm gonna name this archive test.tar. So I'm gonna do like this is the command, and then I have this test.tar, and this test.tar contains those 3 files. So perfect. This is the basic functionality of the command. Now, this is the setup. So we're gonna have 3 files, and we're gonna name those files in specific ways. So I can remove, once again, all the files from previously. I can remove everything. So I have an empty directory here down in the shell. That's good, nothing. So I'm going to do an echo in file 1, an echo in file 2, and an echo in file 3. So all this command, what it's going to do essentially is going to create 3 different files with the following command, with the following contents, test1, test2, and test3. Perfect. Now, suppose that a cron job is configured to execute this command, this second tar here, tar-cf tmp scenario1.tar wildcard. So we can execute this command essentially. We can do like this. So we can call it scenario1.tar, that's good. And if we put the v flag here, it's gonna print out all the names of the files that gets compressed into the archive. So we have these 3 files, file 1, file 2, file 3, and we have created this archive in tmp scenario 1. So this is the archive we have just created. Now, how can we exploit this? Well, let's go back to the drawing board for a moment. And let's try to understand how it could possibly be exploited. So the command that is executed is this one. But then what actually happens is that the actual command that is executed is not this one, right? Because this one has a wildcard character. So I have to expand it. Okay, how do I expand it? I take all the files in a directory and I append them like this. So this is actually the command that is executed. So this is the command. Now, how can we abuse the scenario? Well, consider this. The command tar can be used with different flags. So I can say flag 1, flag 2, flag 3 with different options. So the idea will be to encode a malicious flag within the file name in the directory. So the file name is going to be malicious. And then once the wildcard expansion is being executed, we're going to introduce a malicious flag. So how do we do this specifically? Well, first we're going to create sort of like a script. So let's create this script. We're going to do temp scenario1 hacked. So this script, we're going to execute it here actually. Shell.sh. So this script shell.sh does one simple thing. It creates a file named hacked into the directory tmp scenario1. And notice that this time, this directory right now actually does not even exist. So actually we can change the script to make sure that it creates this flag into tmp. So I think it's better. So let's see if this file exists. It does not exist. There is no such file or directory, to make sure I'm not lying to you. So this script simply creates a file. Now the beauty of the attack is this actually. So we're gonna create 2 files with this echo, empty string, pipe into this thing, redirect. Actually, this is not a pipe, this is an output redirect into this file. Notice what happens here. I've just created a file with this particular file name, which is --checkpoint-action equal exec equal sh space shell.sh. And then I'm going to create another file, and this other file is going to be called like this. It's going to be called checkpoint equal 1, --checkpoint equal 1. Now, let's go back to the drawing board. So once this wildcard expansion is actually expanded, what do we get? We get the following thing. So we're gonna take all of this, and thinking about it in bash, it's sort of like we've just called this command. And boom, we have the way to obtain code execution, because with this setup, tar will actually execute this action, will do this particular exec, which will trigger the shell.sh script. So let's see in action. I'm just gonna do this. I'm not gonna execute any code. I'm just gonna use tar, and I'm gonna use the wildcard. So before, let's see if fact exists. It does not, right? Then I execute this thing, and then I check if fact exists, and notice now it exists. It got created. What does it mean? It means that we actually got remote code execution. Why? Once again, let's review it. Because we were able to write into this directory, to create new files into this directory, and so we created a file with a malicious file name. This malicious file name represents a flag used by tar to trigger code execution. So like we can have maybe RC, if we can do this remotely, or if we can do this locally, we can have privilege escalation if the script is running as root. For example, a root cron job could be. So the basic idea of this kind of technique is we introduce malicious files. These files have specific names which have to do with the program we are trying to exploit. For example, specific flags of the tar command. The wildcard expansion is done by the shell, and the actual command that is executed is a malicious command because it contains malicious flags, for example, malicious arguments, options, and things of the sort. So this first command, this first example with tar should give you actually a practical idea on how this works and should make the previous theoretical discussion more clear. We just create malicious files with no content. Here the malicious part is the file name, it is not the content. And of course in this case the shell.sh creates just a file, but you can imagine that for other purposes, here you can put a reverse shell, here you can put exfiltration of data, you can just use your imagination to understand what you want to put it here. The dangerous thing is that anytime this is executed, this in turn is executed, our malicious code. So that was our first scenario using tar. Now we have a second scenario using find. Now suppose you have this command. Now it's find. So it's find on the current directory. What's this find gonna do? Well, this find essentially is gonna match all the elements that are not this extension, so JPG, PNG or GIF, which means all the files that are not these types of images. Now, on the file that it match, which are all those that are not that do not have this extension, it's going to execute a bash command. So it's going to do rm-f. So it's going to remove that command. It's going to remove that file name. So let's try to play around with this to have an idea. So let's say that we have a bunch of different files. Here I can delete everything. I don't care. So let's say that I have touch test1.txt, touch test2.png, touch test3.jpg, touch test4.pdf, and touch test5.gif. So we have these 5 files. I execute the commands, the command as previously said, and notice here I have just the PNG, JPG, and GIF. The TXT and PDF were deleted. Now, what's the problem here? The problem here actually is these curly braces, because these curly braces will use the file name to create this command, right? So we can exploit this. I mean, this technically is not, now that I'm thinking about it, a wildcard expansion per se. However, it sort of is still an expansion attack based on file names. This is why it's important to mention. Here the wildcards are used to match the regex, but here is actually the problem, because it's going to take the file name and it's going to use the file name to create the command that will then be executed. So, what happens, for example, if we use this command, touch file.exe, echo, base, and bash? So, let's consider this payload. What does this payload do? This payload decodes a base64 encoded string and then it passes that into bash. So what is this string? Well, this string here, I'm gonna put it in another buffer, I'm gonna use Emacs to decode it. base64 decode region. It's called touch-tmp hacked. So once again, this string is the command to create a file in the tmp directory. So once it decoded it, it actually passes into bash to execute it. So let's make sure that we do not have the act. So I'm gonna remove the act that we previously created to make sure that we have removed it. Then we can create this file, this touch.exe. Notice that the way we're going to create the file doesn't really matter the extension or the name before. What really matters here is that the extension will trigger the deletion. So it cannot be JPG, PNG or GIF, because otherwise we're going to ignore those files. We will just execute the command on the files that do not have these extensions. So the structure of this payload is, okay, this is the file name, this is the semicolon. In bash, the semicolon is used to separate commands so that both are executed. So notice this, I do an ls, semicolon whoami. First I do an ls, and then I do an whoami, so which gives me Leo. So when this command is actually executed, the command here will be expanded as follows. So will be expanded as follows. So we have this, and then we substitute into these curly braces the actual name of the file, which is this one. So the command that is executed is, you remove the file for sure, but then you execute this other thing, which is an echo of the malicious base64 encoded string into bash. So let's try this in practice, right? Because it's fun. So once again, notice this. So here is the command. So I'm gonna check if fact exists. It does not exist. I'm gonna execute this command, this user find, and now notice the file actually still exists. If I do /tmp hacked, it's gonna give me /tmp/hacked. It means that we actually got code execution, we actually executed code. If this was a cron job running as root, if this was a malicious script, if this was a script that was run by other users, we could have code execution with respect to those users. So this can be dangerous. And once again, notice the pattern of exploitation. The idea is always the same. We create a malicious file where the malicious part is not the content, but rather the name. This is the idea of these kinds of attack. And this is the second scenario with find. So anytime you find with sort of exec bash, with these kind of things, they are dangerous because they use file names to create the command that is executed. Now notice how this is similar to an injection attack. This is actually an injection attack because we are injecting data into the command. Now when I did my web exploitation series, which is available on my channel, I talk a lot about SQL injection, and I made a video entirely on SQL injection. And in that video, I discussed how SQL injection were all about the injecting of SQL characters into the query by the user input. Here, the idea is exactly the same. This is an injection of what? Of a bash command, of a shell command, so it is more proper to call it a command injection using the semantic of the command find, because the command find creates a command and here it expands these curly braces with the name of the file. So if we, in the name of the file, we put a malicious string, this is going to create a malicious command. So that's the idea. And this is a general technique that you can apply to many different scenarios. Just be careful how file names are used. Now for this third and final example, I brought rsync. Now rsync is a tool used to make backups. And the cool thing about rsync is that it works even when we have remote servers. So when you are doing a backup from one server, so let's say server 1 to server 2, rsync works by, for example, taking files from server 1 and giving them to server 2. And it allows for example, SSH connection. So it uses the SSH tunnel, the SSH connection, to transfer file for backup purposes. So this is actually a really common command to find, so you have to be careful in how you use it. So how do we do the setup here? We're going to use a Docker image. This Docker image will represent the container over which we are doing this file exchange. So here I have all the commands to build the container and stuff. This is the image, it's really simple. We're just installing SSH. So what we do, we build it, it's already built, we run it, we connect with SSH. And actually one thing that we have to do here, the password is password, literally. One thing we have to do is we have to install rsync within the container. So we can do apt install rsync to install it within the container. Quick install, we can actually, okay, this is like an open shell, that's good. Then we open another shell here. So notice we have the shell with rsync and the shell down here. Now, how do we use it? Go into the tmp directory here and let's create a bunch of files. So let's create, please subscribe into file1.txt. Please leave some feedback into file2.txt. And please share the video with file3.txt. So with these 3 different files, very interesting files, I would say. So how do we do the backup? We do it with rsync. So we do rsync -a -e ssh-p. Then we put the, notice here the wildcard, wildcard.txt, and then we put root at localhost tmp. So this is gonna connect to the container within the specific port 2222, and it's gonna put all the stuff in this folder into the tmp folder of the container. So we execute this command. Actually, notice here, if I do ls tmp, there's nothing, right? Here I put password, it did the transfer, and now I do ls tmp, and notice I get these 3 files with the correct content. So notice here, file1.txt, please subscribe. Perfect. Now, how do we exploit this? Once again, the idea is find the right file name. So like find the flag that can be used to trigger code execution. So in this case, let's create this touch.tmp act once again into the shell.txt file. So by the way, let's remove the act from tmp, the previous one. Let's create this particular file. So it's called -e sh shell.txt. This is all there is to it actually, because the next time we will execute a command, let's put this, let's do this. So here it says there is an error, okay, but actually if I check the tmp, it has created the tmp/act file. So let's review. We remove the tmp act, so it's no longer there, right? We do not see it. There's no file like that. We execute the malicious file, the malicious command rsync, which by itself is not malicious. It's not malicious. It's just that it uses this wildcard in a wrong way. We execute this. It gives us some error, so we are not really able to like transfer all the files. However, in doing so, we actually created the act. Why is this the case? This is the case because once again, let's review our theory. This command actually uses wildcard expansion. So we have to take into account all the files in this directory. So we're gonna have this thing. So we're gonna have this thing essentially, and this thing as this /e sh shell.txt. And this is the option that makes the code execution happen. Also notice that in this scenario, the code execution happens, yes, but not within the container. This is important to know. Like if I do tmp here, I do not have the act file within the container. It happens within the initial server that does the rsync, not with the remote container. So that's the idea. The rsync was a bit more complex. I hope it was clear. Anyways, the general pattern of exploitation is you find the command that uses wildcard or that has common substitution, like the find one, that is based on the name of the files. And then on those commands, you find the interesting flags like checkpoint action, checkpoint, etc. And then you create specific file names, so specific files with malicious file names, and then the attack is complete. So that's the general idea of this wildcard expansion exploitation. The general idea is that we have a command that is constructed by taking into account file system elements which the attacker can control. You control the file system elements, you control the final command that is actually executed, and you can introduce malicious options and arguments, and maybe obtain code execution. So I hope the video was fun, I hope it was clear to see. If you have any feedback, please leave it in a comment. As I said, please support this channel, help me grow, subscribe, share with like-minded people, and see ya to the next video. Hi everyone and welcome to this new video in which I continue my Linux privilege escalation series. In this episode in particular, we will talk about Linux reverse shells. So, how to spawn reverse shells in Linux, some basic payloads, some basic theory on the difference between reverse shell and binary shell. So, this is an important episode for the Linux privilege escalation series because when you get onto your target, when you get some kind of remote code execution into your machine, the first thing you want to do to establish a proper foothold is to spawn a reverse shell, and then later on you can do actual privilege escalation. So it is a really important step. I hope the video is enjoyable. If you have any feedback, please leave it in the comments. Let me know what you think of it. And that's it. Enjoy the video. So first things first, in terms of the setup we will use, we'll have a Docker setup. So we have a Docker file, a simple Docker file with really like just some basic commands that I install into the machine with some basic user. We don't really care much about this Docker setup. What we care about is just building the Docker file. So with docker build/t, actually I need to become root. So I build the Docker file, it is already built actually, because I've already done this. Then I run the Docker, I'm running the Docker, and now I can execute a shell in it. So a basic bin bash shell. So now we are inside this Docker, so we are not currently in a ROS, we are inside the Docker, and all the payloads that I will discuss will allow us to obtain a reverse shell within this Docker. Of course, this is simulating a scenario where we have a client, like an attacker machine, an attacker box. The attacker box has managed somehow to obtain code execution into a remote server, maybe through RCE, remote code execution, and the next step after you obtain RCE to properly enumerate and do privilege escalation and all of those stuff is to establish a reverse shell. So you want to establish a reverse shell between your attacker machine and the server. So we will see various methodologies, various payloads that allow us to do exactly this step. So we'll consider the Docker as if it's the server and our host machine as if it's the client. So that's the idea. Now to start off, we can discuss the difference between reverse shell and bind shell. I've already discussed this difference in the video on Windows privilege escalation, but since this is a distinct series, it talks about Linux, I'm gonna repeat it again so that if you just follow the Linux privilege escalation, you will have all the required knowledge. This is because regardless of the system you're in, if you're in Linux or Windows, the idea of a reverse shell is the same, and the difference between reverse shell and binary shell is also the same. So what's the idea here? When we obtain code execution onto a vulnerable system, the first thing we have to do is to spawn a shell. Now, why is this the case? Well, because typically, the way we obtain code execution through a system can be very complex. For example, if you are exploiting a web application using the HTTP protocol, in order to obtain our remote code execution, we might have to send a lot of different HTTP requests, and the flow of those requests can be complex, the information flow, the data flow. So it might not be easy to just repeat it all the time to execute new commands. So what's the idea? Well, we obtain first remote code execution and then we use that remote code execution to obtain a proper shell, a proper remote shell, of course. Remote because we are not obtaining a shell in the system we are using. For example, here I am in my system and I have a normal shell here in the background, here in the beneath buffer. This is a shell, I can do commands, but these commands execute within my local system. If we want to attack a server, we want to obtain the same idea, the same shell, but in the remote server. So it has to be a remote shell. So the idea is we use the remote code execution to trigger the remote shell, and once we have the remote shell, we will be able to execute any command we want directly through an interactive remote shell. So that's the idea. Now, to actually obtain this remote shell, there are two different techniques. One is called the bind shell and the other is called the reverse shell. So what's exactly the difference between bind shell and reverse shell? In the bind shell scenario, the attacker forces the vulnerable compromised server to open a port and to listen for incoming connection. So the compromised system acts as a server while the attacker machine acts as a client. So in this case, the compromised system opens a port and we connect to that port. This is the idea of the bind shell. Because of course to do this connection we need to do typically a TCP handshake, so we need to establish a TCP channel between the two endpoints, and during a TCP channel installation, like when we establish it essentially, one of the components has to be the server listening for incoming connection. So in the bind shell scenario, this component is the remote server, the compromised system, the system we want to attack. This of course is different with respect to reverse shell. In a reverse shell scenario, who actually listen is not the compromised system, the compromised server, but rather it is the attacker machine. So we have the attacker that listen on a given port and on a given IP address. So it listens on a given TCP IP endpoint in the internet that is publicly accessible from all the servers in the internet. And then the compromised system actually connects back to our attacker machine. So the big difference here is that now who's doing the listening is not anymore the compromised system, but rather it is our attacker machine. So the attacker machine now acts as a server with a public IP on a public port on which it listens for incoming connection, while the compromised system acts as a client. And this brings us to the simple reason why most of the times reverse shells are better than bind shells. So, since using reverse shell, the connection is outbound, which means that the compromised server simply makes an outbound connection towards the public internet, it is much harder to recognize that as a malicious threat, as something that is malicious, that is weird, that has to be examined more thoroughly. I mean, it is typically okay to connect to the public internet, while it is much more dangerous to open a port in your network infrastructure to listen for incoming connections. I mean, I'm not saying that outbound connections are not also monitored for sure. You also, if you have, for example, a company network, you might be cut from accessing directly the public internet, but assuming that your laptop, that your computer can access the public internet on its own, then you will have a lot of outbound connections, while you will not have many inbound connections, that is connection in which you are the server, in which you open a specific port. So in both cases, I mean, the idea of having a remote shell is the same. We want to have remote control over a shell process, but the way in which we do it is like the party, the entity who listens and the entity who connects to the listener changes, and this is why typically reverse shells are better. Another reason that also has to do with networking, it's the position in the networking, is for example, suppose that you have a NAT system. So in a NAT system, you have your LAN with your PC, so PC1, then here you have your router, so this is like a router, and here you have the public internet, right? So in a NAT scenario, in the public internet, you do not actually go with your specific IP. Rather, you go with the public IP of the router. So it means that when someone wants to connect to your port here, it actually has to go through the router, and by itself, by default, in most configuration, this connection does not happen directly. If I open an endpoint with IPM port, and from the public internet I connect to that specific port and the public IP of the router, of course the router will not know that this package has to be actually delivered to this particular computer, because there could be other computer listening. So there has to be a specific router configuration which allows for inbound traffic and which allows for the routing of said traffic. Because the router has to understand, like, okay, if you listen on port 444, you have to route it to PC1. But if you listen to port 555, you have to route it to PC2. And all of this to say that when it comes to inbound connection, it is much more difficult to get it right, especially when you're doing like a penetration test, when you're checking out the security of a system, because it's just much more difficult. So for all these reasons, a reverse shell is always better because you just do an outbound connection. Although, as I said, this does not mean that the connection is not monitored. If you have a firewall, if you have a web application firewall, or just any firewall that looks at the packages, all your payloads might be intercepted and analyzed. So you might want to use a reverse shell that uses cryptography to hide, to encrypt the payloads, but that's for another story, that's for another day. So all of this to say, reverse shells are always better. Now, before actually showing how to do this, the actual payloads to spawn a shell, so we have our lab here. Here we have our machine within the Docker. So this is within the Docker. And then down here, I have my shell within the attacker box. So I have this setup. And here I can just bring back the nodes. So I will actually show how to do file transfer between your attacker machine and your victim machine. Now, why is this useful to know? Because sometimes to spawn a reverse shell, you want to approach it in multiple stages, where in the first stage, you write a file to the server, and in the second stage, you execute that file. So if you have a remote code execution, it can happen that maybe that remote code execution is not too stable, so you don't want to do it in just one command, you want to split it out. And so it might be useful to know how to transfer commands from the victim to the machine. So to transfer commands, there are two things you have to do. First, on your attacker machine, you have to start a local HTTP server that is also, of course, accessible from the victim machine, which means that if you are connected to the victim using the internet, this web server has to be publicly accessible, otherwise it doesn't work. In our case, what we can do is, let's create here a folder called www, and in this folder, I'm gonna write a bunch of stuff. I'm gonna write touch test.txt, and in this test.txt, I'm gonna write, so let's go down here, please subscribe guys. So I write this file, then I open a local web server, so I say Python 3 -m to access the modules of Python 3, and then I say http.server, and then the port I want to listen on, which is 1337. So I open the server, and now I'm listening to the server. Now, of course, I go back to the victim machine. Now I am on the victim here, and I'm assuming that I have my remote code execution. So I'm able to execute commands within this server. Now I'm doing it directly with a shell, so I already have a shell, but assume that this shell is just simulating my ability to send remote commands to the server. So for example, one command I can use is curl. Because I have curl installed, I can use curl, and I can use curl specifically to connect to my server in order to get the data. So let's say that I do curl, and then here I have to put HTTP and the IP address of the attacker machine where the web server is listening on. How do I get this IP? In my case, I can just assume that since I am on Docker, I can just grab all the interfaces and grab for Docker. And notice here what do I get? I get this IP address, which is the IP address of the Docker interface. So I'm just gonna do this. I have to put the port, of course, 1337. And let's say here I do test. So I'm trying to access the resource test on my web server. I do this, and notice what happens here. Here I get a not found, a 404 file not found error in HTML, thanks to the command line curl, and here in the log I get, look, someone has tried to obtain the /test file, but we do not have it, so I return a 404. So what's happening here essentially? The idea is that I'm using curl, which is a command line utility to perform HTTP queries. And the idea is that we want to use the HTTP protocol to transfer files between the victim and the attacker machine. Because HTTP is one of the most used protocols, it's very useful. There are a lot of command line tools for it that are very simple to use. And the way I use it is simple. I just say curl, I put the URL which specifies the resources. This is attack control. And then I can either like let it print on the standard output, or I can just redirect this thing into a file. So I can say like this, redirect into test.html. So I do this transfer, and then in test.html I have the response, which of course in this case it does not exist because I have no file in this folder that matches the test name. It's actually called test.txt. So we make another query, and this time we're going to do test.txt, and we're actually going into test.txt file. And notice this. Now in the log, it does not say anymore 404 not found. Rather, it says 200, which is the status code HTTP that says, okay, all good, you have your file. So the web server running on my attacker machine has actually correctly transferred the file over to the victim machine. And now, if we check the files here, notice this, test.txt has 18 bytes. If I get out the content, I have my please subscribe. So it actually works. So that's the idea with file transfer. Of course, you can do it with multiple commands. You can use curl, which is a very famous command line. You can use wget, which is another command. And with wget is similar. You just do wget, then you put the URL, and then you put big O, like dash. So you do wget. I think here is dash O, like minor O. Let's see if like this. Let's remove the test.txt to make sure that we actually download it properly. Test.txt. Okay, no, it's not minor. I think it's capital O. So dash capital O. Okay, that means this makes sense. And notice that now I've actually downloaded the file. So I can go into TMP. I can do it again. Here I have now my file with 18 bytes correctly. I get the output, and I have please subscribe. So here I just show two simple commands, curl and wget. Of course, the command you use here depends on the binaries that already exist on the victim machine, on the target, on the server you're trying to attack. Because if you go into a server and you already have curl there, you can just use it. You can just use it to do file transfer. If you have wget there, you can just use wget. Finally, here I show Perl, like if you have Perl, you can do this. Because sometimes it has happened to me that in the machine I was in, I did not have curl, I did not have wget, but I did have Perl. So it's a very similar way. You just have to change here with the attacker payload, with the IP address of your attacker. So the IP address we said was, let's remember here which one was it. It was this one with port 1327 test.txt. And then we can go here and we can just change it up here. It's the URL. The URL specifies the resource we are interested in. Then we take this command. We go here. Let's say which Perl to make sure that, look, Perl is actually installed. Let's check if we can use this payload. So notice this. Once again, we obtain a different request here. And actually, no, this time I use it with in my own host. So look at this. I use it in my own host, so it doesn't make sense. Let's do it again. But this time, I'm going to make it on the actual Docker. So here I'm on the Docker. I do this Perl. Notice I get 3 or 4. Okay, this is interesting. And what if... Okay, please subscribe. So I get 3 or 4, and then I get please subscribe. So I get the actual file. Actually, let's see if I delete it, if it actually downloads it. Okay, it actually downloads it properly. That's good. So this is another command that you can use anytime you're on a system. Perl is typically installed as a binary. Otherwise, you have curl and wget. Of course, I suggest the first two. This is just in case if you don't have neither curl nor wget. And this covers the file transfer commands. So suppose that you are able to transfer files into the remote machine. How do we actually spawn a reverse shell? So in the video I made on Windows, I showed how to spawn a reverse shell using the command line cmd.exe and the PowerShell. So different payloads for different languages. Well, the idea is that as long as you have an interpreter of commands, you can have different reverse shell payloads. Because at the end of the day, anytime you have an interpreter, like a Bash interpreter, or a Python interpreter, or a Perl interpreter, or a PHP interpreter, or a Ruby interpreter, you can also have compiled languages, like compile like C, C#, and things of the sort. Anytime you have a toolchain which allows you to write and execute code, then you have a different reverse shell payload. What's important here to understand is that these tools have to be installed on the server you're trying to attack, you're trying to test. Because if you don't have those tools, you cannot spawn a reverse shell. The idea of a reverse shell is you're gonna listen with your attacker using netcat, this is your attacker, and then using your victim, in the victim, you're gonna trigger some code using, for example, bash, or you can use Python, or you can use other tools to attack to your attacker, to connect to your attacker. And the way you connect depends on the language you choose to use, essentially. So let's try, for example, this first bash payload. So the first payload we use is this one, this bash-c, and then in the string we have bash-e, then all of these other commands. Now, if you're interested in understanding the exact working of this command, I have a video linked in the description made by 0xdf. It's very fascinating because it goes into in-depth detail explaining this single payload. I'll just leave you to that video because he made it really, really well. So if you're interested in like knowing internally, okay, what are all those things, it can be really helpful to learn how Linux works. For our purposes, we're just doing privilege escalation, so we will just use it without understanding it in a black box way. Because remember, sometimes it's useful to be able to abstract, so you just use it, but at the same time, never forget to take your time and understand how these black boxes really work. And maybe in the future, I can make something along those lines of explaining in depth this kind of command. But there's already a video about that, so I don't really think I need. So how does it work? How do we use it? Well, we take this payload, very easy, very easy. Now, at this point, we can remove the web server. So we can totally remove the web server. We can just focus on the attacker machine and the victim machine. So we have attacker machine and victim machine. So in the attacker machine, we're going to use netcat here, NC, this is called netcat. It is a program to interact with TCP channels to listen on a particular port. And I'm going to use the 4321 port. And here these flags are L, V, and P. In particular, L is for listening, P for specifying the port to listen on, and I think V is for verbose, and N, currently I don't remember, I think it's for not translating IP addresses or something like that. Anyways, we're just gonna go do this command. Notice that I press OK, so I sent the command on my attacker machine, the one down here. So this one is my attacker machine, and now in this up one, which is the victim machine, I'm gonna execute the payload. Now, what's important to understand about this payload, to truly understand it, is that this payload contains some structure that remains the same, and then is parameterized by two different things, which is the IP address of our attacker machine and the port on which the attacker machine is listening on. So the IP address, this one, is the IP address of this machine, and the port, as you can see, is the port that I'm listening on. So once I do this, notice what happens. I execute this command on the victim target, and then look at this, connection from a certain IP address, and here what do I have? I have a bash shell, and here I can say who am I can say hostname, I can go into the root directory, and I can execute my commands. And this would work even if I was exposed to the public internet, assuming, of course, that there is no problem with network latency, delay, and stuff like that. So the idea is that I listen on my attacker machine, I execute the payload on the victim machine. When I execute this payload, I trigger the reverse shell, because at this point, the victim machine connects back to my attacker machine, so he is doing outbound traffic, and I get control over a bash process that is running on the victim. So here on the victim, a bash process is running, and now I have remote control over it. So that's the idea, and it's gonna work with all the different payloads. So the only thing that changes here, again, like for example, stop this, and I'm gonna stop it like this, and I can get back to the setup as before. So the only thing that changes between these different payloads is the program we use to trigger the reverse shell. But notice that all these programs, in their different ways, each one with its own syntax, they essentially do the same thing. They start a process, the bash shell or the sh shell. So they start a shell process then they connect to our endpoints using a TCP connection, and then they redirect the standard output of the shell process into the TCP socket. So essentially, the way it works, if you just analyze all this code, is you have a TCP connection. Of course, all of these different programs, they deal with TCP connection differently. For example, in Bash, you have this reader /dev/TCP. This is how you connect. This is like a device driver of the Linux kernel. In Python, you have the system call socket.socket. In Perl, you have the socket. In PHP, you have the fsock open. In Ruby, you have the TCP socket open. So you always deal with a TCP socket. The next step is to start a shell process. And in this case, for example, this is the bash.i. This is how you start. Or here it's essentially the subprocess call bin.sh, or here is the exec bin.sh and things of the sort. And then you redirect the output into the socket, into the TCP socket. So the idea is that this can happen before or after you execute the program, depending on the programming language. So for example, here you do the execution at the same time, essentially in Ruby. So the idea is that after you have executed the program, or right before executing a program, you want to connect the standard output of the program to the TCP socket. So at this point, you have essentially exposed your process to the TCP socket, which is controlled by attacker. Therefore, you have exposed your process to the attacker. So that's the idea. So this was with Bash. Then there is this other payload with Python. So we can try it the same way. We listen with the attacker machine. We paste this. Just make sure that the IP and the port is the correct one depending on your attacker box. And boom, we have a connection. Now notice that this time we don't have a full shell. We just have an SH shell, because here we're just running SH, which is a bit less powerful than Bash. And to actually upgrade to a full TTY, we can actually use this command, which is Python 3 -c import pty pty spawn bin bash. So this command essentially transforms our semi-working shell into a full-fledged TTY, and it uses the pty.spawn bin bash. It uses a Python library. So here we are abusing the fact that this Python library exists everywhere, and it's extremely useful for these sort of things. And now, once again, we have a full working shell. We can do anything we like. We can go into a root directory. We can do stuff in there. We can get the flag. We can elevate our privileges, and so on and so forth. So for example, with respect to this Python, so this Python shell, we can analyze this as follows. So this Python 3 -c is simply to execute Python from the command line. So the real Python that we execute is this. So we import 3 libraries, the socket, the subprocess, and the OS. We create a socket, we connect to the attacker, we duplicate the standard output, standard input, standard output, and standard error to connect to the socket standard input, output, and error, and then finally we call the subprocess bin.sh. So let's say that we save this into shell.py. So we have saved this into an external file. And then, so this is our attacker. Actually, where is it? I think it's here. What about here? Okay. So we have this shell.py in our www. So let's say that we want to spawn our reverse shell in 2 different steps. So the first thing is going to be download this malicious shell.py into the remote target, and then we can execute it. So how do we do it? First, we can just start our web server in the www. So as follows, Python 3 -m http server 1337. Then within the victim machine, we do curl. Then we put our IP address 172.17.01.1337 shell.py, and we redirect to the current directory. You can also redirect to /tmp/shell so that you know exactly the full path. This is really important, because after this, you listen with netcat to a port, and you just do Python 3 tmp shell.py. It's gonna be, so there is a problem here. There is a string problem. So I wrote it wrong. I made a mistake here. Can happen. So I'm gonna, because I have a string literal that is not needed, so I remove this. And once again, I'm gonna transfer the file. I have to transfer it again, of course. And then I'm gonna execute it. tmp shell.py. And notice what do I get here? Once again, I get a reverse shell. This is a simple sh shell. To expand it, I can use the upgrade technique with import pty, pty.spawn bin bash. And now I have a full pty, so now it's a full shell that I can use however I want. So to finish off the video, the only three payloads that we need to see are the Perl, PHP, and Ruby, but essentially it works the same way. So assume that I can remove this, exit here, wherever. So let's listen to netcat. Here this is the Perl payload, like this. So I execute it, and once again I have a shell, and then I can upgrade it for sure. Then we have the PHP. I mean, they all work the same really. It's just different interpreters, different languages, but at the end of the day, what we really need is to work with the TCP channel. So we have the PHP. So of course here I have to put the right IP address. If you put the wrong one, it doesn't work. 014321. Notice once again I have a reverse shell and I can upgrade it as follows. So remember that these are all different code. They look different, but at the end of the day, they still establish a TCP channel, they call a process, and they connect the process to that TCP channel. And finally, we have the Ruby payload. So here, let me fix the IP address with 17014321. So this is the Ruby. Let's see, of course, if Ruby is installed, because maybe Ruby is not installed, but it is installed, of course. So I copy this payload, I bring it here, and I get a bad file descriptor. So I had some problem with the previous Ruby payload. Then I found this website. I think it's this one, should be this one. And this reverse shell cheat sheet, I'm gonna put it into the description of the video because it's useful. And so like refs, I'm gonna put it here. And I found this other website with Ruby. So here it's listed for every programming language, the way to obtain a reverse shell with that specific programming language. We can take the second payload. I've just changed the IP address here. And notice here, I just listen with my netcat, I paste it here, and then notice that once again, I have a reverse shell as root, because I'm executing on the container, again, I can upgrade it. Can I upgrade it? Oh, I don't think I can upgrade it apparently, so this one is not working as before. So let's see. So sometimes these reverse shell are not too stable. So I got this reverse shell. Maybe I cannot upgrade this one, but it still works enough to obtain the stuff that I need. So that's the general idea, essentially. So the general idea is that a reverse shell allows us to transform a remote code execution into a remote shell on the system we need to test out, maybe in a penetration test or stuff like that. And there are different payloads for reverse shells depending on the programming language you use. Now, they might seem really different from each other, of course. I mean, just look at this last Ruby code. But the idea is that all of these payloads, and even the one in this guide, like here there are even more languages, it's just there are a lot of different languages. Well, all of this payload, in one way or another, they do the same things. They establish a TCP channel, they start a process, a shell process, and then they connect the shell process to the TCP channel in order for you to have remote control over a shell process. So that's it for this video. If you obtain remote code execution, the first thing you should do is do file transfer, check if you have the commands to do file transfer. If you have transfer some reverse shell payload or execute it directly, for example the Python, you can try to execute it directly. If that does not work, then you can put it into a file, transfer into the machine and execute it with Python as I showed before. And then depending on the program you have on the remote machine, you can use different reverse shell payloads. So I hope it was interesting and useful. Leave some comments, leave some feedback, and subscribe to the channel, and see you to the next video. Hi everyone, and welcome to this new video in which I continue my Linux privilege escalation series. In this video in particular, I will show a specific attack called the Unshadow attack that you can do anytime you have access to the shadow file in a Linux operating system. So the shadow file contains the hashes of the user accounts in the system, and the Unshadow attack is all about getting those hashes and performing a brute force attack in order to crack those hashes. This in turn means that if you are able to successfully crack the hashes, you can get passwords for other accounts in the system. So if you get password for the root account, you are doing privilege escalation. Otherwise, if you get password for different accounts, you just do a lateral movement. But anyways, it is a useful technique to know anytime you have access to the shadow file. So this is an important technique to put into your toolset. So I hope the video is interesting and enjoyable. If you have any feedback, please leave it in the comments, subscribe to the channel, share the video with like-minded people, and that's it. You can enjoy the video. So as always, to start off, let's discuss the Docker setup. It's a simple Docker file, we can see it here. It just contains essentially the basic things with the username and some passwords. These passwords were chosen specifically to be able to be cracked, but in general, it's just a system with some tools. We don't really care about the tools, to be honest. So we can build a Docker. I've already done that, so there's no need to do it yourself. So we go into the content, we build a Docker. It's already been built, as you can see here. And then we can run the Docker with this. So we can say docker run. Now we have the Docker, and now we can just execute it a shell within the Docker. Now, anytime you are able to access the etc shadow file, which is this file, etc shadow, this is an important thing. Now, typically to access this file, you have to be root. So you can say, well, if to access this file, I need to be root, what's the point of doing this? Anyways, sometimes it happens that the permissions are misconfigured or that there is a backup of the shadow file somewhere in the system. So it can happen that you are able to grab it, that you are able to somehow obtain it. And this technique, the Unshadow attack, only works when you have these two files, the shadow and the passwd. So these two files are needed in order to perform the Unshadow attack. So what are these files for? Well, the idea here is that anytime we have to authenticate to the system, we must provide a secret for doing the authentication procedure. Consider a web server with a login form. You need to put your username and your password. This is an authenticator factor. It is proof that you are really that particular user. Now, in operating system like Linux, Windows, and also macOS and others, the idea is that within the system, we do not save the password directly. Also, this happens in databases of web server and web applications. So the idea is that you don't want to save your password in clear text. You don't want to save it directly onto the system. Instead, what you want to save is the hash of the password. It is something that you compute based on the password, but it is not the password itself. So the authentication procedure assumes that it has saved all the hashes within a file, and then to authenticate a particular user, the procedure does as follows. So to actually make sense of this procedure, we can just describe it really fast. So we have a saved HP, which is our hash of a password, and then we have the user credentials. So there's our username and password. So here I can just put chmod to remove this. So we have this thing. So the process does like this: check if username exists. So here I can just remove company mode actually. Check if username exists. If it does, compute h of password, and then check that h of p is equal to h of password. So you want to check that the hash you just computed on the new password, on the password that was just given to you by the user, is equal to the saved hash that is saved within a system file. So the idea of the shadow file is actually it is the file in the system that contains these hashes. And this file must exist. It exists both in Linux and in Windows. It's just that in Linux it's called the shadow file. In Windows it has a different name and a different location. But the idea is always the same. We save the hashes of passwords. For example, what is an hash? Well, consider for example the binary md5sum. This binary md5sum. So you can say, for example, echo hello, and then you pipe it into the program md5sum. And here you have an hash of that particular string. And the cool thing about hashes is that even if I have, for example, hello with an 0 instead of an O, and I compute the hash, so like the input is kinda similar, right? However, if you check the output is gonna be completely different. Now, there are various characteristics about hash functions. Specifically, the hash functions we use to save password are called cryptographically secure hash functions. They are crypto hash functions that have been studied by cryptography to have certain mathematical properties. We don't really care about those properties specifically in this video, we just want to show how to crack them in Linux. But the idea essentially is that they are resilient against different types of attacks. Now, specifically, MD5 sum is not considered anymore a strong hash functions, a strong cryptographic hash functions. So there are, for example, SHA-256 sum, this is a different one, or SHA-512, or this. And there are many different versions of these hash functions. There are a lot of different hash functions. The idea, however, is that these are saved within the /etc/shadow file in your distribution, and typically the only user that can read those is the root user and the shadow group. So every member of the shadow group has read access to this particular file. Now, the other file of interest is the passwd file. And if you check into our Ubuntu system, so now we are running into our container. So this is the container that we just created. So we can check etc passwd. So in the etc passwd, as you can see here, there are a lot of different metadata about the different accounts that are registered within the system. So for example, for each account, here you have the username, here you have the user ID, here I don't remember this other number, what it means, but essentially, for example, here you have the shell to use when you log in into the account. So here it's the path to the shell program that you want to execute when you do a login, an interactive login into that user. And here instead is the home directory of the user within the file system. So root as a home directory in the /root and as a shell of /bin/bash. There is a bunch of different service user, for example, www-data. This is the user we typically log in when we obtain a reverse shell within a web server, within a web application, after some kind of exploitation of a remote code execution. So that's the idea. And then we have Ubuntu, for example, is a different user. So it has UID of 1000. So this is the ID of the particular user. This is sort of like, I think, a name of the user. And then here it's the home directory of the user, /home/Ubuntu in lowercase. And once again, this is the shell process, the program that we want to execute when we want to obtain an interactive session with that user. And notice that for most of these users, actually, here we have a user-bin no login. So this means that we don't want an interactive shell when we log in into that user. Why? Because those users are not meant to be used interactively by people. Rather, they are meant to be service users. So you spawn a process and you give that process to the particular users. So like these users are just used to spawn different processes and to sort of like divide resources in order to decrease the attack surface, in order to implement a least privilege design within the system. So that's essentially the idea, so that if you compromise one account, like a www account, you're not compromising all the others. So that's a least privilege idea. I can talk about it in a later video. So the passwd, however, notice that here there are no hashes. So this file can actually be read by anyone in the system, because if you check its permission, look, anyone can read it, others can read it. So this is readable by everyone. However, the shadow file, as we saw, is not readable by anyone. And why is this the case? This is the case because the shadow file, if we check its contents, we can see that this file actually contains the hash for that particular account. So here we have the hash for the account root, or the hash for the account Ubuntu. So the Unshadow attack essentially has to do with combining the information between the passwd and the shadow file, and to crack those information with specific tools. So what's the idea here? So this is what I said essentially, passwd. And so, for example, how are these passwords being generated? This is interesting. Well, these passwords are generated with a specific version of the SHA-512 algorithm of the SHA-512 hash function, which is called SHA-512 crypt. It is a more resilient construction that is more strong against brute force. So it's not just a basic SHA-512, it's sort of like same family, but different construction, different as function. So essentially that's the idea. So how we can we generate it? We can use the OpenSSL command. Now OpenSSL is a famous open source library that implements various cryptography. It is used, for example, to provide the TLS protocol to the various services such as Nginx, the various version of the TLS protocol. So here we are talking about HTTPS, so the secure version of HTTP. And notice here, we can put the OpenSSL, here you can say Passwd, so let's go into my system now, and then we can say this -6 is for the specific type of algorithm, I believe. Let's see if I remember well. Yes, -6 is for the SHA-512 base password algorithm, and then here we have the other arguments. So let's do a note here. So we do -salt. Here we put the salt. We can write 1, 2, 3, and then the new password. So like test password, and it's gonna generate a new password. Now notice that the password does not change if I don't change anything. So the function is deterministic. It's always computes the same value. However, if I change the salt just a little bit, here the hash is completely different. And notice that in this string, in the output that we see, there is the 6 to specify the type of hash. So it's like SHA-512 crypt. Then we find the salt, 1, 2, 3. And here is 1, 2, 3, 1, 2, 4. And then we find the actual hash value computed. And these dollars are just separating values that divide the various meta information, the various metadata. So why, by the way, do we need the salt? This could be an interesting discussion. And the idea is that if we don't have the salt, an attacker can just log in, can just get access to the hashes of the user, and he would be able to quickly identify what are the hashes that sort of like have the same password, which means what are the users that have the same password. Because if I don't put a salt here, I think it's gonna do it automatically. So in this case, it does it automatically. But let's say I put the same salt. Let's say the salt is 1, it's always 1. Well, notice that the hash does not change. So here I'm always getting the same output. So if an attacker essentially knows that the salt is the same and that the hash is the same, is also able to figure out that all those 3 hashes belong to the same password. They were computed starting from the same password. And this can leak critical information. Now, don't think about this simple example with 3 passwords. Think about the real data breaches, the real databases that have thousands, hundreds of thousands of records of users. And suppose that many people use the same password, say 100 of them, thousands of them have the same password. This sort of information leak can be really advantageous for like malicious actors, so that they can just focus on brute forcing the password which is the most present in the database, so they can just compare the various hashes. They see the one that appears the most in the database, and they just crack that. And by focusing their resource on a single hash cracking, they obtain the access to many different accounts. So the idea of salt comes in right at this moment. And the idea is that, okay, let's put something that changes for every user. This is called the salt. Now, the salt is stored within the hash, but we don't really care about that. The idea is that by putting something else in the computation, because now the computation is salt plus password, even users who have the same password, their output will be different because the salt changes. So here we have salt, and then we have salt prime. The password can also be the same, but since the salt changes, these hash are gonna be different, they're not gonna be equal, so I don't really care even if I put the salt here, whatever. Now the attacker has lost any information about which are the hash that have the same password, that were computed from the same password. So that's essentially the idea. Now in practice, how do we deal with this? How do we crack these hashes? Well, to crack the hashes, we need a so-called word list typically. I mean, there are many different approaches, but one of the most simple one, we could say, is the one based on a word list. So a word list of different passwords. For example, one of the most famous word lists is the rockyou.txt word list. We can just download with this curl command. All of this will be in the description, so don't worry about that. So we can create a folder called new data. We can just curl the rockyou like this. We're taking this from GitHub. So it's going to take a while because it's a bit heavy. It's like, I believe, 100 megabytes or something of data. And this contains just a bunch of different passwords. So this is actually 50 because it's compressed. So let's uncompress it with tar. So let's uncompress it and then we check it again and we have 134 megabytes. So a bunch of different passwords. We can read the entire file. It's a bit large, but we can still read it. And I'm going to activate so long mode. So long. Okay. And as you can see here, there are a bunch of different passwords. Now, these passwords were actually taken from real data breaches that happened in the past. So these strings were actually used by various users. Carlos, Jennifer, Bubbles, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. So as you can see, these are like pretty simple passwords. And we can go to the end. Till the end, we see some weird characters, like some spaces. So like that's essentially the idea. Now, this word list contains a lot of these passwords. For example, say that we want to just extract one password with at random. We can just do the command shuffle with n1, rockyou.txt. Actually, I think it's shuff, the command shuff. And here we're gonna get one random password from the rock.txt file. So really interesting. Now, what is gonna be our approach to do this cracking? So essentially the idea is that we're gonna try all of these passwords, we're gonna compute the same hash function on all of them, and then we're gonna compare the output of the hash function with the hash saved in the shadow file. So this attack, as I said, can be done only if we have access to both the Passwd and shadow file. But what really is important is the shadow file, because the Passwd is really easy to obtain. So suppose you have access to both of these files in a specific distribution, in a specific target. So in our case, we're just gonna save them. So let's create, so I'm gonna do new data. Here I'm gonna create touch, shadow, touch, Passwd. I'm gonna remove the tar version. So I'm gonna fill those files for the shadow one. So I'm gonna do cat etc shadow. I'm gonna take all these texts and I'm gonna copy in my local file. And this is one. And then I'm gonna do the same but with the Passwd. So I open the Passwd. I'm just gonna copy this output. So with the Passwd, I copy this output. And now I have my two files of interest, the Passwd and the shadow. Now at this point, a really useful utility comes into play, which is called the Unshadow utility. And you can install it with various ways depending on your operating system. I believe that the Unshadow utility comes when you install John the Ripper. We will talk about that later on. But essentially, assume that you have this Unshadow utility. I have it here. I do which Unshadow, user bin Unshadow. And if I do Unshadow help, I see essentially it's in John, it's a John utility. So it says usage, Unshadow, password file, shadow file. And here with password file, it means the passwd file. So the way you use it is Unshadow, passwd, shadow, and then you output this into a file and you call it Unshadow. So I did this, and now if you open the Unshadow, it sort of like combine the two different information together and he put the hash taken from the shadow into the passwd in a way that fill the gaps essentially. Because in the passwd here, we do not really have the hash. Here we just have a bunch of x's, x, etc. And now though in the Unshadow file, we actually see the hash. So we actually see the hash of the users. So that's the first step. The second step is to use a password cracker. Now there are many different password crackers. The most famous ones are John the Ripper and Hashcat. They are complex tools that allow you to perform various types of attack, all based on the idea of cracking hashes. So the idea is that they can work in different ways. The way we're gonna work with it is using the rockyou.txt word list. So we install, for example, John the Ripper, and we do the command is like this: John -- format equal crypt. So this tells John the Ripper that look, the hash we want to crack is a SHA-512 crypt version. Then we pass the word list, so all the passwords that we want to try on, and then we pass the unshadowed file. So we can just do this command here. So I think it's in the other shell here. Okay, we have the new data, we have the unshadow, so we have the unshadow here, and we have the rockyou.txt, so we have everything we need. We launch the command, and in a bit, for example, is able to crack immediately the first password, which is the password for the user Ubuntu, and the password value is ABC123. Now this is the first user, of course. Now notice that in the Docker file, the second password is this LPRULZ4E, and if you actually check if it's present in the rockyou, I think we might find it, because I created them specifically. So let's do cat rockyou grep for this thing, and notice that we do get a match, which means that this thing actually exists in the rockyou.txt file. So at some point, is the tool we just launched here is gonna find also the second password for the root user. But of course, the question of how much time it takes depends on your processing power, sometimes also your GPUs, because sometimes you can just parallelize this kind of computation effort. And also it depends on how far is within the rockyou.txt word list. If it's at the end or at the beginning or in the middle, it can take also between like 10, 15, 20, 30 minutes, sometimes 1 hour. I mean, it mostly depends also on how like much processing power you have. Here I'm running with a 10-year-old PC, so it's not that fast in terms of CPU. But still, the first password, since it was among the first entries, it immediately cracked, and it's the password of Ubuntu. So essentially, this is the main idea. Now, in our system, we can just, like, let's say that we log into a different account. I mean, I'm root right now. Let's say that we log into the www data. I mean, this account is not available, so what if I do su Ubuntu? And then I do sudo su, and it asks me the password for Ubuntu. I press ABC123. And now essentially I'm in root again, but I had to authenticate to Ubuntu. So for example, I can also do passwd, current password ABC123, and now I can put a new password. So when I put a new password, of course, the hash in the shadow file is gonna change accordingly, because I have a different hash since I authenticate with a different password. So essentially, that's the main idea. Now you can either do it with John the Ripper or with Hashcat. However, when I was preparing for this video, I had some problem using Hashcat because it was like, essentially gave me this error. I'm gonna show you. I think it has to do with either my configuration or something like it's not able to read the various passwords, token length exception. I was not able to debug it, so I just used John the Ripper. If you know how to debug it, it would be cool to just write in the comments. I mean, I'm running with an Arch Linux distribution on an x86-64 thing. So I'm not sure if it's maybe the version. I mean, the Hashcat version that I'm running on is the 626. But essentially, you can also do it with Hashcat. But the thing with Hashcat is that I had this bug, so I couldn't really test it out dynamically. So this is it for this unshadow technique. It's actually pretty simple. It's all about cracking hashes. To do this technique, we must be able to read the shadow file. So suppose you have access to a Linux system, suppose you are able to read the shadow file, then you can try to crack the hashes. Sometimes this is an important step to do, at least maybe one day. Like, it depends of course on why you need to crack that hash, but it can still be a way to approach doing privilege escalation. It's not really that amazing, it's not really that fun to do, but it's an important knowledge to have in your toolkit for doing Linux privilege escalation. So this is it for this video. I hope it was interesting, it was enjoyable, I hope you got something out of it. If you did, please let me know, write in the comments, subscribe to the channel, help me grow here on YouTube, and see you to the next video. Hi everyone, and welcome to this new video in which I continue my Linux privilege escalation series. This video will be the first of a short subsection of the course in which we focus on the enumeration aspect. So, when it comes to privilege escalation, the first step before using the exploitation techniques that we already saw, the first step is actually enumeration. It is to extract the information on the remote system. Once you are able to extract information, once you have enough information, the right information, then you can use the specific exploitation technique to obtain a proper privilege escalation. So we're going to talk about system enumeration, Cronjob Enumeration, and the enumeration of capabilities in these 3 videos, of which this is the first. So in this video specifically, we will introduce the concept of enumeration, and we will ask why is enumeration so important. Then we ask ourselves, okay, suppose you are on a Linux system, because this is the Linux privilege escalation series. What should we enumerate? Then we will see how to enumerate with specific bash commands. These do not cover 100% all of the things, but are the main sources of enumeration, so the most critical and important things to know. And finally, we will talk about automated scripts, how to use them, where to find them, and things of the sort. And in the practical section, how to enumerate, where we will see some actual commands, we will perform them on an Ubuntu installation. So this is a virtual machine running Ubuntu. We will show all the different commands, how to use them, how to read and interpret the relative outputs. So I hope the video is interesting. If it is, please leave some feedback, share this video with like-minded people, subscribe to my channel to help me grow and support me, and that's it. You can now enjoy the video. So we start off with a question. Why is enumeration important? Asking the why question is really fundamental to understand. Okay, we have to learn about system enumeration, but why do we have to do this? Why do we have to spend effort and time to learn this? Well, the idea is that once you obtain a reverse shell into a Linux system, such as a Ubuntu machine, for example, the first thing you need to do is enumeration. Now, what is enumeration? Enumeration is all about gathering meaningful information regarding the system you are dealing with. So in a given system, you will have a lot of different variables, a lot of different things to consider in the picture, and enumeration is about creating the picture, is about painting the picture. A proper enumeration procedure will allow you to understand the specific configurations being deployed on the system that you are interacting with, and more importantly, what are the vulnerable aspects of the system. Why? Because everything that is deployed on a digital system, such as a Linux distribution, can be either secure or not secure. This means that once we have all the information, once we have the picture, we can start to analyze it in order to obtain the security vulnerabilities, in order to understand what are the parts of the system that potentially could be exploited, that potentially could give us a way to privilege escalation. Now, once you understand the vulnerabilities, you can then go to the next step and try to think about exploiting them. Of course, the road from vulnerability to exploit is not always simple. I would say it's really rarely simple. Most of the time it's very hard and time consuming. However, this is the only way. This is the way to go. You start from a vulnerability and then you understand how you can exploit it. So the second step, going from vulnerabilities to exploitation, we already covered some exploitation techniques in the previous videos. However, we did not talk too much about enumeration, and so this video will focus on enumeration and also the following 2 videos. So this is why enumeration is key. Enumeration is the first step to gather information. This information, of course, have to be meaningful, meaning that we don't want to just look at random information in a random order without any structure. We want to look at specific things in the system in a specific way with a specific methodologies so that we understand much faster and much better what are the vulnerabilities. So this is important. So the next question is perfect. Okay, but what do we need to enumerate? And in this question, the idea is, what is a modern operating system running a Linux distribution made of? What are the components? Because each component, each part of the system could be vulnerable. So what are the main components? First of all, we find the underlying hardware architecture. So this specifically means, for example, the CPU in usage. What kind of CPU? Sometimes there are vulnerabilities that affect directly the CPU. Now, these vulnerabilities are not really easy to exploit, but to understand a system, we must always start with what kind of processor is it running, what architecture in particular, what architecture, for example, is it an x86 or x64, is it Intel, is it ARM, Is it another architecture? So on and so forth. And then the model, the specific model that implements that architecture, like the latest Intel processor, the latest AMD processor, and so on and so forth. So all things with the hardware. Of course, our hardware enumeration will be pretty simple. We are mainly interested in the CPU architecture. And this is critical because, for example, if you want to run an exploit, you need to understand well what is the hardware architecture, because you need to compile the exploit with the appropriate version so that it runs on the CPU you are dealing with, if it's 32 or 64 and so on and so forth. Then, going forward, is the software. And specifically with the software, the first thing we need to think about is the kernel version. These are all Linux distribution. After all, we are doing a Linux privilege escalation, so all our machines, we can assume, are running the Linux operating system, so the Linux operating system. Now, Linux is an open source kernel that is developed by the community, and specifically, every Linux kernel has a specific version, and there are vulnerabilities that affects only specific kernel versions with specific kernel configurations. So actually, here it would be kernel version plus configuration. However, to understand easily the configuration is not too easy. So to simplify our life, we are mainly interested in the kernel version. You also have to think about configuration, but it's only more nuanced and more complex. For now, just focus on the kernel version and you will be good. And the next step in this group of 3 elements is the Linux distribution version. Why? Because on top of the kernel, on top of the Linux kernel, there are actually distributions built on top, which offer a lot of software. For example, here we have the kernel, and then we can have Ubuntu, we can have Arch Linux, we can have Kali Linux, and so on and so forth. Actually, there is an hierarchy of distribution, each of which builds on top of others, so it's like pretty complex. So the idea is that sometimes vulnerabilities arise because a certain distribution, like Ubuntu, packaged a software in a vulnerable way. So the vulnerability is only found in specific distributions. And this is why another thing that we want to enumerate is what is the Linux distribution plus its version. For example, we are running Ubuntu version 2004. This is an example. So these first 3 sets of things are like the overall configuration of the system. Hardware you're running with, kernel you're running with, and distribution you're using. Then we have some kind of configuration about users and systems. We start off with the users and the groups. So what are the users of the machine? What are the groups of the machine? And this can be easily enumerated using the etc passwd file. Then we understand if we have access to powerful groups, which means, okay, but my user, for example, who am I among all the users? What are my privileges as the user Leo or as the user whatever? And then we can check, okay, let's check the groups we belong with. Do we belong to powerful groups? And here, when I say powerful groups, it means groups that typically have access to specific command that can be used to do privilege escalation. An example is the Docker group. If you are part of the Docker group, you have access to the Docker command, and you can use the Docker command to perform a privilege escalation. So this is really important. There are other groups of the follow of the sort. So in general, enumerating the groups you belong to is really key. Another aspect of enumeration, of course, is the sudo configuration. This can be done with the command sudo-l. And of course, it works only if either you have the password or sudo is configured to not ask you for a password. So sometimes it works even without password. Other times you need to have the password of your user to use it. Either way, a good try on sudo-l is always useful to do. So understanding how sudo is configured essentially. Continuing, we have to enumerate all the file system directories. Of course, here, in general, it's hard to tell exactly a priori where you will find the useful stuff, where you will find the useful files. But typically, you have to try to enumerate, for example, all the home directories you have access to, this is key, all the OPT directory, because sometimes there are extra binaries, extra file, backup files and things of the sort, and also the var www html, which contains the root directory for web servers if you're running Nginx or Apache, stuff like that. So these are like the expose content towards the internet using the web protocol. There are other directories. You can enumerate the temp directories and so on and so forth. In general, be careful of the file system. You might find interesting stuff. Then another thing regarding the file system are the binaries with special permissions, and in particular with the setuid and getuid like bit on. So I already discussed about this kind of configuration and how you can exploit vulnerable SUID binaries. And specifically, there exist commands that I will show later on to enumerate only the binaries that have these permissions. So this is extremely useful, because if you find a binary with a SUID configuration, then you can ask yourself, wait a second, is this binary vulnerable? If it is, there you have it, a privilege escalation. So always consider those stuff. Then another important thing is the local services. So what's the idea here? Sometimes a server exposes two types of services. So given a service, this service can either be local or public. And here the distinction I make between local and public is the public service is accessible by anyone who has an internet connection. Consider, for example, a web server that exposes a WordPress, and anyone who goes to the correct domain will have access to that WordPress. So in this case, the WordPress listens to the public 443 port, which is the HTTPS protocol. So this is the port for the HTTPS protocol. So this is a type of public service. You do not need a special position in the network to access this service. Anyone in the internet, in the public internet, can access it. Other times, however, you have services that are configured to listen only on local interfaces. So for example, you might have a development server or a debug server or an internal service of any kind, but this service only listens in the local host interface, like 127.0.0.1 at a given port, say 3000, whatever. And maybe this service is used by developers who first have to access the machine, and then they can access the service. Typically, this kind of access is also done through SSH tunneling. So this is a key technique that later on I will show in the channel outside of the context of this series. But the idea is that you can have services which listen locally, and it's a key thing to enumerate them. And this brings me to the next point, enumerate all the network interfaces. Why? Because sometimes the use of a server is not really direct, meaning that the service itself, the server itself, does not contain useful information or useful data. However, it is connected to internal network interfaces that are not exposed to the public internet. At that point, in those situations, the server becomes an extremely useful pivot point. So the server becomes a pivot that we must learn how to use. And to understand this, we must enumerate all the network interfaces to understand if we have access to internal networks, what type of networks, and what are the hosts exposed in those network interfaces. So this is extremely useful. So this in terms of networking. Then of course we can enumerate all the software installed with the relative versions. So for example, if there is a vulnerable version of a known software, then we can exploit it. We can enumerate for backup or saved sessions. Sometimes certain programs save sessions in files, like Tmux is a great example. So if you use Tmux, which is a terminal multiplexer, sometimes it happens that the developers or developer operations, they leave out the saved session files, and you can just access them and you can restore the environment that was running previously. Then you have, for example, repositories that are under version control systems. Now, when you have a repository that is running with Git or SVN or other sort of version control system, the useful thing is to understand that we do not only have access to the latest version of the repository, but since it's running under Git, we have access to the entire history. So sometimes what happens is that we're able to go back in time and access secrets that were later removed, like password, access tokens, secrets of any kind. So it is very useful once you find a Git repository, go back in time, check the logs, check for suspicious stuff. Always useful to keep an eye out for. And finally, these two things, which I will discuss in later videos, which are cronjob and capabilities. Now, these two topics, I will make a specific video for each one of them, for cronjobs and capabilities, so I will not discuss them now, but to make it short, cronjobs are periodic tasks that are executed on the system, while capabilities are another way in which permissions can be handed over to binaries to do specific activities, and you can exploit both of those stuff to perform a privilege escalation. Okay, another thing that I didn't say here, but I put it later, is to enumerate environmental variables. So environmental variables, so variables of the environment of your shell. So this is key. Now, is this 100% all you need? Of course not, but this covers the major classes of findings that you will find in a real system, which means that typically what happens is that either you can exploit the kernel, or you can exploit a specific configuration of user and groups, or some secret was exposed in the environmental variables. You can exploit sudo, you find a specific binary or a backup or something that does not have the right permission, you find a SUID or GUID binary, you find a local service that runs with a misconfigured configuration, you find a network interface that puts you in a pivotal position inside the network, or you find a software with a given CVE, you find some backups, you find a repository and you explore that, or you find a cron job, or you exploit some capabilities. So typically, this is the idea. Of course, in each of those sections, things can get quite complex. For example, you can have a CV for a software that is really, really hard to exploit. But if you do these steps, if you enumerate all this information, then you will be able to understand what you need to do privilege escalation in most of the cases. And so now we can proceed on, okay, perfect. How do we enumerate this stuff? Okay, so now I just mentioned the various classes of things that you should look for. Now I'm gonna actually bring commands to get this information out of a system. And to showcase this, here I have a reverse shell that I just spawned in the Ubuntu. So this is the Ubuntu machine, and here is the command that I use to spawn the reverse. We don't want to do it through the VM interface because I just want to show how it looks like from an attacker point of view. This is how it looks like. So here we have a reverse shell. The first thing I suggest is just to improve the shell with a simple Python 3 c import pty.spawn bin bash. So string here bin bash. So now we have, and here I have to actually, so here I did something wrong. I have to retake the reverse shell, my bad. So it's Python 3 -c import pty spawn bin bash with a single quote here, and then I close the thing. And now I have a better shell. So clear, and it clears. So the first thing to look for hardware architecture, we can get it with the command uname a. I do uname a, I get a bunch of information here, and in particular, so uname a, in particular what we see is, so we see that we have an x86-64 processor. So this is the type of processor that is running. So that's the architecture. So we are x86-64. So this is a 64-bit machine. Then if you want the kernel version, look, it's already here. It's this Linux PC 5.15.0-117 generic. So this is the kernel version. To just get the kernel version, you can do uname-r. And here you get the kernel version. So this is running a kernel 5.15 and all of this other stuff. Then to get the distribution, you can do uname-a as here is written. Look, it's Ubuntu here, but to get the actual it's 20.04.1-ubuntu, or you can also use the lsb release-a. So with this, we get the release, the codename for the release, and all the information about the release. So that's good. Another thing we can get is the environmental variables, so the environment variables. So here are all the environment variables with the command env, with the command band. So the command env is used to print out all the environmental variables. And of course, all these commands, by the way, will be available. Link in the description will point to a GitHub repository. So we'll have everything for creating your own personal cheat sheet and stuff like that. So this is really useful because sometimes people hide stuff in the env variable. So it might be useful. Of course, when you spawn a reverse shell, it's harder for critical stuff to be stored in the environmental variable, but sometimes, let's say that you get execution on a web server, then you could have something like precious, you could have something critical, so always check that out. Then we have users and groups. So of course, with the user, with the whoami command, we can get the name for the current for who we are. So for example, in this case, it's the Leo user. Otherwise, we can just do a cut of etc passwd to have a list of all the users in the machine. So these essentially are all the default users, and then I have the special Leo user I created for this video. Now here, I show another command to create just a text file with just the names of the users. So how do I do this? This is the command with the pipe and the redirect. So the idea is that you do, first of all, a cut, etc passwd, but then we want to cut each line with the separator, with the column separator, and we want to take the first column. So the idea is that the etc passwd has a structure where it has information, then another information, then another information, and the various information are separated by these colon characters, by this dot. So the idea is that we cut thanks to that, and then we get the first column, so this one. And this one actually contains the username. So we cut that, and then we put this into a file named users.txt. So this command, we do this command, and then in the users.txt, it's just a file with all the name of the users. And it can be useful to just enumerate this information depending on your system if you do not have too much time. So another thing to do is the groups. So if you do groups, it's gonna give you all the groups that you are currently in. So Leo, ADM, CD-ROM, sudo, deep, plugdev, lpadmin, lxd, samba share. Then if you want to get all the groups in the system, we do cat /etc/groups, actually /group, here without the final S. So once again, we have all this structure information, and we can use the same technique as before to extract just the name of the various groups. How? We can do a cat, etc, group, then we do a cut, another cut. So like this cut is for reading, and this other cut is for cutting out. F1, and then we redirect all the output of this to the file groups.txt. And then we have groups.txt. I mean, if you do not want to create new files, you do not want to trigger maybe an antivirus or something like that, you can just get this without the redirection, and it's just gonna print them in the standard output. So if you do not want to interact with the file system, just do not consider the final redirection. And here groups I already showed to check if we have access to powerful groups. Of course, here the notion of powerful groups is not really specified. It is not my intention to specify it, but essentially some groups have certain capabilities like the Docker group. If you have access to the Docker group, you can create Docker containers, then you can create a Docker container and you can mount the root file system to the Docker container, and you're able to sort of like do a privilege escalation to access root files and things of the sort. So there are ways to use access membership to certain groups to do privilege escalation. Then another thing we can do is the sudo-shell. So sometimes the sudo configuration requires you to type a password. Here I'm gonna put the password of the user, a really simple password, I can show it. And now notice that the configuration says that I can essentially do all the commands for all the users. I can impersonate anyone to do anything. This is clearly like vulnerable if we have access to the Leo password. I mean, this just means that the Leo account and the root account are essentially the same. Because if you compromise the Leo account with its password, if you do an account takeover to the Leo account, then you are also essentially root. So this kind of configuration can be just means that the Leo account is the root account. Is it vulnerable? Then it depends how you treat the Leo account. If you are able to obtain the password, then of course you can exploit this and attack this. So I made a specific video on sudo, go check it out on how to exploit it, so I'm not gonna talk about this any further. So this is to enumerate the sudo configuration, pretty simple. Then we have the file system directories. So of course we can use commands such as ls. We can also use the command tree, but I don't think it's installed. So like typically this command is not installed, so I'm not gonna showcase it, but essentially tree allows you to visualize a directory as a tree. Like in my local machine here, if I do a tree/l2, so in this case there's not much, but like look at this. So this is all the material for this current video that I'm recording in a tree structure. It can be extremely useful. The problem, however, is that most of the time this is not already installed, so typically you will not find it. And to install new software, you would need root privileges. So it's not really that useful, but it's another way to exploit the file system. Otherwise, you have always ls. It's pretty simple, but also pretty useful. So you have this, so you can do this, you can do in the /home. Of course, in this case, we have all the stuff of the user. For example, a typical pattern is, do you have access to the private SSH keys of a user? Well, if you can read some directory and you see that there is an SSH folder, you can just try to read it. In this case, we can read it because this is our own folder. Of course, there's nothing in it, but we can still read it. So another useful thing to do. Then we can have, for example, var www. Actually, in this case, I guess there is no such file or directory. While as well as var, ls var. So in this case, we do not have the www directory because probably we have no web server, so it was not created. But in general, if you exploit a web server, you will have this directory. It will contain the public exploit files, and it could be useful to explore, maybe to introduce new files, to read the source code of the application, also extremely useful. Then we can enumerate all the SUID and GUID binaries. So the command is find /, which is the starting point of the find process. Then we do perm u equal s. This means give me all the binaries that have the SUID permission, and then we do to redirect dev null to redirect the standard error so that we see no errors. We do this because typically, if you don't do this, you will find a lot of not enough permission errors, so you want to skip them. And now we have this list of files. The idea is that this list of files, all these files have the SUID bit permission. For example, the Passwd, of course, it has this permission because it has to allow users to change password. Now, if one of those programs is vulnerable, then we can exploit it. In this case, of course, these are the default SUID binaries, so they are typically pretty safe. If you find a vulnerability here, you have a research, you can obtain a CVE. It's not that trivial, but in general, it's something to look out for. And then you can do the same thing, but instead of doing -perm -u, we do -perm -g to signal, look, I want the SUID binary, but not on the user, but on the groups. So this is called for the GUID binary, the GUID. And same thing with different binaries, of course. For example, this wall. In this case, we have a GUID binary, so the same thing applies. Then to enumerate for local services, we can use the netstat that prints out the current ports listening. So we do netstat with the flags -lpnt. So in this case, it's just gonna print out the local listening interface for the TCP sockets. So in this case, we have a local DNS server and this 631, which honestly, I don't know what's the process that listens on this. Let's do this as root, so we get also the program name. So let's do sudo netstat. So apparently it's capsd. So capsd, I don't know exactly what it is, but it's the program that is listening on this port. This means that if we exploit this, now we know that we have a local service running on this port. The address is the local interface 127.0.0.1 and the port is 631. This is for the TCP socket. For the UDP socket, the command essentially is the same. You just have to change the last flag from T to U. And here is the UDP ports. And with sudo, we also obtain the name of the process. Now notice that without sudo, we do not see the name. This is because to actually read the name, we need permissions, which we only can do with sudo. So an attacker might not be able to understand immediately what is the kind of process. But for example, if you see a local process listening on port 80, on port 22, on port 21, on well-known ports, you can typically expect that this is a well-known process implementing a well-known protocol. And continuing with network interface is pretty simple with IP-A, with IP space A. So IP space A, we get all the network interfaces. Look, in this case, it's just two. The local host, which every host has, and then this ENP1S0, which is actually the interface that the virtual machine shares with QEMU. So it is a NAT interface, and so this means that I can interact with the my host, with the QEMU listener, on the address 192.168.122.1. So in this case, this ping I sent to the QEMU in my host running the virtual machine listening. So if there is some kind of vulnerability in that specific component, I could be able to escape from the virtual machine to the external host. Of course, this doesn't really happen. It's not that simple, but it's another thing to consider, the network interfaces. Continuing, we have the software installed with the version. So either we can use which with the name of the software, but of course in this case, we will need to know the name of the software. So this is not really that useful. Then either we can go into the well-known directories where software is installed, like the usr locals bin, usr local bin, usr bin, and you can actually check this by going into the path. So the path environment, a variable in the environment, typically tells you where software is. So you start from this directory, then you can do some ls to enumerate the, in this case, for example, it doesn't exist here, and it doesn't exist here either, user bin. So user bin exists, we have all this software, and we can understand like the virus version. I mean, this is not really that fast to do, but here we have access to all the software that is installed. Just look for the path and just explore the binaries of the path. You will see a lot of common binaries. Just skip them and go for the binaries that are not that common, that you typically do not see. Continuing, with respect to backup, save session, and things of the sort, we can use the command find. So the syntax is similar to the finding of the SUID and GUID binaries, but now we're just gonna do -name with this kind of wildcard that it says, look, any kind of name with this specific extension. So like backup extension, KDBX extension, for example, this is the extension used in KeePass, in the KeePass password manager, and things of the sort, so this can be really useful. Then if you have a repositories under a version control system, you can do the git log commands, the git checkout, the git switch. This is not a tutorial on Git, maybe I can make it in the future, but the idea is that you can interact as if it's a normal Git directory. This means you can go back in the history and analyze previous comments to check out secrets. And finally, cron jobs and capabilities will be discussed in a later video, so I will not show any specific command here, because in later videos I will zoom in specifically on these arguments. And so this covers the main commands that you can use to enumerate a system. Of course, once again, there's much more, but this is a solid base to start off. You do this and you have an understanding of the system you're dealing with. Finally, to finish off the video, I want to talk about automated script. So the idea is that there are also automated scripts that essentially do what I showed and even more in an automatic way. So you don't need to press any command, they just give you the output. So how do you use them? And for example, here I listed the two automatic scripts that I know of. One is limpiece and the other is linenum. Personally, I prefer limpiece, but in this video I'm gonna show linenum. They are both the same essentially. So the idea is, how do we use them? The first step is in downloading the script in the attacker machine. So you don't want to download it directly in the victim machine. So for example, we can do this wget to download the linenum script. And here, if you do ls, linenum, we see the script. We can also read it. It's just bash. It's a lot of bash. It's just 1,300 lines of bash. And look at this. It contains all the stuff about the bug, system, user, environmental, job, networking services, software, interesting file, Docker, container checks, and footer. So just a series of commands. You can also read this file to understand the kind of checks that it makes if you're able to read bash. It's not too complex, just requires some time, but the idea essentially is to automate what I previously discussed. So here is the notes, here is the script, and here is our reverse shell. So once we have downloaded it into our attacker machine, the next step is to transfer it into the victim machine. So we're gonna start a local server in the attacker, and then with wget, so here I'm gonna get the IP. The IP in this case is, so in this case, this one does not work. So here I drop my shell. I have to get another shell here. I'm just gonna do the same, essentially, just gonna do the same command here. I have the shell, I'm gonna upgrade it. Import pty the spawn bin bash, and like this. No, okay, what did I do wrong? Of course, because it's technically like this, bin bash. Okay, now we have a shell. So the idea is that we do wget with our IP, with the attacker IP, which is 129.168.122.1. the port is 137, is the lead port, and then it's lin enum, I think. Okay, it's lin enum.sh. So we do this, notice we got a hit here, and we have successfully downloaded the script. I can make it executable with chmod. Typically they are not by default. So actually this one apparently did not read it properly. It's like this. So now it's executable, and then I can execute it. And when I execute it, I can use the T program to make sure that the output is splitted and is written on the standard output and into a file, so I do not lose anything. So I can do with this linenum pipe t and then linenum output.txt. Of course, this name you can decide however you want it. The t command here is used to make sure that the output of the linenum command is printed both on the terminal and also in the txt file. So we executed it, and now it's running the script, it's getting all the information, and it's printing that same information into the txt file so that we can then get it, so we can export it into our machine and analyze it in a better way. So it's very, very useful. So for example, here it says we are a member of the LXD group, could possibly misuse these rights, so stuff like that. And now we have this linenum output. It's a bunch of files and we can just read it. So we can do, actually we can just open here, this linenum output. We can just read it and we have all the output of interest. We can just try to read it, but essentially the idea is that it looks for, so let's try to read it fast. It gets all the information about the releases, about the hostname, the groups. Here are all the group membership. Here are all the users. Here are all the environmental variables. The path, information about the path, the shells, the files, and stuff like that. So like the network interfaces here. So essentially most of what I've told you, the processes, okay, so what I forgot here actually, is that other than the install software, of course, another key aspect of enumeration is to enumerate the processes. You can do that with ps aux. Here it doesn't work because the shell is limited. I can improve it, but right now I don't have that much time. So the idea is that, and one last thing regarding the software install are actually the processes. So remember, in the first video of the series, I showed how you can enumerate the process with ps aux, and ps-axjf that shows the hierarchy of processes. So this is also very important to understand. And essentially for now that's it. So this is the main idea for this video. The automated script, I typically use limpis when I use it, but also linenum can be used. And when it comes to, for example, certification, sometimes you have to be careful of using these automated scripts, because this kind of certification, like the OSCP certification, they don't want you to use scripts that automate the exploitation process. So one thing is if you automate only the enumeration process, but another thing is if you also automate the exploitation process. So be careful on the script you use, be careful on what it does, especially if you have to run it in a critical system where you have specific responsibilities, like during a penetration test, but the idea is that these can be useful. the best thing to do would be to actually create your own automated script based on the specific information that you need. These are a starting useful point, then you can add your own and create your own complex automated script to satisfy your own need. So this is it for this video. I hope it was interesting, enjoyable and useful. If it was so, please leave some feedback in the comment, share with like-minded people, subscribe to the channel, and to the next video. Hi everyone and welcome to this new video. In this video I continue my Linux privilege escalation series, and in particular we are doing this small section on enumeration. In the previous video I discussed how to do a full system enumeration. In this video instead I will focus on the aspect of Cronjob enumeration. So in this video we will see an example of Linux Cronjob enumeration. I will discuss what is a cronjob, what are cronjobs. I will discuss how we can configure them in a Linux system, how we can enumerate them, and then I will show a practical exploitation example where we go from enumeration to exploitation with a given out-of-the-box machine. It is the best machine, which I already made a full walkthrough. In this video we will just focus on the cronjob enumeration aspects. As always, I hope the video is interesting and you get something out of it. If you do, please leave some feedback, subscribe to the channel, and share this video with like-minded people so you can help me grow. So we can start with the video. I hope you enjoy it. First things first, what is a cronjob? Well, in Linux-based systems, a cronjob is essentially a command that is executed with a specific time rule. So when you see the word cronjob, just think command, like a bash command, a script, a program, any sort of action that you can do on the operating system, however, that is executed based on a time rule. This means essentially periodic, every minute or every 5 minutes or every day, or you can get even more complex configuration, like every 5th day of the month execute this task at 12 AM, things of the sort. Now, these commands are typically used to manage a running environment with tasks that need to be repeated every once in a while, such as backups, certificate renewals. So here we're talking about the TLS certificates. So in this case, it's the TLS X.509 certificates that has to be renewed because otherwise they expire, or removing temporary junk files, restarting the processes, and so on and so forth. So in running a complex system that is used for various tasks, for various things, you need to do periodic activities, and Linux offers the cronjob utility to take care of that. Now, understanding what kind of cronjobs are being executed in a system can be extremely useful, especially if the cronjob configuration is vulnerable. Once again, in the previous video we discussed why enumeration is important, and we said that enumeration is the process of painting the picture that represents the system. Once you have the picture, then you can understand the vulnerabilities, and once you understand the vulnerabilities, then you can exploit the system to obtain what you need to obtain. So that's the idea. In terms of cronjob, some configuration can be vulnerable, so once we enumerate them, then we can exploit them to obtain, for example, privilege escalation. Now, before discussing how we can enumerate them, it is useful to discuss how we can configure them and how configuration works. As always, in the context of computer security and offensive security, the general idea is that to understand how you can obtain information and how you can attack a system, first you need foundational knowledge on that given system. In this case, we are talking about cronjobs. Therefore, to enumerate and exploit cronjobs, we first need to understand how we can configure them. Only then we can understand how to enumerate and exploit. So, how can we configure cronjobs? Now, to list out the cronjob configure for your particular user, you can execute the command crontab-l. This means that different users can have different cronjob configuration. Now consider this Kali box. So this is the Kali Linux that I'm attached to out-of-the-box, and here I can do a simple crontab-l. And notice it says no cron tab for the user Leo. So right now I have no cron jobs configured for me. This is the idea. Now to edit the cronjob configuration instead, you can use the crontab-e. Crontab-e. And then it opens an editor. In this case, it's a vanilla configured Emacs because this is what I use. So this is the idea. This file, this crontab file, we can edit this file. After we save this file, the cron daemon will be reconfigured to take into account this new configuration. Now, as you can see, it says edit this file to introduce task to be run by cron. Each task to run has to be defined through a single line, indicating with different fields when the task will be run and what command to run for the task. So this means that we will have different lines here, and each line is representing a specific cron job configuration, where each line specifies some timing rule that specify when the command will be executed and the command to actually execute. To define the time, you can provide concrete values for minute, hour, day of month, and day of week, or use the wildcard in these fields for any. So what does it mean? Essentially, it means that a typical cron job entry will look as follows. So here we have 5 numbers, 1, 5, 1, 2, 3, 4, and 5. And eventually, some of these 5 numbers can also be this wildcard character, this star character. And then we have a command. Other times we might have this thing with the user. So like in this case we don't need the user because the user is already assumed. Other times we might have the same thing, but here we specify the user to run this command with. So there are different configurations. When we edit with crontab-e, we do not need to do that. So it's the user does not need to be specified. So the various numbers, the 5 numbers at the start, taken together are used to specify the timing information. That is, are used to specify when exactly, time-wise, the command has to be executed. Now specifically we have the minute, hour, day of month, and day of the week. So here there is a small typo, day of the week. For example, to execute a command on the 15th of February, so 15th of February at 9 AM, you can use the following rule. So this 09 specifies the minute and the hour on which to execute. So anytime we have minute 0 and hour 9, we execute this command. This means 9 AM. The third number is the day of the month, so the 15th of the month. So when the day is the 15th of the month, we execute the command. And finally, the second is the month. So this fourth number is a month, which is February, because 1 stands for January and 2 stands for February. And this fifth wildcard, it means that no matter when the 15th of February comes, if it's a Monday, a Wednesday, a Friday, a Saturday, it doesn't matter the specific day of the week. We will execute it regardless of the day of the week. For example, let's try to configure a very simple cron job here. We can say wildcard, wildcard, wildcard. So we have gonna be 5. So this is 3, 4, and 5. The command is a simple echo. We say hello world, and then we pipe this into TMP test. We save this, we close the editor, and now after the new minute, so in a bit, so let's go into temp. There is no test file now. Then notice this. Now after the minute has passed, notice this test file. If we check its creation date, it was in the 35, so 16:35 minute. And then if we check the content, it's hello world. If we remove it and we wait another minute, it will be recreated again, because now the crontab-l, look at this, now we have a cron tab, we have a specific job configured, and this job is saying to echo hello world into this file. So in a bit it's gonna be the new minute, it's gonna reappear again. So that's essentially the general idea. And so the crontab method is a way in which you can configure cronjob for specific users, such as the Leo user. Now there are other ways, however, that you can specify cron jobs without using the crontab, and this is by writing into specific configuration directories and files. Now let's get into root. So we're gonna get into root, so now we are root. And if we check the contents of the file etc crontab, we see that we have essentially this content. We can open it with Emacs, etc crontab. We can open it with Emacs, and here we have general cronjobs. Now the syntax used is exactly the same. The only definition is that in this case, other than the 5 like wildcards, 1, 2, 3, 4, and 5, we also need to specify the username before the command. This is because while the cron tab was already configured for the specific user, user Leo, user root, so this information was already implied, so you did not have to specify it explicitly. In this case, instead, this file is general, it's for any user of the system, and therefore we must specify the username that will run this command. For example, the root user to run these commands, and so on and so forth. Now there are other directories, like we have etc, cron, and then we have cron-d, cron-daily, cron-hourly, cron-monthly, cron-weekly, cron-early. So the idea is that in each of these directories, we have specific scripts that will execute in that given, for every given day. So in a new day, you will execute this script, like to clean stuff and so on and so forth. So this is essentially the idea. So like this is John, and here also is another directory cron.d where you can specify the cron jobs. And also notice this difference. While we are in this directory, here we specify cron jobs with the typical Cronjob configuration, while if we go into cron daily, here we specify directly the script to execute. So these scripts they inherit the rule, the time rule, based on the directory. If they are present in cron daily, they will be executed once per day. If they are present in cron weekly, they will be executed once per week. So in this case, we do not need to specify the cron job rule because it is already implied by the directory, sort of. So this is already implied by the directory. And this is essentially the general idea when it comes to Cronjob configuration. Now at this point, we can go into the more offensive side of cronjobs. We've seen the system side, why they are used and how they can be configured. Let's try now to tackle 2 more interesting questions: how they can be enumerated, and then I will show a practical exploitation example. So at this point, we can start to understand how can we enumerate cron jobs, and I want to understand if there are cron jobs executing in this machine. How exactly can I do that? What facilities can I use that will help me to understand if there are cron jobs being executed right now? Because it's not that easy to understand, given that sometimes these commands are really fast to execute. So how can we do it? Well, the idea is that to enumerate cron job in Linux, we can use a tool called PSPY. And here I put the GitHub link that you can see here. This PSPY by Dominic Breuker monitor Linux processes without root permission. So the key idea of this tool is that it does not require root privileges. And this makes sense because if we needed root privileges, then this tool couldn't be used to do privilege escalation. Since the tool does not require root privileges, it makes sense to be used in a privilege escalation scenario. So PSPY is a command line tool designed to snoop on processes without need for root permissions. It allows you to see commands run by other users, cron jobs, etc. as they execute. Great for enumeration of Linux system in CTFs. Also great to demonstrate your colleagues why passing secrets as arguments to the command line is a bad idea. The tool gathers the info from procfs scans, iNotify watchers placed on selected parts of the file system, triggers these scans to catch short-lived processes. So essentially, the idea is that this tool uses a specific file system which is called the /proc file system, and this file system is generated by the Linux kernel during its execution. The Linux kernel uses this file system to contain information, dynamic information that reflects the current state of the processes being run. This is why it's called /proc. And so the idea is that this tool utilizes this information in order to obtain information regarding currently executing processes, which include, of course, cronjob processes. So essentially, you go into the system, you go into /proc, and notice here you have a bunch of different files. Here you have files that have numeric values in the first section of the directory, here, essentially. And then in the other section, you have other stuff, so like this one, always with an ID, with a number, and then these other are more general of the overall system. So if we zoom in into any given number, like let's say CD096, we have a bunch of information for this ID. Now, what is this ID? It is the ID of the process. Like for example, if you do a ps-aux, and the second column is the PID, so if you go into 906, so this one, 906, this is the SSH agent X session manager. So if we go, for example, we take the cmd line file, this cmd line is exactly user bin SSH agent X session management. So these files are actually not really normal files as in your typical files. These files are created by the kernel and they are handled by the kernel. When you ask the content, the kernel is executed and it reads from memory the content of this file. So this is a in-memory file system, the /proc file system, which is handled by the Linux kernel. And the idea is that the PSPY tool uses this file system to obtain information about currently executing cron jobs. When a cron job executes, a new entry in this file system is created, and so the tool understands that. And then there are, of course, optimization to make sure that the process of looking for new directories and files is efficient and doesn't slow down the system and the usage of the tool. So the first thing you need to do if you want to use it is you need to understand the underlying hardware architecture that your CPU is running on. Specifically, if it is a 32-bit CPU or a 64-bit CPU. And I showed how to do this in the previous video. We can simply do uname, uname r, and it uname -a, and here we have all the information. Specifically, we are running on x86_64, meaning it is a 64-bit architecture, and so we can download the 64-bit version of the tool. So we can use wget to download the tool, and we can do wget, and here is the URL essentially, so github.com. And so at this URL we can download the latest version. Of course, this command should be executed on a directory in which we can write. So for example, we can do into tmp, the temporary directory, and then we can do the wget command. We wait a bit. So after we have downloaded the tool, we can check out its characteristic with the file command. Notice that it is an ELF 64-bit executable, and specifically notice that it is statically linked. It means that all the dependencies and all the libraries are contained within the executable, and there is no need for external libraries, like for the glibc library and stuff like that. If we do an LDDD, which tells us the dynamic libraries, it says, look, this is not a dynamic executable. I have no dependencies on the current file system. This is extremely useful when it comes to exploitation, because in a remote system, you never know if you have the right versions of the library. And also, this is why this executable is like 3 megabytes, which is not that light. There is also another version, which is the small version. So the small version is dynamically linked, because the idea is that it's small, the payload is small, however it requires external library, so it might not work if you download it on a host that doesn't have those binaries. So after we download the tool, we can just make it executable as follows. And so at this point, the only thing that we need is just to execute it essentially. So we do pspy./pspy. And then here it's gonna start to analyze the proc file system. It's gonna give us like files that are executed in the moment essentially. So like here, for example, we can see that it executes a lot. This script, xfce4 panel genmon vpn ep.sh. So this script. And then like in a system, in a CTF, you just wait until you see something suspicious. And so that's the idea. So it's the output that we will see. Now, in terms of Cronjob exploitation, I want to give a practical example taken from ActedBox. Now, I've already brought to the channel the walkthrough of the bashed machine, and in that machine at some point there was a Cronjob exploitation. So what's the idea? Here I'm gonna start Kali, and in the history I believe, here I've already have the machine. Essentially, for those who didn't see the walkthrough, I suggest to just go and check it out. Okay, but first I need to connect to the VPN. So here I connect to the VPN, and then I'm able to access the history essentially. So let's go here. So the bash machine was this static site that contained a dev directory which exposed a web shell in PHP. So here we are executing in the context of www data. Here we can get essentially reverse shell payloads using pentestmonkey, testmonkey, reverse shells, and we just need to change the IP. So we go into the Python is good enough, we copy it here, we paste it here. The only thing we need to change is the port 4321 and the IP. I'm gonna put the IP that I'm currently connected to the ActedBox network. So in this case, it is the 10.10.10.10.14.21. So this one, I'm gonna put it here, essentially. So this is it. Now I'm gonna open a netcat listening on 4321. So notice here, I have a reverse shell. I'm gonna upgrade it with Python 3, import pty, pty.spawn, bin bash. And then I'm gonna do the same thing. However, since the sudo-l is vulnerable, because the sudo-l tells me that the user www data can execute all commands as the user script manager. So this is a vulnerable sudo configuration. I can just do sudo -u script manager and then the same thing as the shell upgrade. And now I am script manager. At this point, the idea is to use the PSPY tool. So like here I can do export xterm and then I can clear. So the idea is to use the PSPY tool to enumerate the cronjobs. So how can we do it? Well, we've already downloaded the tool in our machine. So we go into TMP and we have this PSPY64. So the steps are enumerate the architecture to understand the binary that we need. So either 64 or 32. I can say you name A and look at this. x86 64, so we are a 64-bit machine. We can use PSPY64. We download the binary into the attacker box, which we already did because it's in our Kali box. Then we transfer it from the attacker box to the victim machine. So I'm going to start a quick Python 3 server at port 1337. 1337, it's really important, this port, cannot mistake this. And then in the victim machine, I'm going to do a wget HTTP, and then I put the IP address, which I already forgot, of my connection with ActedBox. So I'm going to put a new tab, EPA. So this is the EP 10.10.10.14.21. So here, essentially, 10.10.14.21, 1337, and then PSPY64. So I'm going to get this. Notice this, I have the binary. And since this binary does not need external libraries, I can just execute it, PSPY64. I just do this and I execute it, PSPY64. Actually, before I'm going to open a new tab because we're going to need a new reverse shell here. So let's just spawn it right now because it's better. So here I have a new reverse shell, sudo script manager, Python 3, import pty.spawn bin bash. Okay, so let's execute PSPY in here and let's wait a bit to see the various processes that are executed on the victim machine. So at some point in the output of our PSPY, we notice that essentially it does this thing. It executes this command, it goes into the cd/scripts directory, and for every file that ends with the .py file, it's gonna do Python name of the file, and then it did a Python test.py. Also notice here the PID 1741 and the PID 1740. So first come the 40 and then the 41, and before those the 39, which is the cron daemon, essentially is the cron process. So the idea is that there is a cron job here that goes into the script directory and execute every script name that finishes its name with .py. So the folder here is cd/scripts, and for example there is this test.py, which just open the test.txt. And so the idea is that all the scripts that are present in the /script folder, all the files that end with .py will be executed with Python. So this is the vulnerability of the cronjob. How can we exploit it? Pretty simple. The idea is to create a reverse shell in Python and then expose it with an HTTP server. So let's get it, let's put it into the remote host, into the victim host. So this is my IP address, 1337 rev.py. And then here, I'm starting a netcat listener, and notice that thing, I already got a root shell. So now I can go into /root, I am root, who am I, id, host name. I can spawn a better shell, spawn bin bash, and stuff like that. So this is a practical exploitation, and all of this was possible because we executed PSPY and we were able to understand that there was this specific vulnerable cronjob that executed all the script present in the /script directory. So that's the general idea. And so with this, we conclude this video. The tool here is PSPY, is extremely useful. It doesn't always work, of course. There's no guarantees, but most of the time this tool will be useful. You just run it on the background and read its output to understand what is going on in the system. And that's it for this video. I hope it was enjoyable. If it was so, leave some feedback in the comments and see you to the next video. Hi and welcome to this new video. In this video I continue my Linux privilege escalation series, and in particular we will finish our enumeration section by discussing how to enumerate Linux capabilities. So in this video I will discuss what are capabilities in the Linux operating system, how we can configure them, how we can enumerate them, and then I will show two practical exploitation examples where we give a binary specific capabilities and then we exploit those binaries in order to perform a privilege escalation. And I will show this example within a virtual machine. So this is the virtual machine. So that's it. I hope the video is interesting and enjoyable. If you get something out of it, please leave some feedback, subscribe to the channel, help me grow, spread my channel with like-minded people, and enjoy the video. So to start off, we can discuss what are capabilities in the Linux operating system, what is their role and why were they introduced. Now, other than the basic permissions like file permissions, Linux offers a set of fine-grained permissions that allow processes to do specific tasks with higher privileges, for example, root privileges. Now, I've already discussed Linux permissions, and in that video I said that each file, each resource on the system has an owner, a group, and then permissions for all other users. So like if you get any sort of file, so for example, let's get the file of this presentation, this notes.org. This notes.org has three different sets of permission, the one for the owner, that is Leo, the one for the group, that is also Leo, and then the one for everyone else. In this case, for example, the notes.org can be read by everyone in the system, but can only be modified by the user Leo. So only my account can modify this file. So this kind of permissions apply to every file in the system. And for example, if you have a file that is owned by root, you can specify what the root account can do on that file. Now the idea though is that these permissions are not the only ones. Actually, there are other permissions which are more fine-grained, meaning they do not just handle changes in read, write, and execute. They do not just handle those big permissions, they handle much more fine-grained permission. Now, specifically, while traditional Unix systems distinguish only between two types of processes, those privileged with the effective user ID equal to 0, and I've made a video about that. Go check out the video where I talk about SUID Exploitation. In the video where I talk about SUID Exploitation, I talk about effective user ID. I talk about all this kind of stuff with user ID. So when you have a process with effective user ID 0, that process is a privileged process. Otherwise, if it's different from 0, then it is not privileged. It's a pretty simple view of permissions. Now, in Linux, this is not the case, however, because from Linux kernel 2.2, so from this version onwards, and now we are at version 6 point something, I believe, privileges are split into distinct units known as capabilities, which can be enabled or disabled on a per thread attribute. So what does it mean? It means that instead of having like big blocks of privileges like read, write, and execute, now we have much more fine-grained privileges, and you can assign these specific privileges to like files, binaries, programs, and so on. And essentially, they are used to implement the least privilege design principle. For example, a really simple example of this thing is the program ping. Now, the program ping to work in certain distribution, not in all of them, but in certain distribution, the program ping has to have access to raw sockets. And this thing is typically something that requires pseudo privileges. So what do? Do you assign to this program the entire permissions of root? Or you split the ability to access raw socket into a specific capability, and you assign to this command only the capability to access raw sockets. Essentially what happens is that in certain distribution, the ping command has the capability to access raw sockets. And how can we see that? Very fast, we can do get cap. We will talk about later on this command, usr bin ping. And notice this, it says usr bin ping cap net raw equal EP. It means that this binary has this capability with a certain configuration. So it means that it has a capability. Now, I said that in certain distributions because this is not true for all possible distributions. There are ways of using ping and of packaging and building ping that does not require having special capabilities. So just bear in mind that sometimes you might not find anything when you do get cap on your bin ping depending on your distribution. The distribution here that I'm using, for example, is Akali. It's Akali rolling 2024-02. So that's the idea. And yeah, so capabilities are used to implement the least privilege design principle, which tells us if you have to do an action, do it with the least amount of privileges required. So if the ping command is to access raw socket, perfect. Do not give the entire capabilities to the ping command, but only the one he actually needs. And this is a good principle to have in mind when design system, because it makes sure that even in the act of compromise, for example, even if the ping command is compromised, an attacker can only use a limited amount of capabilities and not the entire list. Now, to see the list of all the supported capabilities, you can check out the following links. So here is the main page in the web form, and then there is the Actrix page of Linux capabilities, extremely useful resources. So essentially, this is the capabilities list. For example, we can have cap chown, make arbitrary changes to file UIDs and GIDs. So like this capability is a specific action. It means that if you have this capability, you can make arbitrary changes to file UIDs and GIDs. If you have cap fowner, you can bypass permission checks on operation that normally require the file system ID of the process to match the UID of the file. It's like these capabilities change the way that the system works, and they are extremely useful. For example, cap set UID, make arbitrary manipulation of process UIDs with set UID, set error UID, and so on and so on. It's like they are really useful to know because they can be used, for example, for exploitation. And in the Actrix here, it explains, it goes into depth about this, that there are 5 different capability sets: inherited, effective, permitted, bounding, and ambient. And essentially, when you assign a capability, you can assign either in one of these sets, in the inherited, effective, permitted, bounding, and ambient, and they have different purposes and they act differently essentially. For example, if you pass something inherited, this determines the capabilities passed down from the parent process to the child process. It means that if a program has this capability as inherited, when it creates a new child, the new child would also have that capability, and all these other details, which for now we're not really interested in. Why? Because at the end of the day, we're interested once again in the system point of view, meaning how do you configure capability, how do you read capability, the enumeration point of view, how do you extract information about the capabilities in a given system, and finally the exploitation point of view. And so the first thing we're interested in is the system point of view. How can we configure capabilities? Now, to obtain all the capabilities of a given binary, you can use the getCap command. For example, you do getCap, you assert bin ping, and here you have the capability assigned to the ping command. Perfect. And this is what we did here in the virtual machine. We did getCap, and this is the capability. Now, to set a new capability instead, you can use the setCap command. For example, we already have the capnet row. Perfect. Let's say though I want to add a new capability, for example, the capnet bind service. How do I add it to the binary? I just do a setcap. Of course, it requires sudo because it requires privileges. I do sudo setcap, and then I put the first capability and then the second capability. I have to repeat this one because otherwise it's just gonna set this only, the capnet bind. So I repeat the capnet row, I add the capnet bind, and then I put the binary name. And with this, we have added the new capability capnet bind service. I can do it on the virtual machine here just to test. So I can clear this and do this. And then now if I do getCap, you assert bin ping. Notice now that I have two capabilities. I have capnet bind service and capnet row. Very useful. And with this, we have the new capability capnet bind service. Finally, to remove a capability, you can also use setcap, but with the minus sign. So here we put EP, which is how we configure the capability, how we put the capability into the various capability sets, so effective and permitted, EP. So this is why it's called EP. And then if we want to remove it, we have to remove it from all the different sets on which we put it. So we do minus EP. So we do this, for example, once again with sudo. And then if I do getCap again, notice that it's gone. So this is really simple. So essentially we can read capabilities, we can set capabilities, and you can remove capabilities using the getCap and the setCap commands. Now, when it comes to the enumeration of capabilities, we can actually use the getCap command, because the getCap command allows for a recursive flag, for a recursive options which searches the entire file system. So a really simple command is the following: getCap -r/ to redirect, this is the redirect for standard error, to dev null. For example, consider this system. So this is the virtual machine. If I do this, what are we gonna get? We have to wait a bit, of course, because it searches the entire file system. And then at the end of the day, when it's done, it's gonna give us all the files with certain capabilities. So notice this. We have ping, as I said, we have dump pickup, we have fping, then we have d68664 gstreamer, and then we have gdb with the cap sysptrace capability, and then we have Python 3.11 with the cap setuid capability. Very interesting capabilities. So like to enumerate, it's really not a big deal. You can just use this getCap command. Otherwise, you can also get the capabilities of a given process with the command getpcaps. So for example, let's say that I want to check the capabilities of a running process. I do psaux. Here I have a bunch of stuff. Let's get the SpiceWd agent, the capabilities of the SpiceWd agent with PID 861. And I do get pickups, PID. And here I have the Cape Wake Alarm I. So this has been inherited from the parent process. So that's the general idea with respect to the first two methods. Finally, you can also enumerate the capabilities using the pseudo file system /proc. In particular, this pseudo file system, if you go in proc here, /proc, it contains a bunch of different information about the running processes. What we're interested in is, for example, let's try to get this Cape Wake Alarm. So we go into 861, which is all the information for this particular process, for the SpiceWd agent, and then we say cat status, and we grep for cap. And these essentially are the capabilities we have: capabilities inherited, bound, ambient, effective, and this kind of thing. And to decode this hexadecimal value, it's like a bit mask. To decode it, we can use cap sh -- decode equal, here we put the value, and now what we get here, cap wake alarm, which is the same thing we got previously, cap wake alarm inherited. So the fact that this is inherited, it means that it belongs to the inherited set, it means that it changes this bit mask value, and then we can decode it and obtain the original thing. So we can also enumerate the capabilities of running processes. And so these essentially are 3 ways in which you can enumerate the capabilities in Linux. Search recursively with get pickup. If you have a specific PID, you can either do get pickups or cat proc PID status. You grab for capabilities and you decode the value using capsh. Now I'm gonna show 2 specific examples of exploitation, because the idea is that some capabilities allows for privilege escalation. So you just need to learn what are the dangerous capabilities, and if you find a binary with said capabilities, with these given capabilities, then you can exploit it in order to perform a privilege escalation. For example, here I've listed some capabilities that allow you to do privilege escalation, but there is an entire list. You can check it out in the link that I put here in this hacktricks, book.hacktricks.xyz, so go there. So there is this entire list. So the one we're interested in, for example, are cap sysadmin, which allows you to do administrative privileged tasks such as mounting device. For example, this capability can be used to do Docker escape. So you are inside a Docker, you want to escape to the host. If you can mount a device, you can just mount the entire file system and you have root privileges over the entire file system, which is pretty dangerous. Cap sysptrace, which allows you to debug any process using the ptrace system call, so ptrace, and we will see an exploitation of this, very interesting. Cap sysmodule, which allows you to load and unload Linux kernel modules, because the Linux kernel, since it's open source, has been developed with a technology known as LKM, which stands for Loadable Kernel Modules. And this LKM technology allows drivers, for example, to install specific module when you plug in a USB device, for a practical example. So the idea is that when you load modules into the kernel, you're actually increasing the kernel code. And if this kernel code is malicious, it could be a really huge problem. For example, a lot of rootkits start off by being kernel modules, which then hide and modify data structure within the kernel. So very, very dangerous capability. And finally, the cap SUID, which allows to set the effective user ID of the created process. Once again, really dangerous. You can just set it to 0 and become root. But as I said, this is just a limited list. A more extensive one is the following one. So this list, for each of these capabilities, they allow you to do something interesting which could be damaging in terms of security. Now for our practical example, I will show just 2 to give the idea. One is going to be with cap SUID and the other is going to be with cap sysptrace. So let's start with cap SUID. Because if you remember well, after we have enumerated all the capabilities in the system, we can do it again essentially. So it's like get cap r/, and then we redirect the standard error to dev null. So after we do this, we notice that we have a bunch of interesting capabilities. In particular, we have the cap SUID on Python 3.11. Now, why is this dangerous? And we can just zoom in by saying get cap of this binary, and we get the cap SUID. Now, this can be easily exploited as follows. So, consider this folder. Here we have Python. We have actually, I think it's py. It's cap SUID py. So, notice this simple script. We import 2 Python libraries. These are internal built-in, so we don't need to download anything. And then we do os.setuid to 0, and then we spawn a bash. Now, this thing normally wouldn't really work, because we could not do this. We could not set the setuid to an arbitrary value. However, since we have the capability, since the Python 3 interpreter has the capability to make arbitrary changes to the effective user ID, we can literally just set our user ID to 0, And when we create a shell, when we create a bash shell with this, not this. So I start with the user Leo. I'm UID 1000, and then I say cap set UID. And notice now, who am I? Well, I am the user root. So it worked. It's extremely easy. Why did this work? Because if I do get cap of user bin python 3.11, this has the cap set UID. If I remove this capability, so if I do set cap set UID minus of python 3 like this, now it no longer has this capability. What I can do is I can try it again, cap set UID, but of course it's not allowed because this operation, the operation of arbitrarily change the set UID, is not allowed. It is only allowed because before this binary had this specific capability. So here I'm gonna set it to plus, and then if I do it now, it's gonna work again. So anytime you see cap set UID capability, you can probably most likely exploit it. Of course, it's not always this simple. You still have to force the program to make a set UID system call. But in this case, it was Python that had this capability, and we can write arbitrary code in Python. So we can also do OS set UID. Internally, it is developed to translate this instruction into the system call to change the user ID, and then we can just spawn a bin bash. So really simple exploitation. So this is the first example. And so our first example we have completed, which was this one, Python 3 with a cap set UID. Now the next example has to do with GDB, which has the cap sys ptrace capability. Now I've already made a video on the tool GDB. It's essentially a debugger. It allows you to debug program, and I've made a video showing how you can get started with GDB. So go check that out. I'm not sure if it's out yet, but if it is, go check that out if you're interested. Now, in terms of the cap sys ptrace capability, this capability essentially has to do with ptrace, with the usage of the ptrace syscall. Now, what is ptrace? Ptrace is the foundational of all debugging because it allows a process to have control over another process. For example, it allows a process to say to the system, look, when this other process gets into this state, then stop its execution. And this is all done through the ptrace system call. It also allows to modify the memory of other processes and so on and so forth. So this thing is mainly developed for debugging reason, but of course, what one sees as debugging reasons, another can see as a means for privilege escalation. So essentially that's the idea. Now, why is this dangerous? Well, because if we can just arbitrarily modify the memory and the execution of a program, then it's like really simple to understand that this can probably be used to do privilege escalation. So how can we do it? Now, there are many ways in which we can use this, but they all revolve around the same idea. So the idea is that we get a process that is actually running on the system as root, and we can do that with the command psaux and then we grep for root. For example, in this case, we have the system journal, whatever. Then with GDB, we can hook into a currently executing program, GDB with the -p flag, and here we put the PID. And notice that now we are debugging that particular root process. I mean, for some opening of files, it says permission denied, but essentially we do have control over the process. So that's the idea of the exploit. Now we can exit because we don't really care about that. So there are many ways to exploit this. I will show a very simple way that has to do with using Python. So let's say, for example, we have a Python root script that has this simple code. So I'm not really interested about the code. I'm just interested about a root process that is executing a Python script. For example, Python root. So here I just started the process as root. Once again, I don't care about the logic, the internal logic. It could be any sort of logic. What I'm interested in is that it is a root process and it executes Python. And I can notice here that if I grep for root, the last process is python 3 python root.py with the PID 1426. Now at this point, we can do what I did before, but with 1426. And now we are entering into essentially the process. Perfect. And then we can just do a call system touch tmp test. So we can just do a call of system, and then we can put our like the command we want to execute. If we do this, this is gonna like there's gonna be some permission denied for sure, but the idea is that it's gonna execute this command as root. And indeed, if you go into the tmp folder, now we see a file test that was created. Not only that, this file test has been created as the root user. So very, very interesting. And so, for example, we can just do a call system of any reverse shell payload, and here we get a connection running as root. So we can get a full shell running as root. And this all has to do with the fact that since the gdb command has the ptrace permission capability, then it can hook into any process, even those that run as root. Because let's get cap usr bin gdb. So let's do set cap. We're gonna remove this. We're gonna do set cap minus usr bin gdb. So task for a password. Okay, we have removed the capability now. There's no more capabilities. And now if we try to hook into this root process, it's gonna say, look, ptrace operation not permitted. We are not able to attach to process 1426. We were only able to attach to the process because we had this particular capability. And now we do it again. And now we are able, and we get, for example, if I get the TUI, I mean, here we do not have a source, TUI layout asma, and we attach to the root running process essentially. But this only works when we have the ptrace capability. There are other ways of exploiting this. For example, another way is to inject our own shellcode and try execution like that. It is not always that reliable. This method for Python is pretty reliable, but of course it requires Python to be running. But there are many ways essentially to get code execution as root even without this specific setup. And it's up to you to explore, because there's a lot of stuff in this space. And so this is it for this video. I discussed what are capabilities in Linux, how we can configure them, how we can enumerate them, and finally I showed 2 specific exploitations example. I will leave some references in the description. This has to do with main pages of list of capabilities and specific tools, a Stack Overflow command which was useful, and the page on hack tricks. So go check out those references because they are extremely useful. In this space there is a lot to say. This is just to give you the basic idea with some practical exploitation example. You will find all the material in the GitHub page. So as always, I hope it was interesting and useful. If it was so, please leave some feedback, subscribe to the channel, and share this video with like-minded people. Thank you for the support, and to the next video. Hi and welcome to this video in which I continue my Linux privilege escalation series. In this episode we will talk about the exploitation of local services. Sometimes the way to privilege escalation, the way to elevate your privileges, is by exploiting the local services that are running on the server. Let's say you got access to a reverse shell. In that server there could be local services which could be vulnerable. So the question is, how do we get access to those local services? So in this video I will talk about what are local services, and then I will show 2 practical exploitation examples where we will use 2 different port forwarding techniques to get access to the local services. In the first one is the local port forwarding, in the second one is the remote port forwarding. And in those examples we'll analyze some Python code and we have a Docker to play with. So that's the idea. I hope the video is enjoyable. If it is, leave some feedback, let me know what you think. Share this video with like-minded people to help me grow, and that's it. Enjoy the video. So what are local services? Now sometimes services are configured to only listen in local network interface. Now a service is any process that listens to a TCP endpoint connection. It could be either TCP or UDP. So anytime you have either TCP or UDP endpoint, and these are characterized by the IP port couple, so you have to define an IP address and a port address. Anytime you have an endpoint like that, you have a service, and if this service runs on local interfaces, then you have a local service. So the thing about local services is that, let's say that we get access to a server, like we have, this is our attacker machine, our attacker box, and this is the server. Now from the outside, we can only access services which are exposed to the public network interfaces. Let's say, for example, port 80 or 443 for HTTP or HTTPS, like typical web servers. Those ports are exposed to the public interface. However, there could be other servers that are listening but only to the local network interfaces. Now, in those cases, we cannot interact with those services directly from our attacker box. First, we need a way to get inside the machine, and then we need a way to do port forwarding to connect one of... So let's start by describing a little bit what are local services. Now, the idea is that sometimes services are configured to only listen in local network interfaces. Now, a service is any process that listens to a TCP or UDP endpoints, we could say. So typically, the most common services are those that listen on the network protocols, such as TCP and UDP. However, to specify a service, you need an IP and you need a port number. So this is the way to specify a TCP UDP based services. Now, depending on the IP that is chosen, you could expose your service to either a public or private network interface. For example, every machine has the network interface 127.0.0.1. If I expose a service on the IP 127.0.0.1 with port, for example, 1337, now this service is exposed only locally. It means that only processes that are running on my machine can access this particular port. This is also known as the local host interface. So when you expose a server to the local host interface, that is only a local running service. Now, in these cases, we are not able to interact with these services from the internet, which means as an attacker, we can only interact with publicly exposed services, which typically are, for example, HTTP, for example, in port 80. This is the port for HTTP. This is the TCP/80 or TCP/443. This is typically the services for HTTPS, which is HTTP on top of a TLS session, which protects with respect to cryptography. So the idea is that we can only access publicly exposed services. Now, let's say though we have a local service that is actually vulnerable and that can allow us to perform privilege escalation. How can we access those services for exploitation? Well, the idea is that we need a way to do port forwarding, which is a technique to join one endpoint towards another endpoint. It's sort of like we connect things which initially we do not have access to. And a simple way to do port forwarding is by using an SSH connection. So anytime we are able to log into the server with SSH and then we find a local service on the machine, then we can use the techniques that I will show in this video through SSH to do port forwarding, to access the local services and to exploit them in order to obtain privilege escalation. So when you connect to a compromised machine, when you get remote code execution into a server, always make sure to check the network interfaces available, and you can do that with the command, for example, EPA, and also check if there are any open ports or processes which listens on well-known ports or in general in any sort of port. So for example, let's activate one of our local service labs. So let's do this one. So I'm gonna go here into source. So this is the local port forwarding. The first example, here there's a Docker file. It's a simple Docker file to deploy this Python application. And here we are creating a user called Ubuntu with the password ABC123. The app itself, local port forwarding app, is a simple Python app that exposes a vulnerable endpoint /cmd. As you can see, this vulnerable endpoint takes the CMD input from the user through a JSON and then simply runs the command that was specified in the input. So this is extremely vulnerable by design. It's just to showcase the technique. However, notice that this application is run on the local interface 127001 listening on port 7777, so like 4 sevens. So let's start the Docker to see what I mean, because these things can be a bit confusing, but I believe that Pratice will be able to explain it all. So I've just finished to build a machine with the Docker build no cache /t local service lab 1. And now we can start the image, we can start the Docker. So we have started it and we can connect it with the SSH command. So we can say yes, and the password is ABC123. So now we are inside the Docker. So to actually enumerate and make sure that we have this local service, let's run the command IPA. So we do IPA, and here we have, we have two interfaces. One is the ATH0 at if17. This is the Docker interface, that is the interface that the container uses to interact with the Docker system. And then we have the typical loopback interface, which has the name LO, with the internet address 127001. Perfect. Then we can check for listening ports with the command netstat-ltpn. So this is gonna check for TCP listening ports. And notice that here we have the typical 22 port that listen on all network interfaces. This 0.0.0.0 means listen on all two network interfaces. It means that it's gonna listen on the 172.17.02 and also on the 127.0.0.1. So both, it just means all network interfaces that I have available. Notice instead that we have another TCP process that actually is listening only on the 127.0.0.1 on port 777. So this is our local process. It is the Flask application that is running on the server, on the container. And we can also check with ps-aux that we have effectively a Python 3 application, so Python 3 app.py. So this is all very interesting. Now let's say that we are in this particular condition. Let's go into app, we can check the code. So we want to be able to access this application, however, not from within the Docker. Why? Because I can already access the application from within the Docker. I can already do, for example, a curl. Let's say, do I have curl? Okay, here I have curl. Let's say that I have a curl, so I do curl HTTP 127.0.0.1 port 777. I go into the CMD endpoint, which is, we can use get, for example. And here I'm gonna use -d to give the data. I have to give it in JSON form, and then I have to say cmd equal UMI. And then here I believe we're gonna do a post, actually let's do a post request. And it says, okay, method not allowed. If I do a get, it says, did not attempt to load JSON because of the request content. So I'm gonna say I'm gonna add an header, content type, and then here I put the colon application/JSON. Okay, notice that here I'm able to do this command directly in the container. So you could say, okay, technically I've already achieved execution as root because this program, this Python script, is actually running as root. And notice here, I said the command whoami, and he replied with root. And so by performing an HTTP request with curl or with any other tool directly in the container, I'm able to access the endpoint 127.0.0.1 of course. Now the issue, the technique that I want to showcase in this video is, okay, let's say however that I couldn't do it within the container. Let's say maybe that I needed to access it graphically with a browser. I needed somehow to access it from my attacker box, not from the server that was already compromised. If I try to access, if I try to do the same command from my attacker box, notice what do I get? I get fail to connect to the server. Why is this the case? This is the case because if I just see my attacker box here, and the Docker image, the Docker container, the running image, here the only thing that is exposed is the port 22. I'm using the port 22 to establish an SSH connection. I mean, actually, this is the listening port. Then I use another one to actually send the data. However, this is the listening port. I use this, but the 777 is just used internally in the Docker. It is not exposed publicly. So as an attacker, I cannot access directly the 7777. And this could be a problem if I had to interact with the service, with the web server, and so on and so forth, with a specific setup. Like, for example, I needed to use my browser, the attacker browser, to access the web application. This is not the case for this trivial example, but just imagine we had this issue. So that's the idea. How do we do that? How can we connect this thing? So the idea is that there are two main ways in which we can access a local service. And this is the local port forwarding and the remote port forwarding. Now, in the local port forwarding, the idea is that with this technique, we redirect traffic from a local port on the client machine to a specified port on a remote server through an SSH connection. So the idea is that with local port forwarding, we take our client, which is the attacker. So the client is the attacker. So client equal attacker. And we say, look, I select the particular endpoint, like the particular port 1337, and then through the SSH connection, I'm able to link this port to the localhost 777 port of the remote Docker. Sort of like I create a tunnel between this port and this one. This means that if I send a package to the 1337 of my client machine, the SSH connection will forward it. This is why it's called port forwarding. Will forward it to the 7777 listening on the Docker. So essentially, that's the big idea. Now, how do I do that? This is the first example, local port forwarding. So this is the code we analyze. This is the way like we can access the machine from within the Docker. However, notice that the application only listens in the local interface. How can we reach that interface from the outside? So the idea is to use SSH, and we want to do a local port forwarding, and we can do this with the option -L, so capital L. So essentially with this we are saying connect the local port of the attacker 1338 to the remote port of the server, to the remote endpoint, not port, endpoint, because there's also an IP address. This is IP and this is port. So connect the local port 1338 of the attacker to the remote endpoint 127.0.0.1.7777. And once we do that, our localhost 1238 will be connected to the localhost 7777. This means that we will be able to access the web server running on the container with this curl. So notice here that here I'm doing this on my attacker box. I'm saying on my attacker box, go into the localhost interface into port 1338. Thanks to the port forwarding done by SSH, this will actually go to the localhost of the remote server into port 7777. So essentially, this is how it works. It's just two simple commands. So we quit the previous connection, we proceed with the local port forwarding, we connect, we put the password, and now notice here we have to specify the 1338. And notice now that I'm able to reach the target, and I'm able, let's do an hostname, I'm able to execute code within the Docker container. Notice the hostname is the same. So how did I do that? I did that because now my attacker box is connected through port forwarding to the remote endpoint that is running on the Docker, even though that remote endpoint is essentially a local endpoint because I connected it with SSH. So this is the syntax for the local port forwarding. Notice here that I'm not specifying the IP address of the attacker. This is because it is implied that it is 127.0.0.1.1338. So I can also make it explicit. So I can do this way essentially, ABC123, and it's gonna work the same. Notice I get root, and here I get hostname. So the full local port command, if you want, is essentially, it has the following structure. In the L option here, we are specifying two particular endpoints in the connection. The first one is the attacker/client endpoint, and the second one is the server endpoint. So we are saying connect the endpoint 127.0.0.1.1.338 to the server endpoint 127.0.0.1.777, so that all the packages that go towards this 127.1.338 from the attacker machine go into the server local port, localhost port 7777. So essentially this is the first technique. Now in this case it was pretty trivial to exploit the code because it's not really that interesting, the code itself. But just consider, for example, that you have, for example, a debugger listening on a localhost interface, and you want to access that debugger because it will allow you to perform privilege escalation. So if you have a situation where you find like local services, for example, as follows, you do a netstat and you get, oh look, there is a server listening on port 7777, but it is only in the localhost interface. I want to be able to access it from the outside. No worries, you can just do port forwarding. In this case, it is a local port forwarding because we are forwarding traffic from the attacker machine to the server. So from the attacker to the server, and essentially it's sort of like we are being able to access services which would normally be only available to the localhost, to the local network interfaces of the server. This is done thanks to SSH. SSH acts as a port forwarder because it uses the same connection that we have to the machine to forward the ports. So it's a very powerful feature of SSH. And so this is the first example with local port forwarding, where, as we said, it redirects traffic from a local port on the client machine, which is the 127.0.0.1.1.338, to a specified port on the remote machine, which was 127.0.0.1.777. And by doing this, we get access to the local services of the remote host. Notice here that the port we choose for the attacker here, for the attacker machine, is arbitrary. We can specify whatever port we want. There is no constraint. The only constraint is on the server endpoint, because the server is specifically listening on that point on its own interfaces. So for example, if you go back to the previous example and we connect but we use a different port for the attacker, let's say we use 4444, it will still work as long, of course, that we use the right port when we connect to the server. So if we do 1238 like this, it's gonna be like, look, I have no connection, so we have to put 4444. But this one we choose on our own. We can choose arbitrary with all the ports that we have available, so there's really no issue there. And so this covers the first example, which is of local port forwarding. So now we can focus on the second example instead, which has to do with remote port forwarding, which is a similar technique. It's just that it reverses the role of who is the client and who is the server. So it just flips the roles. So I have built a Docker for this once again. All this data will be available in the description, so don't worry, you can just follow along. And here we can start the Docker. So we're gonna start the Docker, and once again we can connect with SSH at the same 1237 port. So we connect, we have the password ABC123, and we get access to the system. Perfect. Now, if we check with netstat, notice that we have no server listening on these particular ports. Okay. The actual code in this example is a little bit different, because now we will not simulate a server listening on a local port. which means that we have no server that we want to reach. Rather, we will simulate a client. Now, in this second example of remote port forwarding, we will not have a local server on the remote Docker container. Rather, we will have a client on the Docker container. And this client will connect to a localhost interface on its own interface. So it will connect to the localhost 127.0.0.1.4.4.4.4 interface, and it will, essentially it will receive a command from the server, and it will execute the command it receives. So here we connect with the socket, then we say, okay, let's receive 1024 bytes, then we split the data we receive with white space, we check if the first element is CMD, and if it is CMD, we execute the second element, and we give back the result to the server that sent us the command in the first place. So, for example, and with in the configuration of the remote machine, we can do a sudo -l to say, look, with no password, you can execute this usrbin python3 app. So we're gonna do this command. We can execute it with sudo. So it says, look, problem during communication, connection refused. Why does it give us this problem? Well, the idea is that the first thing it does, so this is the globals, here are the libraries, this is the main guard, and then we call main, and main tries to connect with the socket. If there are problems in the connection, we just print an error, problem during communication. In particular, here it says connection refused because currently there is no listening services on the remote server. There is no services that is listening on port 4444. So we are not able to exploit this because it just crashes. How can we make it not crash? Well, there could be different ways. The first way is to start our own server in port 4444 directly from the container. So directly from the container here, somehow I start a server in the endpoint listening on 127.0.0.1.4.4.4.4, and also I create a malicious server that sends the command I want. So this is a way we could handle this case. For example, this could be done with netcat, but we do not have netcat in this machine. There could be other ways. However, the way that I want to show is through port forwarding. Now, in particular, this time, we will not forward a client, we will forward a server. That is, like we will use, so with the remote machine, we can execute the script. So the problem is that we cannot create a local service listening on that port. Now, to solve this other problem, notice that this is a different problem, because now we have a client on the remote machine, and we want to give to the client a proper server. We want to forward the server, essentially. So to solve this problem, the idea is to use remote port forwarding, which allows us to connect the Python script TCP client with a remote service that is running on our machine. So while with local port forwarding, we get access to services that are running on like the internet, that are not exposed to the internet, however, with remote port forwarding, we do the opposite, essentially. We expose our server to clients on the internet. So that's the idea. It's just reverse. It's because we are using the client-server model. We are assuming that the client connects to the server. So with local port forwarding, we connect to new servers. With remote port forwarding, we are exposing servers to new potential clients for new connection. So how do we do that? The idea is literally the same. So we say, look, I'm going to expose with remote port forwarding my local port 4444, and I'm going to expose it to the remote port 1338. So the syntax for the remote port forwarding, now in the first section of the command, we actually have the endpoint on the server, and on the second part, we have the endpoint on our client. So the idea is that the first one is always the client, the second one is always the server. So the way we do it essentially is that we connect with SSH, then in our host, we set up a server listening on port 1338, and then we are able to connect it from the machine, from the client TCP running on the container. Because when the client TCP will access its own localhost 4444, thanks to port forwarding, that endpoint will be connected with the our localhost 1338 with the 1338 of our localhost machine. So how do we do this? It's pretty simple. First we connect with SSH, so we quit the previous connection, we connect like this, and then we put ABC123. Perfect. At this point, let's check the ports here. Notice that we have here, we have this local service that SSH has just created, 127.0.0.1.4.4.4. So now the client will be able to connect to this port in the localhost, to port 4444. Of course, at this point on our end, in the 1338 port, no service is actually listening on, so we will still have the same problem. Like if we just do this, we're still gonna have the same problem. It says port failed, right? So we're gonna have the same problem. However, notice, if I just now start to listen on port 1338, so now I just set up my server. With the remote port forwarding, my server is exposed to more clients, and in particular now I launch the script on the Docker container, and look, I got a connection from the client in the Docker container towards my server. At this point here, I can send to the client the command cmd who am I. The client will execute it and it will give me root execution. It will say, look, I am root. I can start up a new session. I can connect back and I say hostname, and it's gonna give me the hostname of the Docker, which is f03f1555.0f86. So the idea now is that we are not using the clients to connect to more servers. We are exposing our own server here, which is a simple netcat. It's a simple TCP server that is just a dump server that does nothing, just what we tell it to do. And then we are able to connect it, we are able to connect to this server through the TCP client because we had forwarded the ports before. Like we do connection, and here we can do whatever we want. So it says, of course, no such file or directory, it has a problem, and so on and so forth. So the command for remote port forwarding is /r. Here I have to put, here I can put the full endpoint on the server, and after the semicolon here, so it's like, once again, I have 2 endpoints to specify. If I don't put the IP, it's gonna assume it's gonna be the localhost IP, so 127.0.0.1. So this first IP is the endpoint on remote container. The second is endpoint on my host. And I'm gonna connect this particular endpoint to this other particular endpoint. But now the flow of data is inverse with respect to the local port forwarding, because now data flows from this port 444 to the 1338. So before it was from my host to the remote server, now it's from the remote server to my particular host, because actually my host contains a server. So that's essentially the idea. And essentially that's it for the local service exploitation. Just remember these 2 techniques. Ask yourself if you need to access remote servers, then do a local port forwarding, choose an arbitrary port on your machine, and select specifically the endpoint where the remote server is listening on. It could be also another interface. Make sure to remember this. It's not always localhost. The remote server could listen on a very specific interface, and you're able to access this interface thanks to local port forwarding. This is the case when you want to access a service that is a server that is running on a localhost interface or any other interfaces that are not exposed to the public internet. The case of remote port forwarding is less common. I would say the most common case is local port forwarding. The case for remote port forwarding is less common because the idea now is that we want to simulate a server. We want to trick the client into connect to a server we own. So in this case, we sort of like we're doing the reverse thing. And in this case, we need the remote port forwarding with the /r. So here we select the port that the client tries to connect on. So we are bound on this parameter, and then here we can put an arbitrary port. We can put a server listening on that port on our localhost interface, on any interface that our particular computer can access, and we will connect the client from the remote container into our own server. And this could be used for exploitation. Like for example, you have a client that expects data from a database. You can sort of like trick the client into believing that the data it's receiving is valid, while in reality it is receiving it from your own malicious database. So this could be an idea to use. The most common case, however, especially for privilege escalation, is the local port forwarding case. You get into a server with SSH, you check the local services, you see, look, some service is running, maybe it's vulnerable, maybe I need to access it from my host, and then you do local port forwarding. So, I hope the video was enjoyable. If it was so, please leave some feedback. Tell me what you think. Tell me if you ever tried these techniques or how you tried them, if they worked. Share this video with like-minded people to help me grow, and that's it. See ya to the next video. Hi and welcome to this new video in which I continue my Linux privilege escalation series. In this video we will focus on a specific type of exploits which are known as binary exploit. So we're gonna talk about binary exploitation, and I will show a really simple example of a buffer overflow on a 32-bit application. So essentially, we have this simple application which is vulnerable to a buffer overflow because of the way that the strcopy function is used. Here essentially we are copying from the char input, from the buffer input to the buffer as a local variable. We are copying the value, but we have no check to make sure that this pointer points to less than 512 bytes. So this is a typical buffer overflow situation and we can exploit it. I will show the assumption we will be working with, an analysis with GDB, and the final exploitation step. During the video, I will also be working on a Kali Linux machine, this one, where we have all the laboratory to show the buffer overflow. So here we have the vulnerable.c, here we have the genpayload.py, which will be a Python script used to generate our final exploit, and here we have another shellgot.c example. So we can compile the program with this gcc command. Notice that it has a bunch of different flags, and these flags are used to remove certain protections. The objective of this video is not to introduce to you modern binary exploitation that bypasses all the modern mitigation, but rather to just give you the intuition, the idea behind binary exploitation, and why it is important to consider in the context of privilege escalation. So we can compile our program, and if we just execute the compiled program, look at this now, we have vulnerable.c, which is the file I showed previously. It's a simple file, and then we have compiled it into the ELF binary. It's an ELF 32-bit binary, and we can execute it. So we execute it. Of course, notice that in the main function, we check the arguments. If the arguments are not greater than 1, we do not do anything. That is, we only execute the vulnerable function when we have at least one argument. Actually, at least 2 arguments, because the name of the program is always the first argument in the argv array. So if we put, for example, AAAA, we execute it again. Now we trigger the vulnerable call, so this code actually is executed, the vulnerable here. But still, notice how nothing happens. Even if we just do it with a longer argument, we can keep sending stuff, but essentially nothing happens. And why is this the case? Because when we call vulnerable, when we reach this function, we have a certain input, which is a pointer to a char. So essentially this points to our arguments like AAAA. So specifically, it's this string in the memory of the program, right? And then we just perform a stir copy. And this stir copy takes the memory from the source, which is the input, and copies into the destination, which is this buffer. So this is the output. Now here the vulnerability lies in the fact that this output has a certain fixed size, which is 512 bytes. However, no check is made to be sure that the input is less or equal to this size. This means that it is possible for me to give, let's say, a 1024 bytes input, and what happens is that I will run out of space in this buffer, so all the memory for this buffer I will run out of space with a bunch of A's, and then essentially what I'm gonna overwrite in the memory is I'm gonna overwrite critical control structures that are used by the processor to handle the control flow of the program. And we can see this in action how? By just calling the binary with a very long string as input. So let's put like a lot of A here. Let's put like even more than this. Let's put like a lot. And notice what's happened now. We get a segmentation fault. We get a memory error because the processor in the execution, it executed this string copy. So it copies this huge string into the memory, and this overwrote all the memory for the buffer, and then it went overboard. It went into an overflow. So that's the idea. When we have binaries like this, which look like they do nothing, like in this case, but are actually vulnerable to memory corruption vulnerabilities such as buffer overflows, sometimes it is possible to take these binaries and use them to hijack the control flow of the program in order to introduce malicious code. In this case, for example, we will develop a very simple payload, a very simple exploit essentially, and we can see the bytes of the exploit in this payload.bin file. If we just analyze these bytes, we will see essentially, we can do this with the flag b, so we get all the bytes of the payload. We see a bunch of bytes 90, so all of these are like 90, 90, 90, 90. Then here we see a bunch of different other bytes, and at some point we see a bunch of bytes repeated, E0, D4, FF, FF, E0, D4, FF, FF, repeated many times. So that's the general structure of our exploit, and in this video I will show why we built it that way. Now, what can we do with this sequence of bytes? Well, the idea is pretty simple. So we said that this binary is kinda naive, like it just does nothing, right? But in actuality, it's really pretty dangerous. If we give in input this payload, we can do this with this flag, with the shell substitution syntax. Notice what we get now. We get a shell. We get a shell as the user who was executing this program. And so a binary that at first glance is not really that dangerous can actually be used to execute arbitrary payloads with a shell. For example, in this case, you can execute UMI, ls, and so on and so forth. Now, of course, in this specific case, we obtain a shell as the user Leo, because the process running the binary was executing at this particular user. Now, this can be more dangerous, for example, if we have a root-owned SUID binary. I've already made a video describing the SUID exploitation. For example, if we have a binary that is owned by root and that it has the SUID bit on, then once we're able to hijack the control flow of the program and we're able to introduce arbitrary instructions, we can just execute a set with d to 0, and then we can execute a bin sh, and we will obtain a root shell. So essentially, this can be extremely dangerous depending on the configuration of the system. And all of this is to say that another road that brings us to privilege escalation in a Linux system is the exploitation of specific binaries, of specific programs. Now, typically, this is an hard path to follow, because in this video, I'm gonna really show a simplified version, a simplified exploit. Typically, modern binary exploitation and research is really hard. However, it is important to understand that this path exists, that binaries can be hijacked, that the control flow of a program can be hijacked, and I will show a simple way of doing it. So, I hope the video is enjoyable, I hope you get something out of it. If you do, leave some feedback, subscribe to the channel, and share this with like-minded people to help me grow. Thank you and enjoy the video. So we already saw the code essentially, I already discussed it. Here we have a bunch of C libraries, here we have two functions, a main and a vulnerable. The main makes sure to call the vulnerable when we have at least two arguments, and here the check is made on argc. Now when we run the program through the shell, for example in this syntax, we do -- name of the program and then the input. This array of arrays, it's sort of like an array of strings, is filled up with these arguments. So the first element is going to be the name of the program, /vulnerable. The second is going to be the AAA. And of course, remember that in C, the arrays are indexed from 0. So this is going to be index 0 and this is going to be index 1. This means that when we check the argc is greater than 1, we are checking that there are at least 2 arguments, and then we are giving to the vulnerable function the second one, which is this AAA. So to the second one, the input is going to point to the AAA string here. And then we will simply perform a str copy. So str copy is used to copy memory from one location to another location. In this case, we have a buffer which points to 512 bytes of memory. This is like uninitialized, so it could contain anything that was in memory. And we want to copy it. Essentially, we want to say, okay, now I want to copy this string into the buffer. The problem arises when the string we are copying is way too big compared to the destination buffer. If this is the case, then we will copy the entire string, we will finish the size of the buffer, and then we will overwrite critical data that is used by the CPU to handle the program. So this is the program. Now to compile it, we actually have to use various different flags. Let's review them. So the -o is just to specify the name of the output. Here is just the name of the source code, vulnerable C. The -g is to add the debug information to the build, so we can debug it with GDB. And then these different flags are used to, so the -m32 is used to do a 32-bit compilation. So why 32-bit? Well, the idea is that 32-bit application and 64-bit application works differently. 32-bit is a bit simpler just because the addresses have less bytes. They only have 4 bytes because we are working in a 32-bit memory, essentially. But honestly, even in 64-bit, it's not like it changes so much. I mean, some things change, so it's a little bit easier to do buffer overflow exploitation in a 32-bit system, but many of the ideas, they carry over to 64-bit with certain adjustments. So that's the idea. We compile it and then we execute it. So the question is this program safe? So is this program safe? And the idea is that no, it's not safe, because it suffers from a very well-known memory corruption bug, which in this case is the buffer overflow. How can we notice it? We just give the program a big enough input, long enough that it will finish the space we have for buffer, and it will overwrite the critical sensitive area after the buffer, and then we get a segmentation fault. So if you have a C program and you give it certain input and you get a segmentation fault, most likely you have a memory corruption error. This should not happen in a safe program. If you get a segmentation fault, something has gone wrong and it could be dangerous. So this can be considered a vulnerability. Of course, to go from vulnerability to binary exploit, it takes a lot of research and a lot of work. It is all about making sure that the condition that this bug arises are completely controlled, and they are controlled in a way to not only crash the program, we don't want a crash, but rather we want to hijack the execution of the program into a new direction. So if the program was going its own path 1, we want to introduce an input that makes it go astray, but then we want to control where it goes to obtain a code execution, to obtain a code exec. So this can be very hard to do. In this video, I will show a really simple example. So this is not modern binary exploitation. It's extremely simplified just to make sure that it's okay for this series, because this series is about I would say initial content on Linux privilege escalation. So it's good to talk about buffer overflows. Specifically, why is my approach simple? Because I make a lot of assumptions. So in this video, we will analyze a very simple exploit. This is because we assume to be working in a very simple model that does not have the protections that modern systems offer regarding memory corruption. Now, these protections in particular are the following. We do not have a non-executable stack. This means that if you consider the memory for a program, it is divided in various sections, and the stack is the area of the memory, the region of the memory, the section of the memory where local variables live. For example, if we go back to the code, this buffer variable lives in the stack frame of the vulnerable function. So the stack frame is created every time the vulnerable function is called, and in the stack, if this is all the stack, right? If this is the stack frame is a chunk of this stack. This is the stack frame of vulnerable. If you call other function, you will have other stack frames. Well, typically what happens is that in modern binaries, the stack is non-executable. This means in particular that when the CPU tries to fetch instruction from this particular memory, from this particular region, it will get an error. It will throw a sort of like exception because it will realize that it's fetching instruction from the stack area and the stack is non-executable. You can configure it to remove this protection, and we have removed it through this essentially this flag -z exec stack, which means make the stack executable. Another memory protection is that we have no canary value. Now the canary value is used after the stack frame of a function, so it's like a special value here, is called canary, and it makes sure that in the context of a buffer overflow, the buffer overflow would naturally also overwrite the canary with a new value. Well, after the function is over, the canary is checked to make sure that no one has overwritten it, and if someone has, then the control flow is interrupted because a smash stacking attack has been intercepted. So the idea is that if you modify the canary through a buffer overflow, the operating system realizes that and does not make you go forward with the attack. So this is another thing, and we remove this with the flag here, with the compilation flag -f no -stack -protector. So we remove the stack protector, which is the canary value. Then another thing, another assumption we make is that we work in a 32-bit architecture. This is not like it increases or decreases security, it simply changes the way things work. In a 32-bit architecture, for example, the arguments are passed to the stack. So when we call a function, like for example the vulnerable function, these arguments are all passed within the stack. While if you use a 64-bit architecture, for example, the arguments are passed through CPU registers. So this is the idea, but honestly it does not change too much, this change from 64 to 32. It's just that to simplify, 32-bit architecture have just less bytes per address, it's a little bit simpler. And finally, this no ASLR, essentially, this has to do with the randomization of the addresses. So in modern Linux programs, essentially, every time the program is executed, the kernel randomizes the layout of the memory. It means that the position of the stack will be random for every execution. All the addresses within the stack start from the same offset, from the same base, sort of, but the position of the base will be randomized at each startup. This protection is useful against exploits that makes use of specific memory addresses. Like if you say you have this function in memory address 0xFFFF D788 or something like that, if you use an hard-coded memory address with ASLR, the exploit won't work. To simplify things, we will disable it. To actually disable it, you can write into the kernel file /proc/sys/kernel/randomize via space. You can write the value 0, and this will disable ASLR all over your system. So be careful, only do this in a test system like a virtual machine, because it could be dangerous, it could decrease the overall security of your system. So while the basic idea behind binary exploitation does not change if we are in 32-bit or in 64-bit, if we have the canary on or the canary off, if the stack is executable or not, so the basic idea is the same. However, what changes is the way in which it is performed. And the way in which it is performed nowadays in modern system is drastically different, as one has to deal with all of these new protection and countermeasures and mitigations. For example, if you have SLR activated, to actually use addresses, then you need some sort of like address leak to understand where things are within the memory layout and things of the sort. I mean, for every protection, there is a countermeasure most of the time. It's just that it adds the complexity and sort of like the constraint with which you are working with. So making assumption in this case simplifies our life. and these are the assumption I made. So we can get out GDB. I've already made a video on GDB, so go check that out if you have no clue about GDB. I will not talk too much about the tool. I will just assume you know how it works. If you have no clue, as I said, go check out my previous video where I discuss how to use it. So we have loaded the binary GDB. The first thing we can do is just list out the functions. As we can see, we have two functions in the vulnerable.c file, which are main and vulnerable, so nothing new there. At this point, we can check out the code for the main function, and I'm not talking about the source code, because we can already see that actually. I mean, this is the source code, so nothing new there. I'm talking about the assembly code, the code that is actually executed by the CPU. How do we get that code? We can use the disas function of GDB. So we can do disas main, and this essentially is the code for the main function. So the interesting things of this code are, as always, the typical, the initial of every function is a prologue. This is the prologue, where we just create space in the stack for the function. Then we call something regarding x86. I'm not sure if this is for 32-bit compatibility, not really sure about that. And then we start to check for the argc value. We check if it's less than 1, jump less equal, is jump less equal. And if the check goes through, if it is not equal, then we do the call. So we do this push, and then we do the call to vulnerable. So here we push the value of the register into the stack, and this is the first argument of vulnerable. And since vulnerable only has one argument, we just call the function vulnerable. So we don't need to care about the details of all the other assembly code. Here the main idea is that, look, we call the vulnerable function, and then after the vulnerable function has finished to execute, we will come back to the main code starting from this like address, starting from the instruction main plus 51, this add esp 0x10. So that's the idea. So this is the code for main, and we can do the same for the code for vulnerable essentially. So also for vulnerable, we have the prologue here, these first values, and then essentially we have the call to the string copy. So here we get the arguments from the stack, and then we have the call to the string copy, and then essentially we have the return final value. So that's the idea. Very simple assembly. I mean, we will not delve into the assembly. This is not going to be a video about assembly. I can make later a video about that. What we are interested in is the main flow of the program, and it's really, really simple, as we can see from the code itself. Now let's do a run of the program, but when we do a run, I want to check essentially how the stack changes depending on our input. So in particular, I will be interested in putting a breakpoint in this, before this particular instruction, before the call to the str copy. Why? Because before the call to the str copy, the stack is valid and it has all the bytes that typically it has. After the call of str copy, we will have copied our long string, all the bytes, which means that we will have disrupted the stack structure. So I just want to understand how it all works. I can put a breakpoint with vulnerable plus 35, with this wildcard, with this asterisk to reference the address here. And then I can say run. So here I run. Notice that if I do this as main again, the address I get here are different from the initial address that I got here. This is because at this point the program was not loaded, so these were the static address present in the elf binary file. After the process has been run and loaded, so like loaded and executed, this address get loaded into memory, so they change. And specifically, the return address of the vulnerable call, which is the address after the call to vulnerable, before it was 0x0000. Now it is 0x565561f4. No, actually it's this one, f1. So it's like 0x565561f1. Now, why is this address important? Well, consider this. If we disassemble the vulnerable code here, we have no information regarding the place in the code where we have been called. I mean, if you consider a point of view of the CPU while it is executing the instruction of vulnerable, like let's say here, this function, the CPU has to know where to go back, right? Because it's going to execute all these instructions, and then at some point it's going to do, okay, now I return to the place I come from, right? So we were called in main. After vulnerable, I have to go back to main. I have to go back to the function that called me. Now, where is this information saved? This is a critical question, because depending on where it is saved, a malicious attacker could manipulate that return value, could manipulate that address that specifies where execution should return to. Now, where is this variable stored? It is actually stored in the stack. And we can see that how, well, first of all, how we can analyze the memory of the stack. We can use the GTB command X. We can do, like, for example, X 10 WX $ESP to get the no register. I think it's because it has to run. So, okay, it has to run with some arguments like A. Now I am in the breakpoint, and now I can analyze the stack memory. So in this case, I'm reading 10 words, which is 10 sequence of 4 bytes each, starting from the register ESP, which represents the end of the stack. So essentially the stack starts at a given address, and then it grows downwards towards higher addresses. So essentially you can say that actually the stack grows towards lower addresses, but when we read it from a given address towards higher one, because we are reading the previous stack, all the stack that exists so far. And it grows, it expands towards lower addresses. So for example, in this case, I'm reading 10 sequence of 4 bytes each, starting from the address 690 towards 680, towards 6B0, and so on and so forth. Now, to actually understand where this saved address it is, which is actually this one, to actually see the saved return address, we can just read enough bytes from the stack. Like for example, in this case, 128 should be enough. And if we just check this particular number, we just check it among here. So let's see. Okay, there is no such number, so we probably have to check a bit more. So let's say 138. Notice that what we got now. We got, essentially, at the end, so technically the last one is 136. We just care about 136. But notice this value, which is present in the stack, because what we are seeing here is all the memory present in the stack. At some point in the stack, we see this saved value. This saved value represents exactly where the processor will look for to understand where to go next after the vulnerable function has been executed. So this means the processor executes all the instruction here in vulnerable. At the end, the last ret instruction simply reads this value from the stack, and it starts to execute the next instruction from this particular address. So this is where the concept of control hijacking comes in, because if you're able to do a buffer overflow, if you're able to overwrite all these bytes, and you're able to change this saved return address to an arbitrary value, we will be able to control where, like, the CPU goes back to fetch new instruction. So essentially, that's the idea of our exploit. So this is the state of the stack before we write any value. Let's write the value with the next instruction, and let's read once again the state of the stack. Notice that we wrote a bunch of 414141 bytes here. So before, let's see, so before the address 680 was empty, 0000, now it contains 41, 0x41, 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 which in hexadecimal, this is just the ASCII encoding for A. So since we write AAA, we got the 414141. For example, if instead we were to do AAAA, BBBB, CCCC, DDDD, and we run again, we check the state of the program, of the stack before writing, we write with the next instruction, we check after writing, notice how it changed. So before we had all 0 here, and now we have 41, 41, 41, 42, 42, 42, 43, 43, 43, 44, 44, 44. So we can control the memory that is written starting from this address. Now with this view, it's also easy to understand why buffer overflows can be dangerous for a program. Because what's the idea? Well, the idea is that remember that this value at the end here is an important one because it is used by the CPU to check where to go next. But if you are able to write this value up here, and if you are able to write more bytes, which means that we're gonna write the third row, the fourth row, and we're gonna write all these rows, all these rows, all these rows. If there is no check on our length, if you can just keep writing and writing and writing, if there is no boundary check, at some point we will be able to write a value exactly here. And when we change this address, it is exactly when segmentation fault happen. It is when we change this address to an invalid address. What happens, however, if we change this address, but not to an invalid address? What happens, for example, if we change this address to an address that points to the stack? Well, this is exactly what we will do. And to quickly compute how many bytes we need to write in order to overwrite this save return address starting from our position in the stack, which is this address, well, what we can do is we can start from this address. And what's the address of this value? Well, we start from the column, which represents the address of the first column here. It's like this address, the FFFFD890 is the address for this. We add 4 more bytes we get here. We add 4 more bytes we get here. We add 4 more bytes we get to the start of this one. So the start of this is the address, the value, this value with the C at the end. So if we just check one word of memory from this address, we get essentially the saved return address. We start from this, and then we simply subtract. We do print decimal the initial one, which is this one, which is this value. And notice we get 524 bytes. So we have 524 bytes if we want to overwrite the return address. So let's check our assumption, right? How can we do it? Well, for example, we can compute with Python. So Python C, I can do print A times 524 plus B, so 4 B's. And I get a certain string, I get this particular pattern. Then I can run the program with this particular pattern. I can write into the stack with next instruction, and I can read the content of the stack. So notice that I was able essentially to write everything, but now here the save return instruction is for true, which means that it is no longer valid. If I now continue the execution, it's gonna say, look, program has a problem, a segmentation fault, because it's not able to understand the instruction. Like this address does not point to anywhere in the system, and this is a problem, and so we have a segmentation fault. But what we were able to do is show that we're able to control exactly the value that we write into the return address, which is a critical point in binary exploitation of this type. Now, the particular exploitation technique that I will follow is to use a so-called NOPASSWD. So essentially the idea is that the processor has different opcodes which define the kind of action to execute upon reading an instruction. So when we have an opcode of 0x90 and the CPU reads this instruction is called NOP because it stands for no operation. It means essentially do nothing. Process the instruction, but do not take any action whatsoever. It's called a NOP instruction. So the idea is to use this NOP instruction as padding. Now, why they are useful? What's their usage? Well, the idea is that we want to write into the return address an address in the stack. But the problem is that we also want to write a specific shellcode, which we will discuss in a bit what it is. The shellcode essentially is just binary instruction that the CPU will execute. Now the problem, however, is that if we jump in the middle of the shellcode, this will break the logic of the shellcode and therefore will make our exploit not work. So we want to start execute the shellcode from the first instruction of the shellcode. This means that we need to know exactly where the shellcode will be in the memory, and this knowledge sometimes is really hard to know. So what can we do instead? The idea is just to have a return address which is roughly around the shellcode area, but not exactly to the start of the shellcode, as long as it hits the NOPASSWD, which is made of all 0x90 instruction, which is the 0x90 byte. So as long as we hit one of those NOP instruction, we will go down the NOP instruction, we will keep executing them until we hit the shellcode. And so with this setup, with the usage of the NOPASSWD, it's gonna be easier to hit and run our shellcode. So essentially, this is the idea, this is the stack, this is where we'll start write. We'll write a lot of NOPASSWD, then we will write our shellcode, and finally we will write a lot of new return address. This is just the same address repeated, and this address will point to the stack area and hopefully to the NOPASSWD. We will do a little bit of guessing to guess this new return address. Of course, for example, in this case, we are assuming no ASLR, because if there was randomization, then this new return address could not be computed by hard coding it into the exploit. It would have to be computed at runtime depending on the specific application. So it's like we are simplifying our life here. And so that's the general idea. Now, though, to continue going forward, we need to talk about shellcode. So roughly, what is the shellcode? To understand the shellcode, we can see this simple example in C. I actually do not remember where I took this shellcode. I did not write it on my own, but I forgot where I took it. So if you remember, if you recognize it from elsewhere, please write to me in the comments and I will put a reference in the description. So forgive me for that. But essentially, the idea is this. The CPU, when the CPU executes single instructions. Now, typically, these instructions are wrapped into binaries, like for example, elf binaries. And the elf binary is just a wrapper around the code and the data. Now, when we talk about shellcode, we're just talking about raw code that the CPU will execute. So if the CPU starts to execute this first instruction, it will understand how many bytes to read, and then it will decode the instruction, interpret it, and execute it. And this is all to say that the shellcode is a byte representation of the code that can be executed by the CPU. We put this in memory, we inject this into memory, we point the CPU to execute that code, and then we have our code execution. So the idea is to introduce code execution through the usage of shellcode. So this simple C program defines a shellcode as an unsigned char, then we print out the length of the shellcode, and then using a function pointer, we executed the shellcode. So how can we compile and test it? Well, the idea is that we can open a new shell, we can go into tmp bof, we can compile this shellcode, so we have the shellcode, and we can test it out. If we execute the shellcode, we get a simple shell. This is the same payload that we have obtained execution when we do cat payload.bin. Because at the end of the day, the idea of our exploit is to introduce within the memory of the vulnerable process exactly the following shellcode. And if you look at the payload itself, if we just look at the payload, like in here, hexdump cv payload.bin, and we make it more readable, we see that after the NOPASSWD, so let's see here, so the NOPASSWD ends roughly here. And then we have an EB1F5E89. And notice the shellcode here, EB1F E589. Of course, since this is C, in C, the raw bytes are written such as /x and then the byte itself, the hexadecimal representation of the bytes. So EB, so the first thing is EB1F, then continuing 89. After we have, so like EB1F89, then we have 768031. So 768031. So these 3 bytes correspond to these 3 bytes of our exploit, because the structure of our exploit, as I said, is we have the NOPASSWD, which is all these 90 bytes. So this is all the NOPASSWD. NOPASSWD. Then we have the shellcode. We have the shellcode, and at the end, so this is all the shellcode, and then we have the new the new return address. So the return address that we use to overwrite the old return address, and this value will be used to hijack the control flow of the program. Now, how can we generate this payload? There are many ways of doing this. I will show a very simple way using a Python script. So this is a Python script that uses Python 2.7. This is an important difference, by the way. It's not Python 3, it's Python 2.7, and this is because of the way that bytes are handled in Python 2.7. If we execute this script with Python 3, it's gonna complain. It's gonna say, you cannot concatenate a string to bytes. If we do it with Python 2.7, no problem whatsoever. So this is really good. So here I use the struct, and I don't even think I use the sys function here, so I can remove this import. So I just use the struct library, and this is used to pack stuff, but I will talk about that later. So this is a simple guard to execute main only when we call the script from the command line, and this is the main function. So here I define a bunch of things. I define the shellcode taken directly from the shellcode.c file. So just copy and paste the shellcode and it works. Here I have the offset, which we computed manually by taking into consideration the amount of bytes that exist between. So let's do a run here, simple run. I do a run here, and then I do next instruction, and then I print all the stack to make sure we see the return address. So this 524 or 26, what is it, the value is 24, was obtained by understanding how many bytes separated the saved return address, which is saved here in this, from the first address of the stack that we can write to. How did we get this number? We just printed this value with the final letter, not 0 but C, because the 0 is for the first column. For the last column it's C, minus this first one with 414141, and this equals to 524. So this is the offset value we use, and then we have the amount of times we want to write the new return address. And then we find the return address. So this value is hard-coded, and this means that this only works because we have disabled ASLR. If I enable it again, it's not gonna work because this address is gonna change every time. Now, how did I obtain this address? Well, a bit using GDB and a little bit by trying with simple values. So the idea is that with GDB, we get roughly where the stack area is when we debug the program. For example, we know that ff d something, we're probably around this area. Now, the particular number after d, however, I picked manually. Why? Because when we use GDB, we are modifying a little bit the memory layout, the memory area. So the stack is a bit different, which means that without GDB, few numbers, the few remaining numbers of the stack could change. I just moved a little bit. I tried 5, I tried 4, and 4 worked, and that's it. So like the idea is, you pick a number with GDB, and then you try a bunch of values manually to see the one that works. You can also write a little scripts that automates this stuff. This is not really important for now. It's just to show that you need this kind of information. But in this way, in this naive way, this only works because we have disabled ASLR. Then we actually write the payload, this buffer value. So this is where the payload we write, and this payload is then written into the payload.bin file. Remember to open this file in a write mode because we need to write stuff, and also in binary mode because we need to write raw bytes. So that's it. And with respect to the payload, it's really simple. First, we write the NOPASSWD, then the malicious shellcode, then we write some more NOP instruction to make sure that the new return address value is properly aligned in memory, and then we write the new return address. Now, why do we do this thing, this memory alignment? Because, for example, if the shellcode ends, but it is not really aligned in memory, so for example, let's say it ends here, it means that the final byte of the shellcode is here. The new return address is gonna write these 3 bytes here, and then a single byte here, and this is gonna totally mess up the memory. So it's not gonna work, and we're not gonna be able to control the return address, because the return address has to be aligned at a specific offset in memory. So we just do this to make sure that it is aligned. So essentially, that's how it works. We can just execute it. So we can just remove the previous payload. So I remove payload.bin, I execute with Python 3 the generation of payload, and then I try it with the vulnerable program. Payload.bin. So let's see where is payload.bin. I do cat payload.bin, and notice that I have a working shell. So for example, in this case, I have enabled once again ASLR, just to show that now it will not work. Randomized via space now is the value true, so it is enabled again. And if I try the exploit, it's just gonna give me segmentation fault. To make sure it works, we have to disable it. If I disable it, like this, with echo 0, proxies, kernel, randomize via space, and I execute again, notice that it works. So make sure if you try this on your own that you have disabled ASLR. With respect to this return address, use GDB, understand where the stack lives, and try to guess the last values here, the low-end values of the address. Like just try with the one right after this thing, the FFFFD, and it should work. So this is the idea. We can sort of like hijack the execution of this program and obtain from a process that would not do much, that would not do anything, we can obtain a full shell. And with this shell, we can do anything we want. So essentially, that's the idea. And in here, you can find the script for the generation of the payload and the final payload itself. So if you have any problem trying this on your own, just write in the comments and I will try to support you. So what are the takeaways to conclude this video? The idea is that while the binary exploit shown in the video is extremely simple, the same idea can be applied to modern binaries with all the latest protections. Indeed, all these protections with enough work by researchers and with certain assumptions, sometimes it happens that this protection can be bypassed with appropriate techniques and primitives. Which means that the biggest takeaway is that sometimes the binaries present in a system can be vulnerable to binary exploitation for a variety of reasons, including memory corruption. This in turn can make it possible to hijack the execution flow of the binary in order to execute arbitrary code, including malicious code. And this means that exploitation of user space programs can also be a path towards privilege escalation. And here at the end, I use a specific word. I said user space programs. So what I showed today was binary exploits, binary exploitation of user space programs. The idea is that, is there another type of binary exploitation? And actually there is. It is the exploitation of kernel programs, of kernel binaries, of kernel space code. So not really kernel binaries, but of kernel space code. So that's the idea. And in the next video, which is going to be the final for the Linux privilege escalation series, we will see some practical example of kernel exploits to discuss more about this idea. So I hope the video was enjoyable. I hope you got something out of it. If you did, leave some feedback, subscribe to the channel, and share this video with like-minded people to help me grow. And that's it. To the next video. Hi everyone, and welcome to this new video in which I continue my Linux privilege escalation series. In this video, we will talk about using kernel exploits. So we will introduce the idea of kernel exploitation. Now, in the previous idea, we discussed a similar thing, which is binary exploitation. So binary exploitation. And the idea of binary exploitation was that we had an elf binary, so an executable that can be run on Linux system, and this elf binary had a memory corruption issue, a buffer overflow. Specifically, we had a stacked base buffer overflow. Now, by using this buffer overflow, we were able to hijack the normal execution of the program and obtain a shell. So we were able to take the program as it was written by the developers and use it to execute our own code. And this is an example of binary exploitation. And then we discussed, if the program was owned by root and maybe had the setuid bit, then we would be able to obtain a shell as root, and therefore we would perform a privilege escalation. So the idea was that one way to do privilege escalation is you consider the elf binaries in your system, you analyze those that are vulnerable, for example, to memory corruption, and you try to exploit them through binary exploitation techniques. Of course, the exploit we developed was very simple, because the point was not to introduce the modern techniques of binary exploitation, but rather to give an idea as to how this is done, how it works in principle. And then at the end of the video, I mentioned the difference between user space programs and kernel space. So what's the difference? I mean, what is a kernel and what is kernel exploitation? So we can start with this question. As always, I hope the video is enjoyable. If you find it so, please leave some feedback, subscribe to the channel and share this video with like-minded people to help me grow. Thank you very much and enjoy the video. So, what is a kernel? Now, the kernel is one of the lowest software layers found within a modern operating system. So we're talking about software, but at the same time, we're talking about one of the lowest software layers in the abstraction stack that is built in modern computers. Now, what is the kernel used for? When we talk about software, usually software is written to abstract over something else. In particular, the kernel is used to abstract away from the firmware and the hardware layers, which are complex and difficult to interact with. So what is the idea here? Let's say that we are a developer of a video game and we want to write code for a video game. Now, instead of having to know the specific details of the machine that we will be run on, which we would need without kernel. So if we had no kernel, all programs that we write, we will have to know all the details of the firmware and the hardware of every machine they will run on. And this, of course, is really difficult because you're just a developer, you just want to make a game, you don't really care that much about the hardware details of the computer of the people who will buy your games. So over time, over the years in the history of computer science, people came up with this idea of a kernel. The objective of the kernel is to interact with user space programs, is to give user space programs an abstraction over the hardware and the firmware. So the kernel therefore acts as an abstraction layer on top of which modern software runs. So that when I, game developer, write a new game, I will just use the APIs offered by the kernel and I will stop there. I will not go below that layer, I will not go below that level, which means that all the firmware, all the drivers and all the hardware, I will not care about that too much. Maybe I can put some hardware requirements, but I will not care about the specific hardware details of the machine I'm working on. It's just gonna run. Why? Because when the user space asks, for example, write in this memory address, write a pixel on the screen, the kernel is able to translate this abstract request into the operational procedure needed for interacting with that specific monitor, with that specific memory RAM, and so on and so forth. And this picture essentially represents what we just said. User space programs do not talk to the hardware or to the firmware, rather they talk to the kernel. And it is the objective of the kernel to translate the request with the appropriate language and so on and so forth. So for example, let's say that we have this very simple program. So here I've written into the simple.c file. It's a really simple program, as I said. It just prints a string essentially. And we can compile this with gcc simple.c -o simple and then n to execute it. Very, very simple. We just print a string. Now, anytime we have a simple C program that prints a string as the one shown below, like this, with printf hello world, internally, this program will make use of system calls, which are APIs implemented and offered by the kernel to interact with the underlying machine. So the abstraction layer that is between the kernel and the user space program, such as this one, the one we just executed is a user space program, and it prints a string hello world. This API is made up of system calls. So the single functions are called system calls, which means that different kernel will provide different system calls. And for example, even the Linux kernel, depending on the version, will support different system calls. As it grows, it can support more system calls, it can deprecate some of the old ones, and so on and so forth. It can even change the arguments to some of them sometimes. Now there is a really useful program we can use to list out all the system calls that are made during the execution of a given program. And this command is the strace command. So for example, here I just executed simple and we got the string, right? This seemed like a simple operation. Well, in actuality, there is a lot going on that we do not see. If we want to see, for example, all the system call that the user space programs makes to the kernel, we can use strace and then we do simple. And notice what we get here. We get a bunch of lines here. Now, each line is representing a different system call. And the way that the strace prints them out is for debugging purpose. In particular, for example, the first system call we make is the exec_va system call. This is used to start a new program. Essentially, what the shell does is first it forks its own process, and then in the new forked version, it's gonna do an exec_va. So it's gonna like clone itself, and then in the new copy, it's not gonna execute the same old shell, but it's gonna execute the new program. And here we see the arguments that are used for the system call. So we see, like for example, this is a memory address, because sometimes in C you have pointers. So here we put here strace prints out the memory address that at time of execution was the value of the pointer variable. So we have this exec_va, and then here on the right we have the return value of the system call. Then for example we have brk, we have access, openat, fstat, mmap, which is used to map memory areas, close, openat, read, pread64, fstat, once again mmap, a bunch of mmmaps. It's like arc, prctl, set id address, set robust list. This is all to say that there's a lot of interaction that the C program makes with the underlying kernel. And finally, there is the write system call, which is the one actually used to write to the screen. And here we put this one here as first argument, which represents where we want to write the string. In this case, 1 stands for standard output. It is the file descriptor, the ID, that represents the standard output, which in this case is simply the shell. We are simply printing a hello world. So this is all just to say that even the simple act of printing a string actually requires a lot of interaction with the underlying kernel. Now, why do we care about that? This is the interesting part. So why are kernel exploits especially dangerous? Now, since the kernel has to interact with the underlying hardware and firmware, it requires a lot more privileges. This is natural. It requires to be able to configure the processor in a certain way, like to configure the entire machine in a certain way. The kernel is essentially the orchestrator behind all the interaction that the computer makes. Therefore, it has to have like root privileges, administrator privileges. But remember that the kernel is written in software. Software is a software, and all software can potentially be vulnerable. I mean, even hardware can be vulnerable. However, to exploit hardware, you need a different set of assumptions. To exploit software instead is much more feasible. This means that even code that runs in kernel mode can be vulnerable. And code that runs in kernel mode is run with a higher privileges. So a kernel exploit is a malicious code that uses a vulnerability found within the kernel code, so found within code that is executed in kernel mode, in order to once again hijack the normal flow of execution and execute arbitrary malicious code. This time, however, what is attacked is the kernel of the machine, meaning that the attacker is able to change the underlying configuration of the operating system. It is very different from attacking a user space program, because you are literally inside the kernel, and therefore, for example, you can hide certain stuff, you can disable certain protection mechanism, and so on and so forth. Given you have a more underlying access to the system, you have also more power. It also means that doing kernel exploitation is much harder. To make it simple, in practice, this means that a successful kernel exploitation can result in obtaining a root shell. Of course, this is like very simplified version. In general, kernel exploits are extremely dangerous, also because of rootkits, for example. So the idea is that a rootkit is a malicious piece of software that is installed in your system and that is used to like monitor your activity within the system, to exfiltrate data from your system to some attacker machine, to wait maybe for a specific time in order to attack, to inject payload, and so on and so forth. And rootkits can be installed once you have root privileges and once you're able to inject malicious code in the kernel. Now, of course, there are many different kernel exploits that historically have been found, so there are known vulnerabilities in old version of the kernel. New ones are being researched right now, and they will be published like in the future and so on and so forth. So one of the things that is important to do is to enumerate the kernel version. This is actually pretty simple. You can use the command uname-a. So you can just use this command, and among here you find this Linux, here the host name, and here is the kernel version, like 5.15.0. So this is the kernel version. You can also use, for example, in my case, uname-r, and it just gives me the specific kernel version, 6.9.7. So to showcase a practical example of kernel exploitation, I brought a little example taken from one of the machines in ActedBox. Here we're talking about the Valentine machine. I did not make a full playthrough on this machine, it is a bit old. Maybe in the future I can do. If you're also interested in that, write it in the comment and let me know. So the idea is that this machine, for the final part of privilege escalation, can be approached in different ways. There is an intended way, and there's also a way with kernel exploitation. So we can just go and actually do the machine. Here, essentially, I am within the machine here in Valentine. So I can say hostname, Valentine. I will not show how to get here. I will just show how kernel exploitation works with a practical example. To get there, essentially, first you have to find an SSH keys, but that is outside the scope of this video. So at this point here, we are inside the machine, and the first thing we can do, of course, is to enumerate the kernel version, because to do kernel exploitation, you need to have a vulnerable kernel version, and also you need to have a specific kernel configuration. So when it comes to kernel, there are two things. There is the version and there is the configuration. Now, the configuration for a Linux kernel is extremely complex. It has a lot of different flags because the kernel supports a lot of different hardware platforms with different sort of requirements and behavior, sort of. So you can have kernel configured in a certain way for a certain traffic, for a certain processing, for a certain type of data processing, and other kernels for more normal usage, and so on and so forth. So sometimes exploits do not work. This is typically not easy. Of course, it's also important to mention that you must be extremely careful when trying kernel exploits. And in particular, you should not try kernel exploits if you should not make the system crash. It's like, if you don't want the system to crash, be extremely careful about trying kernel exploits. This is because if a kernel exploits crash and it doesn't work well, the entire system will crash down and you will have to reboot it and to re-execute it from the start. And this is essentially what happened with the recent CrowdStrike accident. They had a bug in a module of the kernel. It was the Windows kernel for sure, but it doesn't really matter at in this case. Anytime you have a bug in the kernel, you have a kernel panic and the entire system crash down. This is very different from when you have, for example, a bug in a user space program. It's different because a user space program is actually managed by the kernel. If the user space program crashes, the kernel is able to recover the situation, to recover the memory, to recover all the resources that was used for the program, and to assign it to different processes. So there's no real loss. If a single program crashes, you just lose the data for that single program. If a kernel crashes, if the kernel code crashes, if you have, for example, a crash, an exception, an error in kernel code, the entire system will crash down too. So be extremely mindful and careful when you try kernel exploits. So let's enumerate the version for this particular kernel. So let's do uname-a. We got a kernel that is 3.0 3.2.0, so much older than the current one, because the current one in my machine is like 6.9, this is 3.2, so 3 major version behind. And this machine also runs Ubuntu 12.04, so very old Ubuntu. Now, perfect, we have this kernel version. At this point, we can use an utility in Kali. So here down I have a shell in Kali, where here up I have a shell in Valentine. So we can use a utility in Kali, which is called search exploit. So it's called search exploit. How does it work? Essentially, this is a simple command line interface that searches an online database of exploits. I think that this online database is actually downloaded locally, but essentially you have this search exploit. You can just do search exploit and then Linux kernel and then the version 3.2. And then here you have a bunch of results essentially that says, look, all these exploits are for example, this one is kernel version 2.6 until 5.9, 2.6 until 3.9, 2.6 until 3.9, like Dirty Cow. Dirty Cow was a famous kernel exploit that is a race condition in the way that copy on write mechanism was implemented by all versions of the kernel and a lot of other exploits. Now, among all of these kernel exploits, we're gonna use actually the Dirty Cow exploit. So what is Dirty Cow? Dirty Cow. I will not show it fully, I will not discuss it fully, we will just use kernel exploits, we will not implement it. Maybe in the future I can implement something like that. Anyways, the idea is that this Dirty Cow was a vulnerability, specifically it was a race condition in how the kernel internally handle the copy on write mechanism. So what's the idea of copy on write? If, for example, you have two variables like A, which is like hello, and then B, which is like A, initially these point to the same memory area. Because B is just A unchanged, so there's no need to make a new copy of A and assign it to B. They literally point to the same memory area. It's like if you consider the memory, for example, this is the hello, it's written in memory here, at a certain address like X, A points to X and B points to X as well. When you make a change, so when you say like B equals hello world, so when you change B, at this point, what's going to happen underneath is that the kernel will make a copy for the string hello, and then it will change it. So it will make a new copy in memory. Essentially, they exploited the way this mechanism works, and in particular, they had this race condition where, using this race condition, they would be able to overwrite files in the file system that were only readable by the user. So you had a readable file, for example, the etc passwd file. This file can only be read by a user. It cannot be overwritten. Like here, the only one who can write it is the root here. But a general user has only read permission over this particular file. Thanks to this copy on write mechanism and to the race condition that the kernel contained in the handling of this copy on write mechanism, a user will be able to overwrite this file and add arbitrary strings, and this essentially allows you to add a new user with a UID 0, which means to add a new root account. So that's the general idea of the exploit. So here I lost myself, I think this is 2 and then this is 3. And then, okay, here, for example, so yeah, so we're gonna use this Dirty Cow exploit. Now, of course, there are many copies of the exploit. We will use this, this one, essentially. We will use this here. On the right, there is this 40839, which is like a unique identifier for the particular exploit. So the way we can obtain it, essentially, is by doing search exploit, then we do -m, and then we put this ID, 40839. And it says, look, this is the Dirty Cow ptrace poc data race condition privilege escalation. Here is a link to the exploit. Here is a link to the local file. Here is the URL where you can find the exploit. So if you just go here and we just go to the URL, we find this Linux kernel exploit. So this exploit uses the Pokemon exploits of the Dirty Cow vulnerability as a base and automatically generates a new passwd line. To use these exploits, modify the user value according to your needs. The default is firefart. So essentially it's going to create a new account named firefart. Original exploit, Dirty Cow betrays Pokemon bypass is this one. So this one is the original exploit of Dirty Cow. Echo Pikachu Pokeball, so this is it. And essentially to run, so we can compile with this and we can run with that. Afterwards, you can either su firefart or ssh firefart. Don't forget to restore your Passwd. So this is essentially this is the idea. And this is the main. This is the main. It's gonna make a backup file. It's gonna set up the user info struct. It's gonna enter the password for the new user. It's gonna generate the hash. It's gonna generate the complete Passwd file. And then at this point is the actual exploit. So this is the finish of the exploit. Here we create a copy on write on the etc Passwd. As I said, I will not go into the details on explaining this exploit. For now, we will just use it. But the idea is that these exploits are a condition to modify the Passwd file and to generate this new line that the code generates. So that's essentially the idea. So now we got it in our local folder. Look at this, it's 40839.c. Perfect. At this point, the objective is to bring it into the remote machine. So we can do that we get our IP address with the At-the-box VPN, which is 10.10.14.19. We open a Python server. So we do Python 3, HTTP server 1337. Remember the port. Then we go into the Valentine machine and we do a simple curl, which is installed. Perfect. We do a simple curl 10.10.14.19 1337. And here we put the name of the file, which is 40839.c. 40839.c, and we print it to the standard output. So at this point, we have downloaded the exploit in the remote machine. Remember that within the exploit, there was written how to compile it. So we can just read it essentially. So it says, look, compile with GCC, pthread, lcrypt. So we do this. So we need some libraries. It says, okay, dirty, because this is called dirty. We don't call it dirty. We call it 40839. And now we have compiled it. So at this point, we have compiled the exploit. It's this 40839. Okay, let's check the value of the etc Passwd. We do cat etc Passwd. Notice that we have normal users, and here we have the root user. So this is the state, and we're gonna save this into a file so that we remember. We're gonna save this into the scratch buffer. Perfect. And then we're gonna run the exploit. So to run the exploit, the idea was that we can either just run it and it will ask for a password, or we can run it directly with a new password. So we can say 40839 and then a new password, which I'm just gonna say password, very simple. So let's run it. It says etc Passwd successfully backed up. Please enter the password, complete line, mmap. So essentially the exploit worked and it added this particular line to the etc Passwd file. If we just terminate the process and we just cut out the new bash, the new Passwd, essentially notice here, it changed the file and now there's written firefart. So now we can do su firefart. It's gonna ask us for a password and we're just gonna put the password that we entered previously here. Password, and we have a root shell. The username is firefart, but the ID essentially is 0, which means that we can go to the root directory and here we have the root flag. And so we have successfully exploited this machine. This time, however, we did not use a binary exploitation, we use kernel exploitation. We use a kernel exploits, that is, we exploited the logic that is implemented within the kernel. Of course, we did not do it manually. We use an exploit written by researcher, by other people, and so on and so forth. But the idea is that what was vulnerable here was the actual kernel code. So this is the way we got in. It's kernel code that allowed us to obtain execution as root. Specifically, it allowed us to obtain a write primitive on any file of the system as root. But if we have that, we can modify the passwd file to obtain, to sort of set up an account with root privileges. This attack also uses an interesting fact on how the etc Passwd is handled. So if you notice here, all these rows have in the second column an X. Like for example, hype here is an X, gnat is an X, irc as an X, backup as an X, www, like all these have an X. However, Firefart does not have an X, but has an hashed value. So when a user does not have an X here, it's going to be treated as the hash of the password. So sometimes it's not look the etc shadow, which typically contains the hashes. The hashes can also be put in the passwd. And this, I believe, is done for compatibility with older system. So if you're able to just write in the Passwd, you can trick the system into authenticating with any user, and you can also choose your ID here, which is 0. So with 0, it means root. It means we have root execution. So essentially, this is the idea for the exploitation. And in these notes, just take note of this. So just this is it for the practical example. So this is it for this video. Here are some references. In particular, there is the walkthrough by 0xdf of the Valentine machine. Maybe in the future I will bring a video walkthrough of it. If you're interested, just let me know. And then some references on dirty cow exploitation, specifically the 2 exploits, the one we use and the one that was referred in the one we use, and also a blog post describing the vulnerability, which is written in a pretty clear way, so it's very easy to understand. So the takeaways for this is that exploitation can not only happen in binaries running in user space, but also in binaries running in kernel space. Of course, kernel exploitation is much more harder than normal binary exploitation because you cannot interact directly with the kernel. You are a user space program. You can only interact with the kernel indirectly through system calls. However, in kernel code, there still could be vulnerabilities. So by doing a lot of research, by doing a lot of study, like this kind of exploitation is extremely hard. I'm nowhere near to be an expert on this. But what I know is that with enough effort, sometimes certain vulnerabilities in kernel code can be exploited to obtain privilege escalation, to obtain execution as an administrator of the system. And this actually applies to both Windows and Linux. However, this is the Linux privilege escalation, so we'll stick with Linux. So this is it for this video. I hope it was fun, I hope it was enjoyable, I hope you learned something from this. If you did, please leave some feedback, leave some comments, tell me what you think of it, tell me what you want to see in the future, share this video with like-minded people, and see you to the next video.